Okay. So in Module 3, we're going to learn how to tell the difference between step growth and chain growth polymerizations. We're going to talk a little bit about addition and condensation, which is sort of older language, but you still see it a lot. So step growth and condensation are almost synonyms, and chain growth and addition polymerization are almost synonyms. Okay, so I'm going to take these two polymers. They look way different. One's PET, one's polyethylene. I'm going to put them on separate sides. Okay? This one, where does this one go? To the left? Yep. What about that one? What about that one? Yep. That one was in the quiz. Right. And this one sometimes gives people a little bit of trouble because they see the ring. They see all the rings in the other one. The ring is not in the backbone. It's a side group. So you're correct. It goes to the right.
What? Oh, yeah, it is.
That goes to the right. It's the oddball because it has that double bond, but that's made from butadiene. So it goes to the right, and that one goes to the left. So you guys knew how to do this pretty intuitively, right? You've seen it a couple of times. We talked about it during the quiz. And so the ones on the left are step growth polymers, and they are more complicated in general, and they have a functional group somewhere in the backbone. So here we've got that ester. Here we've got a carbonate. That's polycarbonate. Here is an amide. This is Kevlar. This is also an amide. This is Nomex. This is also an amide. It's nylon. Okay.
Is it nylon 6/6?
I think so. 1, 2, 3, 4. Yep. Nylon 6/6. Okay. So we really sort of covered this already today when we talked about the quiz. So which do you think we covered the more expensive, the step growth? And then what's the big thing you can notice about the difference in the backbones? The rings and functional groups are in the backbone are only on the left. So they're on the right, it's an all-carbon backbone, all carbon, where the step growth have some kind of linkage, some kind of organic functional group is linking them together.
What do you mean by functional group?
Alcohol, amine, ester, amide, that's a organic functional group. So not a methyl group, not a CH2, something that's going to be more reactive. So, step growth polymers, we also can call them condensation polymers. Condensation implies that a small molecule splits out during synthesis. And it's the way we originally classified polymers was condensation. But polyurethanes, I don't have an example on here, but polyurethanes, their kinetics and their growth profile is step growth, but they don't split out a small molecule, so you can't call them condensation. And so using the terms step growth and chain growth it makes more sense, and it also makes more sense when we start talking about kinetics, because it's more related to how they polymerize. So now there are exceptions. You can have a chain growth polymer, pointing at the wrong thing. You can have a chain growth polymer that has a functional group in the backbone, but that would have been made through ring opening polymerization, more than likely. Okay, so we are not going to cover ring opening polymerization in TE200, and we are not going to worry about any exceptions to the rule of thumb that an all-carbon backbone is chain growth, and if you see a functional group, step growth. Just know there can be exceptions, okay? But that's beyond this class, okay? All right, so we've got that step growth, or condensation polymerization, chain growth or addition polymerization, and then that ring opening polymerization. So nylon 6,6 and nylon 6 are super similar, but they're made in totally different ways. Okay? So we're going to start with step growth polymerizations. Learn a little of the basics. Okay? So we've got, with step growth polymerizations, we got two types. We've got AABB, where I take something that has an A functional group on both ends. So it's AA. There's an A on each end. And then I have a monomer with two B functional groups, one on each end. Those polymerize. That gives me that perfectly alternating copolymer, right? So this would be like PET. This would be like nylon 6,6. We can also have an AB type, where you have an A on one end and a B on the other end. And the classic example is an amino acid. You have an amine and an acid, and you can polymerize it. If it's a natural amino acid, we can call it a peptide, right? So, but it's a polyamide, right? So we can have that. We can also do that with a hydroxy acid and make a polyester. Okay. So for this AABB type, we have bifunctional monomers, and they polymerize, where only blue can polymerize with, oh, it used to be gray. I made it orange now. Blue can polymerize with orange. Orange can polymerize with blue. They can't react any other way. Somebody in here had some squigs that reacted this way, right? Blue could only react with red, and red could only react with blue. Okay, so that's mimicking this type of reaction. So this forms step by step, right? We got dimers. Oh, it is animated. Okay, we've got dimers forming, and they just sort of slowly form. Eventually, we start linking more and more together. We get trimers and other low molecular weight Xmers, and then they start combining, and we start to get higher and higher molecular weights. Okay? Step growth. Stepwise. Any A can react with any B. Any A can react with any B. And the monomer is usually gone pretty fast. Okay? Because it's going to react. It's going to run into an A or a B, and it's going to react. The monomer is usually consumed pretty quickly. But the molecular weight grows very, very slowly. Okay. So again, we've got our AA. Here it is in an actual chemical structure. There's our AA. Here's our BB. And it reacts. Here, I'm not showing any small molecules split out, but here you see that there is a small molecule that comes from the chlorine and the hydrogen, okay? It's not water. Doesn't always have to be water. In this case, we got HCl. Sometimes it's an alcohol. Often it's water, HCl. That's what's common for the small molecule byproduct, okay? So the chemical structures we're not worried about until the second exam, okay? We're worried about big picture right now. All right. We already covered this. The second type is the AB type, okay? So now the blue can react with the orange. We form dimers. Eventually we start making some trimers, more dimers, and it's not until we get to high extent of reaction that these small oligomers start linking together into higher molecular weight chains. Okay? So we have to push these, all step growth reactions, you have to push to high degree of conversion or you won't have many repeat units. Okay? So here's that example. So there's our AB monomer. Here's our AB monomer. It can react with itself. The amine reacts with the acid. A small molecule of water splits out as the byproduct, and we make an amide. Okay. There's the summary. Here's some very well-known step growth polymers. So we've got polyethylene terephthalate, PET, nylon 6,6, polycarbonate. That's your shatter-resistant, bullet-resistant glass, polycarbonate. Kevlar, the fiber that's going to be in your sporting equipment, also in bullet-resistant vests. Why do I not say proof? I don't say bulletproof.
Because it's damaged. Yeah, if you shoot in the same spot twice, it won't go through.
Somebody can always get a bigger bullet. Okay? You got high enough caliber, going through. Okay? So it's resistant, and I didn't, I came here, I was sloppy with my language, but we have the Textile Protection and Comfort Center, and I learned that you do not say bulletproof. We say resistant. Okay? So looking forward, when we move into Module 5, which will be after our first exam, we're going to learn about polymer synthesis. So I want you to look at these monomers. Are these going to be AABB or AB monomers? So what's this one? AB. What about this one? And this one? Yep. What about this one? AB. What about these two? So the color helped, I think, right? But you can see, right? We got an amine and an acid. That's an AB. They're different. The two ends are different, right? That's all we're looking for here. Okay? All right. So, do you think, now we're going to figure out, are these AABB polymers or AB type polymers? It's this top one, nylon 6,6. AABB. What about this one? This is PET. What is this one? AABB. So here I kept the whole monomer together. Here I split it. See, you can see the oxygen, CH2, oxygen. That's from one monomer. And then this is from the other monomer. So yeah, that's AABB. What about this one? What about this one? Yeah. And this is Kevlar. This is something very similar to Kevlar, or very similar to Nomex, but not Nomex. Okay. Chain growth polymerizations. Switching gears. Chain growth polymerization. The stars are my initiator. The initiators put an active site on the first monomer. That step is called initiation, okay? When you have an active site on the first monomer, that is the initiation step. Then we have to grow the chain. That's called propagation. And what happens is it grows fast, okay? It grows fast and then it dies eventually. A second chain can get initiated. Oops, I made it go too fast. Okay? So First reaction. So let's compare this to step growth. Step growth. Any A can react with any B. We have one reaction. A reacts with B to make the polymer. One reaction. Chain growth, first reaction is initiation. Second reaction is what? Propagation. Third reaction is when you kill the active site. Termination. So we have initiation, propagation, termination. Okay? So these monomers typically have a double bond that you're polymerizing. There's typically a lot of monomer left at the end of the reaction, right? I didn't probably leave enough in this schematic, okay? There's a lot of monomer left. And the average length of the chain doesn't really change throughout the polymerization. You just get more polymer. So for step growth, the molecular weight is increasing as the reaction proceeds. Chain growth, the molecular weight of what's polymerized is not really changing. You just get more polymer as you push the reaction. So those are really big differences. You guys get that? Making sense? Because they have such different mechanisms, that's totally different. So then here's all your common polymers, right? A lot of commodity plastics are chain growth. I've got polyethylene shown up there 3 times, right? Just to make you, right? This is how, if I'm writing it by hand on the board, I'll write it like this or write like that, but we can do out all the carbons and hydrogens. And then here's polypropylene, here's PVC, here's polystyrene, polymethyl methacrylate, otherwise known as, anybody know what that one is? Trade name? Plexiglass. And PTFE, what's that one's trade name? Teflon. So this is from a book called Giant Molecules. For me, this is I like the way this visualizes the difference. So like the left, I'm not making polymer. I've got all these reactions and I end up with a 2.5 repeat units. Not very long, right? Where here, you polymerize, you got a high chain, even though that chain is not very long, but you know, that's what happens. That's the difference. Step growth, you know, you have a step growth and a chain growth. You go a few minutes, and here you've got low molecular weight stuff. Here you got some high molecular weight polymer. Okay. All right, so this is the end of, I'm trying to think. Okay, so we have this table where we're going to compare and contrast step growth and chain growth, and then a few review questions. That's it for Module 3. There's really even no reading for Module 3, okay? So we will finish Module 3 and start Module 4 on Tuesday, okay? I will make sure I go and look at the Moodle dates to try and get the Module 4 stuff on the days that I actually want you to have it done. I think that I messed up the dates so badly in Module 2. I don't know what happened in Module 4, but I'll check that, okay? But you will have some calculations and stuff to do next week, okay? Some homework, traditional problem set style homework next week. So we finished Module 3 last time, essentially. We're gonna review what we learned in Module 3, which is comparing and contrasting step growth and chain growth polymers. With this table, we're going to review it, and then we're going to do molecular weight, and we'll definitely finish the molecular weight presentation part on Thursday. And so we'll have homework due, maybe some the first problem on Thursday and the rest on Tuesday or something like that. So anyway, we were behind, and I think we're catching up. So after molecular weight, that's everything that's on the first exam. Okay. So module 1 is a lot of like vocabulary, why we care about polymers and that kind of thing. Typically don't ask you a lot of questions, but that's like you have to be able to use the language and that kind of thing. I absolutely will ask you about 3 things that make polymers different. I do that every year.
Do you have like a estimated time-ish that we'll be doing the test?
It'll be open from 3 to 5 days.
Okay.
I try and do it longer.
Yeah.
Can you do like part of the test and then stop and come back and do another part?
I will have the test broken into 2 or 3 parts, and you can do the parts. You could do part 1, and then a day later do part 2, but you have to do all of part 1 when you start it. I think you will be really happy with the amount of information I give you before the exam. I will give you what I call an exam template, where I will give you some problems that'll be on the exam, but words will be missing. And it's to give you an idea of the style of question I ask, that kind of thing. And tries to get you to be more focused in how you study. 100% I will ask you about stuff on this table. On this exam and on the final. And maybe on the second exam. Being able to compare and contrast step and chain growth polymerizations is a big part. That's something I want you to retain beyond this class. So I will ask you about it more than once, okay? Okay, so let's finish this module 3. So when we're talking about monomer consumption, which one is the monomer? So we've got 2 choices. Monomer concentration decreases steadily as the reaction time increases. So as the reaction proceeds, the monomer concentration just sort of steadily goes down. Or the monomer disappear early in favor of low molecular weight oligomers. So you're making dimers and trimers, but you're not making high molecular weight polymer. Go ahead.
Second is definitely chain growth.
Chain growth. Oh, second is definitely chain growth.
Oh wait, sorry, step growth.
Yeah. Yep. So that second one is definitely step growth when you're building it up step by step. And I knew what you meant. Oligomers steadily increase in size. Polymer's average molecular weight increases as the reaction proceeds. High polymer appears immediately. Average molecular weight doesn't change much as the reaction proceeds, but you get more and more polymer. So top or bottom is step growth. Top, bottom. Let's see it. I'm only getting a few. So the top is going to be step. And the bottom is going to be chain. So in chain growth, once a chain gets initiated, it grows super fast. And it grows to sort of the statistical average molecular weight. And other chains grow super fast, but you never have a lot of oligomers. That's only in step growth. Okay, let's look at molecular weight versus time. Long reaction times are essential to produce polymer with high molecular weight. Increased reaction time increases your yield, your polymer yield, but doesn't really affect the average molecular weight. Second one is chain growth. Yep. Excuse me. So, I get allergies in the fall, and then then it settles in here, and it's just a anyway. Definitely not COVID. Just to reassure you guys, it happens every fall. The dog and I get allergies every fall. So the only growth reaction. So what is reacting? The only growth reaction is the addition of a monomer to a growing chain. We have a reactive terminus grows, or the reaction can occur independently between any pair of species. So any A can react with any B. Top is chain growth. The reaction mixture. What's in the reaction mixture? So the reaction mixture consists of high molecular weight polymer. That term high polymer, you'll see that, and it's just it's sort of older language, but you'll definitely see people refer to high polymer, and they mean high molecular weight. High molecular weight polymer, unreacted monomers, and very few actively growing chain. Or the reaction mixture consists of oligomers of many sizes in a statistically calculable distribution. Which one is step growth? Top, bottom? See it. Yeah. So the chain growth, step growth. So the reaction mixture, many different sizes, and it's a statistically calculable distribution. We are going to calculate it. This table is set up as a drag and drop activity in the H5P module in Moodle. And again, these slides are available to you in Moodle. See people really writing. That's why I'm like, this is all available to you if you don't get it all down. Okay. So look at these pictures. Which one's chain growth? Yeah, I'm seeing people use their pointing. Yeah. Chain growth. We got a high molecular weight chain. Here we got little oligomers. That's what I'm trying to show anyway. Okay, this is the first time you've seen this. I've got the average molecular weight on the vertical axis and percent completion. So this is the extent of reaction. So the amount of A's or the number of monomers. How many have been consumed? Mm-hmm.
Is it red for step growth?
Yes. Red is step growth. Why? Why? Go ahead.
Because the small oligomers form first.
Yeah, see how it just goes up so slowly. We're going to derive that red curve, the theoretical version of that red curve soon. It's pretty easy, okay? So the blue one, the average molecular weight of the chains, so we're leaving out any unreacted monomer. It's pretty flat for chain growth. Okay, so these are some step growth polymers. That first one, is that AAB? BB or AB type? AB. How many linkages? Right. Okay. Let's look at the one right below it. AABB or AB? Do you see two amide linkages? One right in the middle and one at the wraparound? Does that make sense to everybody? The NH carbonyl. When you see two linkages, usually AABB. You see one linkage, usually AB. Okay. See that nylon up there? What's that one? Exactly right. And what about this ester? AB. It's actually usually made from ring opening, but we're not worried about that, okay? So yeah, only one linkage, we're going to say, it's, from what we've studied, it's going to be an AB type. Make sense? Everybody good on that? Okay, we've got 200 monomers. We end with 10 molecules. Which one is step growth?
Right.
One on the right. So that means that one's chain growth. Oh, what just happened? But now I gave you the answer. Why is it? Okay, what's the number average degree of polymerization? What's the average number of repeat units? Number average degree of polymerization. We started with 200 monomers. We ended with 10 molecules. Go ahead.
Would it just be the 200 divided by 10, meaning the average should be 20?
Exactly right.
I mean, theoretically. Chain growth gets a very different actual.
Okay, so what you just did, what we can all just do in our head is a number average. Okay? And so we're just taking the number of repeat units and divided by the number of molecules. You have done number averages since you were in elementary school. We are going to learn about weight averages. So the weight averages of these two distributions would be really different. Okay? Because is the number average good here for most things?
No.
Is it useful? It's not very useful in this case, right? This is extreme, right? But it's, yeah. Okay, so this is what we're going to do in Module 4. So here's the summary for Module 3, right? So our step growth, chains are built up step by step. That's why step's in the name, okay? So the monomers form oligomers. The oligomers start reacting. Eventually, we get high molecular weight polymer. All the species are involved in the process throughout. Any A can react with any B. Any alcohol can react with any acid or whatever it is that we're making. Active sites. Okay, sorry. Chain growth polymers. We have 3 reactions. What's the first one? Initiation. What's the second one? Propagation. What's the third one? Termination. Initiation, propagation, termination. So, the active site is on the end of the growing chain. When you add a monomer, the active site moves to the end. So every time you add another monomer, the active site moves to the end of that repeat unit, that monomer. Okay? And they add sequentially one by one. There's not a whole lot of active sites and actively growing chains at any instant in time. There's not a lot. The distribution of the species, we've got fully formed, no longer reacting chains. I call them dead chains. Okay? We have unreacted monomers. And we have a very small number of growing chains which grow rapidly. Okay. So after exam 1, we're going to do synthesis in detail and look at the molecular reactions. Okay. Before exam 1, if I draw a polymer structure on the exam, I would expect you to be able to tell me if it was step growth or chain growth. And if it's step growth, if it was AABB or AB. Okay? So the harder part is for synthesis is after our first exam. That is the end of Module 3. Any questions about Module 3? Oh, and I didn't download it. I actually thought I was going to be canceling classes last night, because I didn't realize that I didn't take my Allegra yesterday, and I thought I was like sick. And then I took it this morning, and I'm like, oh, no, I'm just a dummy. So, so I am still coughing a little bit, but it responds to Allegra, so I do know that it's some experimental evidence that it is definitely allergies. Although the dog has gotten over hers, makes me mad. So, all right, so Module 4, if you go to this H5P presentation, there are 2 videos. We've covered the first video on Tuesday, and those lecture notes are right here. What we're going to talk about today, the lecture notes are right here. And so, sorry. So we've got the video, some sample problems, distributions, and molecular weight, which we really covered already. And then this, I don't know, where's 11, 13, 11. So this video is what we're going to cover today. And you'll see some pop beads and stuff. And so this has, there's some extra stuff at the end. That's notes for me. But there's a solution to this question. And then that's the solution for this one, okay? So don't need that. This is what we're doing. Okay, so we covered some of this on the old slides already, right? So my mistake. This is where we ended, okay? So these equations are step growth. So I try not to use P, extent of reaction, with chain growth. You can talk about the extent of reaction for any reaction, but in here, to keep it so you know these equations are step growth, I try and use this just for step growth. And these are pretty straightforward equations. And right at the very end of class, I was like, if you put the weight average over the number average, this equation over that equation, you can pretty quickly see it simplifies to 1 plus P. And you remember when we were doing those calculations right here on the board on Tuesday? P has to be really close to 1, right? P has to be 99.5% to get 200 repeat units. Almost always we're rounding that to 1. So what's the polydispersity for almost every step growth polymerization that has high molecular weight polymer? No. 2. 2. Okay? All right. So I just have some visualization with my plastic pop beads. Okay, so remember, our extent of reaction is the initial concentration minus the concentration divided by the initial concentration. That's the extent of reaction, because C minus C naught is the number that have reacted. Make sense? This stuff is pretty intuitive if you can remember what all the variables are. But remembering what all the variables are is hard, okay? Okay, so here's our pop bead model. When I did this and I took all the pictures, I put them in my video editor to like do the stop motion and everything. I didn't count right. I have 16 AA monomers and only 14 BB monomers. So we can't go to 100% reaction. Because what happens if you have extra A's?
They're left.
Yeah, they're left. Everything ends in an A. And A doesn't react with A. So, to make the math work and not deal with negative numbers, you always have to set the A to whatever you have more of. Or you want to define the concentration of the one you have more of, or it gets messy. There's other tricks and things you can do, but anyway, it's just easier to start with. We have 32 A's because I have 16 AA monomers. That step, until I started doing this, I think was very confusing, right? Because you're counting A's, not monomers. Everybody got that? Which here, it doesn't really matter, but as you move forward, it does. Okay? So, at t equals 0, p equals 0, because 32 minus 32 divided by 32 equals 0. Got it? So our number average degree of polymerization is 1. Okay. Then, as we start polymerizing, it goes up very, very slowly. So remember, this is 43%, 44% reacted. But we don't even have, I mean, we can round it to 2. There's just not a lot there yet. There's 50% reacted, 2 repeat units. And if I go back to that 50% reacted, that the 2 repeat units, that makes sense, right? Half the A's are gone. We've only reacted half of them, so they've only linked to 1B. Now it starts going up steeper, right? Once we get to a certain point, and if I had more of the beads or, had been willing to deal with more of them, it would keep shooting up faster and faster, right? But so when we are 87.5% reacted, we have 8 repeat units. And then this reaction's done. It can't go any further. So is this helping you visualize a little bit what's going on here? Okay. So what I suggest you do is, when I took these photos, this is the question that's in that H5P presentation. I didn't have the concentration of A's equal to concentration of B's, and that was just my mistake. Now I would blame it on the cat, but we didn't have the cat yet, so it was just me. So if we add one more BB, what can we get? We can go to 94% reacted and make 1 chain, right? 16 repeat units. That was for AABB. It's easier for AB. AB, right? Because here I've got single monomers. Unless you have a chemical contaminant, right? Like if some of these were blocked, either the A or the B was blocked, you always have a stoichiometric equivalence. right? Stoichiometric equivalence. Remember that from freshman chemistry? Right? So every A has a B. So this one, you can do the same thing. And there is a sheet where you can manipulate the Google sheet that it does a force copy from the H5P presentation, and you can manipulate it and you can create this plot. Okay. It's pretty easy. Okay. So we're going to do the quiz. Why won't this move? Yes, you're going to submit it online. And so the homework, I have the deadline for 11:45 on Tuesday, right? I had it last Tuesday, but 2 days ago. But I have fixed it to next Tuesday, and that's not for you to turn it in. That's for you to have it done and bring it to class, okay? You can turn it in after we go over it. Okay, so you can just finish up what you're working on while I'm starting to talk. So we're going to go over this. Then we can talk about exam 1, when we want to do it, that kind of thing. I was looking at our online schedule. It's all messed up. Anyway, my other class, I had the wellness day a week early, and anyway. I don't know what I was doing when I was doing the schedules. It's not my strong suit. So we're going to go over this. We're just going to talk about exam and that kind of thing, and then probably end class early. Tuesday, we will go over the homework, do the exam review, that kind of thing, okay? And then maybe we're going to start my fun lecture on the history of polymer science and engineering, or maybe we'll wait and do that on Thursday. And the exam will be online, asynchronous, like you guys can take it when it works for you. It'll be open for several days. And we'll talk more about that in a minute. So let's go over this first. What's this one? MN. Next one? N sub X. The number of Xmers. So if I have 2 moles of trimers, N sub X is 2 moles, right? N sub 3 is 2 moles. M sub X, the mass of an Xmer, of 1 Xmer. M sub naught, mass of 1 repeat unit. Mm-hmm. So M sub naught and M sub 1 are going to be the same thing. I didn't make up the notation. Capital X, degree of polymerization.
Average degree?
Yeah, number average degree of polymerization. So dP sub n or X sub n, number average. What if the n was a W? Weight average. PDI. X?
Yeah. Was correcting mine.
It's the degree of polymerization.
Oh, okay.
The number of repeat units. Yep. So usually if it's a capital, you're talking about the length of the chain, and when it's lowercase, you're usually talking about a specific Xmer. But you have to check that in context. Okay, what's an overbar mean?
Wait, can we keep going from there? It just went too fast.
Oh,
Yeah.
number average degree of polymerization. and the polydispersity index. What's the overbar? Average. And when I don't open the equation editor, it's an underline. Okay? How does PDI, which is polydispersity index, relate to the weight average molecular weight and the number average molecular weight?
The weight average.
Great. So I can write this in terms of the weight average degree of polymerization over the number average degree of polymerization, or I could write it as the weight average molecular weight over the number average molecular weight. Sorry, making a mess. And that, what's its relationship to 1? Always greater than or equal to 1. And the special case of when it equals 1, what does that tell you? Every single chain is the same length, same mass. How does the weight average molecular weight relate to the weight average degree of polymerization? Mm-hmm. So you said M naught times weight average what? Divide. You could do divided by, but what if I want to multiply it? I'm going to do the weight average degree of polymerization. So this equals. Because this is the average number, the weight average number of chains times the mass of one repeat unit. The weight average length of the chain. Right, mass of one repeat unit gives you the mass of the chains, the average mass of the chains. Okay, then there's the real one, the real calculation. And I didn't give you the equations.
You did.
Oh, there they are. Thank you. Didn't give them on the same page. All right. Calculate the number and weight average molecular weight of the following. What's the polydispersity? So that's the polydispersity is trivial after we do the rest, right? Okay. So the number average molecular weight equals the sum of nx mx over the sum of nx equals, so we've got 10 times, so that's 10 moles. I'm going to put the units at the end, so I don't have to write them for each one. 10 times, I'm going to simplify this to 200. So I'm going to write this as kilograms per mole, okay? I don't like punching all those zeros in my calculator. It makes me make mistakes, gives me answers in exponential notation. I don't like any of that. So I just cross off this, and then I have kilograms per mole, okay? I find that way easier because I am not good at punching things into my calculator. Okay, so now I've got 20 times 250 plus 10 times 300. What are the units? Moles times kilogram per mole. This is, I will tell you guys this. I will tell it to you throughout the semester. It's especially important in kinetics. And I know probably 90% of you are not going to do it. But one day you'll be like, she was right. I should have been doing it all along. Okay? I'll tell you the story about when I was a graduate student. Just a second. Let me finish this. I've got sum of nx, 10 plus 20 plus 10, and that is in moles. Moles cancel. My answer is going to be in kilograms per mole. Always, always put your units in and cancel them like they're variables. Always. You've heard it before, probably in physics class, right? How many of you actually do it? Oh, yay. I know it's most of you don't. You're like, this is a waste of time. I'll tell you why it's not a waste of time. I didn't listen. I got told the same thing over and over. I'm in graduate school working on my PhD. I have spent many days dealing with these equations, putting them into the, it was called Sigma plot. It's like Excel, only better. And so it's sort of like equations. It's sort of like coding. And when I did the derivations on paper, did I do a dimensional analysis? Did I check my units and stuff? No, I didn't. I analyzed all my data. None of it made sense. I've been doing this stuff for probably pushing 2 weeks. I had an arithmetic error from way in the beginning. Tracking that down, figuring that out. How did I do it? Eventually, I did the dimensional analysis. I put the units in and figured out where I went wrong. But was it overly stressful? Was I backed up to a deadline? Was all of this going on when I could have, if I just would have been in the habit of always checking my units, it would have been a non-issue? Yes. So don't do what I did. Do it, even when it's trivial like this. One thing that's nice is it reminds me that I've got kilograms. So I'm going to, my number's going to come out in the hundreds instead of the 100,000s. Okay. So if you plug that into your calculator, if you save this top line, it's going to be the bottom, and it's going to be the denominator in the weight average. So I'm not plugging that in. Somebody tell me what the answer is. 250. Did I have to do this problem at all? Look at the average. 10 times 200, 20 times 250, 10 times 300. The steps are even. It's symmetrical. I could have just written down the answer. All right? On exams, it's always good to check that, right? Save you some time. Okay. So the weight average molecular weight, sum of nx times mx squared, sum of nx mx. Okay, here is where it's really good to drop all those zeros. It makes it a lot easier. So now I've got 10 times 200 squared plus 20 times 250 squared plus 10 times 300 squared over, right there, 10 times 200 plus 20 times 250 plus 10 times 300. Okay, so what do I have for units? I have moles times kilogram per mole. Am I off the page? Divided by moles times kilogram per mole. Cross, 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 cross. So my answer is going to be in kilograms per mole multiplied by 1,000. What do I get? 255. 255,000 grams per mole. Polydispersity index. Weight average over the number average equals 255 divided by 250. Grams per mole, kilograms per, anyway, the units cancel. This is pretty close to 1. 1. So usually when we start talking about exams, people start being like, what about significant figures? I am of the common sense significant figure. I hate it when you spit out 5 numbers or, the whole thing your calculator did. I realized that Moodle has trained you to do that. And it's bad. You should round. Now, if we look at this, there's no overbars telling us where the significant figures are, right? So how many significant figures should I have when I'm doing this? Because you're going to see data like this a lot. 2, 3, that's reasonable. 5, not good. Okay? Now, there's an exception. Do not round this to 2. Don't round the polydispersity to 1, okay? You don't want the polydispersity to be 1, and you usually don't want P to be 100%, right? You should carry out those, get the significant figures you need. Those are my 2 exceptions. Because if it's a synthetic polymer, the polydispersity can be close to 1. This can happen. But being 1 is, not reasonable. Okay. And reacting every single A to get an extent of reaction of 100%, probably not realistic. So there's where you can break the significant figure rules, right? Okay. Okay, so I have not, I wish I had gone through and looked at the exam 1 stuff and turned on that section because we would look at it right now, but I have not, so we're not going to do that. So, what will happen... Yep, you're going to turn it in through Moodle. I think I made the deadline tonight. And then, or maybe I forgot to change that one.
I don't think it's.
Oh, is it? Okay. So in the molecular weight section, go down to the graded assessments. There's the assignments. When you submit the actual homework assignment next Tuesday, this video solution and Excel sheet will open up to you. Here's what you're supposed to do today, and then that'll unlock this video. It's just what we did in class. So then, so the exam 1, this, you cannot see this yet. Okay, this is not open to you yet. Exam 1. So we're using the honor system, and it's to your advantage. If I start suspecting a lot of cheating and stuff, we'll go back to in-person, in-class exams, and nobody wants to do that, especially the final. So don't cheat. Please don't cheat. I have found that it seems to be a lot less stressful if you can take the exam where you want to and within a few day window when you want to. It seems to bring down some test anxiety. It seems to allow you to navigate conflicts without having to be like, hey, can I take this at another time, and that kind of thing. So I like doing this, but I'm not naive. I know it's pretty straightforward to cheat, and I do not believe on spying on students in their home or at the library, wherever you're going. Okay, so I will not use any like cameras and any of the lockdown browsers and that kind of thing. And like a lockdown browser, that just discriminates against the poor kids, right? Because other people have more than one device. So anyway, I just don't cheat, right? We can all get along and not cheat, right? So, and it's gone pretty well. So let's not change it this semester. Okay, so you'll have some study guides. I will redo a video that talks about like how to study, my suggestions. This is just copied from module 2 because it's important, so I'll put it in here. And then what is different than most professors is I give you an exam template that you can start to study from, okay? We will not talk about this. I will not give you any answers. I will update it to make sure that it's still going to reflect the test that I give this semester. But so there's some, are the following statements true or false? So this will be around 10 points. Each one is worth 1 point. Polymers are blank molecules, right? So just to give you an idea of like how that one's, I usually say small or large, and it's meant to be sort of break the ice, right? Have a smile on the first question. But here's really the type of true false I'll give you. Generally, as the degree of crystallinity increases, some property of the sample decreases, right? Stuff like this. Excuse me. Students like it. I'm not, as I've gotten older and, taught for a longer amount of time, I'm not trying to trick you. It's not like a gotcha moment. But this level of class, like in upper level classes, I've really moved away from exams. They don't mirror life very well and that type of thing. So I would try and do something different style of assessment. Writing, creation of a figure, infographic, stuff. That's what I do in graduate classes for sure, and usually in like 400, 500 level classes. Here at a 200 level class, it's a little bit harder because we're just getting introduced to the concepts and we're doing more basic things. And so I think a traditional style exam is a good way of testing it, but writing something that I can allow you to have an online exam, so it can't be something as simple that you could just quickly Google and not be too hard and that type of thing. It's harder than you might think. The second exam is easier because it's way harder to Google chemical structures. But so the second exam will be all synthesis. So I'm sort of talking a little bit about my philosophy and that type of thing because I want this to not be too easy and not be too hard. And I don't want you to be surprised. So I try and give you a lot of information about what I'm going to ask and the style I'm going to ask it. So 100% you will compare and contrast step growth and chain growth polymers. Just a second. And 100% you will have a table just like this with different numbers. And I will ask you to calculate the number, the weight, averages, and the polydispersity. 100% chance. Okay? And then there's all kinds of other stuff. So, what was your question?
Do we know yet what day exam 1 is gonna open?
That's the next topic of conversation. Okay, so I was looking at my phone when you were taking the quiz. I was looking at my schedule that I put in the syllabus. This is wrong. That's Yeah, it's the 10th. Okay, so Tuesday is the 3rd. And now we're butting up to fall break because I am an idiot and didn't do this right. So I can open the exam. What I would do is I would promise it would be open before noon on Wednesday, and maybe I'd get it open Tuesday evening. And have it be open, until Saturday or Sunday. If I had realized it was fall break, I would have tried harder to finish earlier so that we weren't getting into the holiday weekend. But if you've got Wednesday, Thursday, Friday, you could get it done before. And then if you want to do it over the weekend, you could do it over the weekend. So that seems okay, Wednesday. So if I have it open by Wednesday by noon or earlier, that's going to work for my friends that come to class. Because there's more of you. But you know what? You guys get the advantage. Reach out if you need something different. Okay? Because it certainly is not a problem to extend it to the end of fall break. Okay? But I don't want to just have it open. Go ahead.
So it's Wednesday to Saturday? Or what was
Sunday.
Sunday, okay.
Like to the end of Sunday or to the morning of Sunday?
The evening. I usually cut it off at 10 p.m.
That's good. I've had classes where the due date is noon or 8:30 in the morning, and you're like, so it's not really due on that day. It's kind of due the night before that day.
Right. Yeah.
It's worth asking.
I usually, sometimes, especially with my graduate level classes, we do a lot of peer review. And so I'll be like, it's due that evening, but I'm like, nobody's going to look at it before noon the next day. So, you've got sort of that slush fund there. So yeah, it will be clear. The exam will be in grade scope. I will give you a practice grade scope thing. So if you have not used grade scope, you can go in and make sure you upload something. I don't care what you upload. We're not going to correct the practice exam, okay? If you ask Zimu or I to check your answers, we're happy to do so. But we're not going to go in and do it unless you ask. Does that make sense to everybody? So you can upload whatever you want, but you will be required to show your work. You will be required to show your molecular weight calculations. Okay? This is even more important on the next two exams. But this one, you will be required to show your molecular weight calculation to get full credit. And that means you somehow have to scan or take a picture of your work and get it in the computer. Okay? So just make sure you know how you want to do that. Have that plan before you start the exam. Go ahead.
You said since we're gonna need to submit our work, is there gonna be an extra thing within the test, like folder that's just place to submit our work?
No, you submit it into Gradescope. Yep. Which is why I have the practice one, so you can try it.
So the questions for the test will be on Moodle?
You will access Gradescope through Moodle.
And all of the questions are on Gradescope.
That's correct.
We'll submit paper or work on Gradescope as well.
Yes.
Okay.
Everything gets submitted through Gradescope. You will click the button in Moodle. It will open. I believe it opens like in the Moodle window. You are now in a new website, but it doesn't necessarily appear that way.
Okay.
Everything is in Gradescope. From the grading standpoint, Gradescope is amazing. It's so much better.
Are there time limits for the parts and stuff?
There will be time limits. So we will have, so the exam will be broken into 2 or 3 parts, depending on how I get it finally, like how I have it set up. So like one part will have, you don't submit any files at all. So that would be more like taking a Moodle quiz or something like that. If anyone has accommodations, testing time accommodations, I have not gotten those set up yet. Once they are set up in Gradescope, they are set up for the whole semester. So what I will do is I will email everyone I believe that I miss some of the letters and stuff like that, but I will email everyone that I have put an accommodation in and then send an email to everyone else saying, if you didn't get a notice from me, you're not getting any accommodations. But the quiet testing area, the quiet room and stuff, that accommodation's on you now, right? Other questions? I think this is the easiest of the exams. I think the hard part is it's like a new format and you're getting an exam from me that you've never seen before. But that's why I try and do these templates so you're not getting caught off guard by my style. What else did I want to say? Oh, if you have if you're running out of time or something happens and you can't upload your work, you email it to Zimu and I, and then we have the time. We can check the timestamps if we need to, right? So if something happens, don't panic. Just email us the files. Sometimes they won't go, and Gradescope works pretty well, but there's usually, in a class of 30 to 40, there's usually one student that has trouble per exam, and we're not unreasonable. It's easier to be reasonable when we're teaching 30 and 40, even 60 students than when you're in a huge service class like Chem 101, right? So we're reasonable when we can be. So what have we covered? Crystallinity.
Step growth and chain growth.
Mm-hmm.
Isomer.
Isomerism, yeah.
Tacticity, is that?
That's part of isomerism, right?
We touched a little bit on the glass transition temperature.
Mm-hmm. So we've covered a lot, but what we've covered in depth has really been the difference between step growth and chain growth. And everything else a lot of it is like the initial stuff where we're starting to pull the pieces together so that we can, start to dive a little deeper. We're going to do synthesis, then kinetics, then what I think is the more interesting stuff, more structure property relationships and stuff like that, that we started, right? We talked about how crystallinity impacts properties. What makes a polymer crystallizable as opposed to not crystallizable? What? Yeah, so is its structure ordered, symmetrical? Can it pack together? Randomness is no good for crystallinity, right? So what I encourage you to do for Tuesday, okay, is start to study, right? Because then on Tuesday, you can ask all kinds of great questions. So what we will do on Tuesday is we will go over all of the homework. The front page of the homework is, I think, pretty straightforward. If you know the names of the variables and stuff, I think you'll zip right through it. And then there's some more sort of extensive questions than what we did on the back page today. You know, longer versions of this. So we'll start off with the homework. Then we'll review, and then we'll just have questions about the exam after that, okay? So start early, and then you don't have to put in so much time. If you do a little every day, you will spend less time than cramming the night before, okay? Research has shown this. And you'll do better. And you'll retain it longer. Okay? This is the Exam 1 section. Here are checklists for the 4 modules we covered. This is out of date. This is really out of date. This is in Module 2. The current version is in Module 2 here. I could switch to student, and then we won't see those things. There we go. So this exam template is a good place to start studying from, okay? So you can see that maybe you recognize those. And then I say, always ask some version of compare and contrast, right? And that's what this is trying to get to. So this will give you a good idea of my style. Here's a grade scope practice exam. Here's the honor pledge. And I used to always say, you know, talking about being honest and not cheating and signing an honor pledge is like, it's a research-backed method. It's been shown to reduce cheating, except for, you know what those people did? Those researchers, it's been all over NPR. Yeah, these guys that studied honesty fudged their data.
I'm sure wait, don't tell me how to blast with that.
Yeah. I didn't hear it there, but it's, it's like big name researchers at big name universities. One guy's from Harvard.
I would look at that sketchy because it's like to an extent, if I'm planning to cheat on a test, yeah, sure, I'll be honest.
It's not somebody who has a plan. It's somebody that, like, you remind somebody, what they said was, you know, you're reminding people to be honest. It stops the, like, casual looking over. Not somebody who has a plan, you're not stopping them. But yeah, I couldn't believe it. I'm like, I cite that research every time we have an exam. And then, yeah, so anyway. I still have the honor pledge. This honor pledge will, I have the 3 parts, the 3 links to the exam hidden, but there will be 3 parts, and there will be detailed instructions. It will tell you how many points and what type of question. Okay? Only one part will you have to upload anything. And maybe I'll put it into 2 parts, but with this first exam will be the only one that'll have 3 parts. I sort of like it because you can take part, and then if you're like, oh, I'm not really ready, you can study some more before you take a different part. Okay, go ahead.
Will we at all on the exam have to draw chemical structures or identify them?
Not this time.
Okay.
You'll have to calculate molecular weight. So I will, this is true for the whole semester, I will never say polyethylene and ask you to draw it. I will never give you a structure and ask you to name it. Okay? I will give you, and then this is in that exam template, I will give you 5 structures and say which one are step growth and which one are chain growth. Of the step growth ones, which are AABB and which ones are AB. Okay? And those questions are actually in the template. I just didn't give you any of the structures. So you can see exactly what I'm going to ask you. But there'll be 5 chemical structures of polymers. Okay. But, people usually do well in this first one. This is the easiest. Then the next 2, exam 2 and exam 3, I used to, when we did them in person, I did them as a single test, and it was by far the hardest test because it's 2 really hard topics. But the thing is, if synthesis is really hard for you, usually kinetics isn't. If kinetics is really hard for you, usually synthesis isn't. So I don't know which exam will be the hardest one for you, but, it probably won't be both of them. So looking forward. All right, so this is there, and then there'll be part A, B, C. You'll see, and then I can't tell you. I just took the first dose of steroids. I can't tell you how much better I feel. Steroids. I know you can't take them long term, but they work. Just that inflammation and stuff, it takes it out right away. It's always amazing when you give them to, I've had lots of rescue dogs, and I take in older ones, and they'll just be like puppies for a little while, It's amazing. Anyway, I literally took those meds not even an hour and a half ago. Feeling so much better. I'm glad I went to the doctor. Okay. Because there's not a lot they can do with a virus. So we need to go over molecular weight. Is there any questions from the quiz you guys did? How did everybody feel about the first page? Yeah? Okay, good. Okay, so a sample of polystyrene is described as having a polydispersity of 1.03. What's this tell you?
The weight average is slightly larger than the number average.
Yep.
So that's a narrow.
What?
It's a narrow MWD.
Yeah, it's a very narrow molecular weight distribution. How about anybody got something in very plain English? Grandma can understand?
The sample has a large variety of different Xmer sizes.
A large or a small?
Small.
Small, yes. Okay, plainer language.
I said all the chains are nearly the same length.
Yeah. Almost every chain is the same length. Mm-hmm. Yeah, so everything everyone said was right. But sometimes it's nice to hear it just in basic English, right? Non-technical English, I guess I should say. A polymer has a number average molecular weight. Actually, let me go back. Any questions on that first one? And everybody knows what happens if the polydispersity is 1, that means
They're all
every single chain is the same length, same mass. Okay. So number 2. Polymer has number average molecular weight of 100,000. Polydispersity of 5. It's the mass of its repeat unit, M0, 206 grams per mole. What is its weight, average molecular weight?
I got 500,000.
Right? We just need to multiply the 100,000 by the polydispersity. Okay. Same polymer. What is its number average degree of polymerization?
485.44.
No, number average degree of polymerization. So what am I doing there? Yeah, 100,000 divided by 206 grams per mole.
That's 485.44.
Okay. Yeah, you got too many numbers. Tell me 400 and what?
485.44.
Yeah, okay. So it's the number of repeat units. Do I want the 0.44 and stuff? No. 480, 485. Yeah. And it's unitless, right? Because it's the number of repeat units. It's the average number of repeat units. So it's unitless. I will take points off for units. Okay. What is its weight average degree of polymerization?
2,427.
2,000, what? 430.
Okay. How many numbers am I supposed to get for each one?
Okay, so the 100,000 technically has 1, 5 has 1, the other one has 2, the 206 has 3. So you definitely don't want more than 3.
Okay, so is this like 6 figs? I don't
This
know
is
the-
sloppy significant
Okay,
figures.
like, I
It's
don't-
not, we're not following the rules, but we're not like, I know that Moodle trained you badly when you had to type things in for physics and stuff.
Try WebAssign.
Is it WebAssign? Whatever.
WebAssign's worse sometimes because it's like you can type something in as the actual answer and you get it wrong unless you leave it as a radical.
Yeah, it's like really
You have
bad.
to leave it as the square root of whatever.
And it's not
So-
like the square
so
root
this is
of
like
7,
casual.
25,
Seriously, this is casual sig figs.
Yes.
Okay.
I do not want to see 6 and 7 significant figures just because your calculator spits it out. If you have 3 instead of 2, I don't care.
So for this problem, we had 24, 27.
Yeah.
instead of-
Yeah.
Wait, was that as in it's fine or?
It's fine. Yeah. I'll tell you, on the first exam, I won't take off points for significant figures, but I have the comment and I hit the little comment box. Okay. So those were all pretty easy. You are an engineer working for a company that synthesizes and uses polymers for a range of products. A competitor makes an identical polymer, PET, but its properties are superior. One of the organic chemists in your company comes to you one day and says he has reproduced the competitor's product exactly because it has the same number average molecular weight. A, he must be demented because he's wearing a UNC Chapel Hill t-shirt. He's also an organic chemist, and he cannot possibly be right. Coleman and Painter, that originally was Notre Dame because we were at Penn State. And that was their legitimate opinion on organic chemists. He is right, even if he is demented. An average is an average, and the samples must be equivalent. He is wrong because the distribution of molecular weights could be very different. He is right because if the distributions are different, then the average would also be different, and he would only be demented if he was wearing a Duke t-shirt. Go ahead.
My answer was the third one.
Yep.
Distribution can be very different, and that's because the number average does not take into account various monomers having different weights.
Not monomers, chains, but yes, exactly right. Exactly right. Go ahead.
I said A and C.
A and C, yes. That's acceptable. So yeah, so if you just have one average, you don't have any information on the molecular weight distribution. And the molecular weight distribution is very important for processing. it impacts the mechanical properties a lot. So you need more information. If you're buying PET to make a widget, you need to know more information. Okay. For a step growth polymerization to reach the number average degree of polymerization of 200, how far do you have to push the reaction? In other words, what's the extent of reaction? Tell me what variable, what is the extent, how do we represent extent of reaction?
1/1 minus P.
That's the number average degree of polymerization. P, right? P is the extent of reaction. So we have the number average degree. Oh, I don't have them on here. Okay. So the number average degree of polymerization equals 1 over 1 minus P. I don't know why it zooms in like that every time. And then the weight average is 1 plus P over 1 minus P. Okay, so what I have the number average degree of polymerization. So I have this, right? I want P. I have the number average degree of polymerization. I want the extent of reaction. So that's the equation I want. So I'm going to multiply both sides by 1 minus P, and I'm going to divide both sides by the number average degree of polymerization, and then flip them around, plus P minus 1 over X, so the extent of reaction equals 1 minus 1 over the number average degree of polymerization. This equals 1 over 1 minus 1 over 200. I didn't write units for the 200. Does it have units? No, because it's the average number of repeat units. So it's a number. Extent of reaction. Does it have units? We can write it as a percentage, but it's a fraction. It goes from 0 to 1, or we can write it as a percentage. So we're in good shape. There's no units. So this is 0.995. Don't round that to 1, right?
As a fraction?
Hmm?
Can we leave it as a fraction?
Yeah.
Do you want to add a percentage or no?
Just make sure you put the percent sign. Mm-hmm. Yep. Yeah, so, all of those, yeah, that's totally fine. 199 over 200. For the polymer in problem 5, what is the weight average degree of polymerization, and what is the polydispersity?
The XW, subscript W, is that the one where you do the casual one or no? Just want to ask. Like casual sig figs it, or do I actually?
So you never, for things, for polydispersity and extent of reaction, unless it's 1, don't write it as 1. Okay? Does that make sense? Even if you have to go out to 999.5. Right? Don't write it as 1 unless it actually is 1, because it has a very different meaning. Okay, so this problem, the polymer in problem 5, right? This equals 200. I can take this number in and plug it in, or I can simply write down 400. Right? Because what's the polydispersity index? And y is it 2? Let's do the algebra. 1 plus p over 1 minus p over 1 minus p. So I can multiply by 1 minus p over 1 minus p, right? Multiply by 1. Do we agree that that is approximately 2?
Approximately 2, yes.
Approximately 2, right? It's 1 plus 995, 0.995. Close enough to 2 for me.
So for this one, we can round it to 2.
And you lose in a math class.
No, that's not right. If we write like 1.995, is that okay?
Yeah, that's also fine.
I again left mine as a fraction of 399 over 200.
Yeah. You might be lazier with the calculator than I am.
Didn't use a calculator. I just
Yeah. It's pretty easy to do in your head too, though. Okay, so then if you plug 0.995 right into here, what do you get? 399, 398? 399. Close enough. Right? Make sense? Right. Well, so on average, for any step growth polymer that hasn't been fractionated, that hasn't had something done to it after, you have to do some kind of chemical procedure after it's been made. Its polydispersity is going to be right around 2 because of this. Does that make sense to everybody? It's like it's embedded in these equations. Because if you have a decent number of repeat units, P is damn close to 1. Right? Everybody. Okay. Calculate the number and weight average molecular weight of the following. You will have that table with different numbers on the exam. I will ask you this. I'll tell you that right now. Okay? I will ask you number average, weight average, and polydispersity. Okay? So here, we'll start with the number average. Number average molecular weight. The sum of nx mx over the sum of nx. Do you need to know that equation? No. I will always give that to you. Okay, so I've got 15 times 300 kilograms per mole, because I don't like plugging all those zeros in my calculator. 20 times 550 plus 10 times 600. So that is moles times kilogram per mole, right? And then I have 15 plus 20 plus 10 moles. Who plugged it in? Go ahead.
478 kilograms per mole.
478. And then I'm just going to put the zeros back on and write grams per mole. Oops.
Is it fine if we just leave it in kilograms?
Absolutely, as long as you have units written. Mm-hmm.
If I rounded to 480.
Totally fine. Totally fine. Okay. MW. Sum of nx mx squared. Sum of nx mx. If I saved this in my calculator or I wrote the number down for the top, I just need it for the bottom now. So I've got 15 times 300 squared. If you get some huge number, make sure that you didn't do this. Okay? This is no good. 20 times 550 squared plus 10 times 600 squared. 15 times 300. 20 times 550 plus 10 times 600. And this one, let me do the units right here. So I've got moles times kilograms squared, moles squared, moles kilogram per mole. And that is all going to cancel down into kilograms per mole. Check. Okay. Who's got a number?
510,000
Grams per mole. I don't know why we don't do polymer molecular weights in kilograms per mole, but it's not convention. There's certainly nothing wrong with it. If you are looking at proteins and stuff, you will see, anybody know the unit of a Dalton? What's a Dalton?
Oh, I just know where they're applied.
Yeah. So a Dalton is a gram per mole. That's all it is. I don't know who Dalton was. But anyway. So proteins are, their mass is usually given in kilodaltons. So I don't know why. Okay. What's the polydispersity? I don't think I asked you for it, but.
Isn't it going to be 510 over 478?
Yeah. So 51 divided by 48. 48. Is close to 1. And look at the data. 300,000, 550, 600,000. I was like, oh yeah, I'll make this polydisperse. It's still not very dispersed. Doesn't have a very broad molecular weight distribution. Okay. The last one. Is the last one too complicated for me to put on an exam? Yeah. Maybe not anymore. I could give you an Excel sheet with data in it. But since we're doing it online, but back in the paper days, I still think about exams in terms of paper. This is way too complicated. Okay? So. I've now downloaded it more than once. I need to exhibit more patience. Okay, so here's our data. NX. Oh. I already had it open. Oopsie. Okay, so 5 chains, degree of polymerization 10, 25. This is our data right here. So this, the number of chains is the number of Xmers. So N sub X, right? The length, how many repeat units do we have, is X. And then remember, we had this equation, right? But if we wanted the number average degree of polymerization, we just have to convert every M into an X. Okay, so now I have that is going to equal the sum of NX times X over NX, right? And the weight average, I got to make that an X, I got to make that an X and that an X. Okay. So I need X times NX for each X. And N naught is like how many we started with. That's the sum. Well, that's like, that is the sum of this column. So the sum of X times NX, the sum of NX times X, or X times NX, doesn't matter. The sum is right here. And then we need to divide it by the sum right here. So that sum is 25. That gives us our number average degree of polymerization. 2,860. And I will make this bigger. Okay. To get the weight average, so we need this sum, right, is going to be our denominator, which is right here. And then we need NX times X squared, which is right here, summed. So I've got the sum over the sum of that. And I get 36,000. Okay. So now we've got a very big polydispersity index, right? 12. Is this chain growth or step growth? Step. No. Sorry. Step growth of polydispersity is always going to be around 2. So this would be a chain growth polymerization. To have that kind of polydispersity, it would be chain growth. And it probably would be a not very controlled chain growth polymerization. Like maybe free radical polymerization or something. All right. What else did I ask you on here? Okay, we calculated the number and weight average degree of polymerization and the polydispersity of this collection of chains. If these chains are methylmethacrylate, polymethylmethacrylate, what would be the corresponding number and weight average molecular weights? The molecular weight of this repeat unit is 100 grams per mole. Well, that's pretty easy. We just multiply by 100. Oops, that one's not there. Equals. Okay. Add 5 more chains with a degree of polymerization of 10 to to the above distribution. Okay, degree of polymerization of 10. So now I'm going to add 5 plus 5. So now I've got 10. Did the number average molecular weight change much?
By about 10,000.
Or, yeah, the number average degree of polymerization, right? So we went from 2,860 to 2,750. But what happened on the weight average? Almost nothing, right?
5.
It's in the rounding error, right? The weight average really didn't change. It doesn't care about those low molecular weight chains. It just doesn't care. Instead of having 5, let's have 20. Let's add 20. So we got 25. So 36,000 is the number of repeat units. Still 36,000. It doesn't care. All right, so let's put 5 on the highest molecular weights. Now we got 10,000. Now we have 10, sorry, of 50,000 repeat units. Look at what happened. It changed a lot. So the whole point of this was to get you to think about the big chains impact the weight average way more than the little chains. Does that make sense to everybody? Right? If you go back to the elephants and the mosquitoes, we went from 2,000 to 10,000 by going from the number average to the weight average. Those mosquitoes just didn't impact the weight average at all. Make sense? So this Excel sheet you can download as soon as you upload your problem set. Okay. So don't forget to upload your problem set at some point. And
You have to upload it right now.
no. Okay, so let's start thinking about the exam. First of all, does anybody have any questions on the molecular weight calculations? Go ahead.
So this is technically connects to the exam. So for the exam, how we put like the numbers, like do you expect us to do the casual sig figs or like
Yes.
exact? Okay, but what if you like give one more digit than you're supposed to?
That's why I'm saying it's casual. It's not.
I don't know what.
But then follow the significant figure rules if you want to.
This still doesn't help at all. But okay, whatever. Right, I'll try.
So the homework you just submitted,
Mhm.
that we just corrected, is it graded, or is it like the pop quiz, where it's just like you submit it and you get the credit?
Sort of in between.
Did you actually bother to correct it? Level of thing.
We grade for effort, not for correctness. So if you have attempted every problem, then you'll get it's a 4. That's how we enter it in the sheet. It's a 4.
And the test will be open until Saturday?
Sunday. And then I appreciate that it's fall break, and I'm sorry my scheduling was bad. So if you are going out of town for fall break and you want to take it when you get back, you just need to email me before Sunday at midnight, okay? That I don't appreciate, but
How long does the test usually take?
I will give you. I try and make sure, especially when you have to upload something, that I'm overestimating how long it will take. There will be how many minutes I think it will take you for the 3 parts. The amount of content I am testing you on is what is I'm trying to make it the equivalent of what I would do in a 70-minute class period. But if you add up the 3 sections, it will be more than 70 minutes because you got 3 sections. You got to get into it and read it, and you got to close it and submit it, and So anyway, it's going to add up to more than that. But I would think actual taking would be probably less than that.
And you said we don't have to take the 3 parts back to back to back.
Correct.
You can take each part whenever you want to.
You could take them in any order too.
Okay.
So.
Does each part account for a different lesson, or are they
No, it's more style of question. Okay, so only in one part will you have to upload anything.
Okay.
Does that make sense? Yeah. So in this case, the molecular weight questions, I will ask you maybe some easy molecular weight questions, like on that first page where it was 100,000, polydispersity is 5, what's the weight average? I might ask you like that in a multiple choice question, and that wouldn't be in the calculations section.
Oh,
okay. So I used to have the first part be totally auto-graded, but now I think you have to explain a few times. So you might have to type a brief explanation, and I will tell you over and over to be brief. I don't want a brain dump. Okay? When I'm telling you to be very brief and say, I do mean it, and then sometimes I will give you instructions that says, you can answer this question in a phrase or 2. I mean that. Or I say a few sentences or less. Okay? Being concise is an important part of scientific communication.
For the first part of the homework, and there were a ton of correct answers, or the first explain this, is that okay, or do you want it in simple terms, or are you gonna explain that on the test?
What do you mean?
For the question on the homework that you gave us when it said explain this, or in order.
Oh, yeah. So what does the polydispersity of 1.03? As long as your answer is correct, I don't. You can answer it any language you want. Yeah. But I think it's really important in here to just be every chain is essentially the same length, right? So. Okay, so studying for the exams. We have quizzes, homework, and then any of the review H5P questions, okay? And we did them in class as the wolf and the pack, remember? Okay, so introduction to polymers, right? We've got, if we go down here, a lot of this, I should turn it back to the student. So this one is really so there's this, right? So I am not going to ask you to define any of those terms on the exam, but I expect you to know what, I might use those terms and you might, right? Does that make sense? I will 100% ask you about how and why polymers are unique compared to small molecules. I'll ask you something related to that. And then maybe that's sort of hit or miss. Now, I think when we go, so again, here's the study guide again. And this module 2 is a review, okay? This was not required, but these, you'll recognize these questions are what we did on the board. And then every so often, there's a video talking about the right answers and talking you through it, okay? So that, that's available. And you had a pop quiz in this section, okay? This one, very short study guide, very short. The review questions are embedded in the H5P activity. And it was like, is it step growth? Is it chain growth? Is it AA, BB, or AB for step growth, right? And then the molecular weight, you've got the quiz, you've got the homework assignment. You have, in this presentation, there is some examples. There's the solutions of those examples, okay? So there's some questions in here if you want some extra practice. There is, again, the homework and the quiz. Again, people usually do quite well on the first exam. So I'm not telling you, you've got to study, but, you know, there's a lot of content, but I don't think any of it is super hard or really confusing. Tacticity can get a little bit confusing, so make sure you review that. I'll probably ask you a little bit about, like, can it crystallize or not? And it might not be that straightforward of a question. It might be like, which one is opaque, right? The one that can crystallize is what you want to pick. Does that make sense? So randomness prevents or inhibits crystallinity. Atacticity prevents or inhibits crystallinity, right? Any kind of that kind of thing. How you guys feeling? Pretty good. Questions? Yeah. If you want to ask something, everybody else in the room is going to be happy.
If we just have time, can we go over the relationship between the glass transition temperature and the different properties?
Mm-hmm. So an amorphous polymer, there's two states, right? Amorphous polymer. It's either amorphous and glassy, which means it's below its glass transition temperature, or it's amorphous and rubbery, which means it's like silly putty, or, it's gooey. Usually, an amorphous polymer above its TG is not especially useful until you cross-link it. I'm sure there's examples that I'm not thinking of, but what do you think the TG of chewing gum is?
Wouldn't it be slightly below our body temperature? Because it's very rubbery when you're chewing it, but when you're storing it, it's harder.
Yeah. If you think about bazooka, it's pretty hard. And you put it in your mouth and start to chew it, it gets softer. I mean, and part of it is the mechanical action, but part of it is it's warming up to your body temperature. So yeah. Years ago I heard a story about a drug delivery system that it released the drug due to a phase change. And so when it hit body temperature, it released the drug. But they were wanting to use this as an alternate for vaccines so that you didn't need needles in like Africa, where they don't have the same infrastructure.
It's Africa. It's really hot there.
Yeah.
They don't have the infrastructure to keep it cool.
Well, it wasn't that it didn't need to be refrigerated, but it couldn't be at 100 degrees, right?
That's one of those she was looking like, yeah, very smart, but at the same time, look at the environment.
Yeah. So, they weren't thinking that if needles are a problem to use, then you probably also don't have climate control. And so large swaths of Africa are very hot. Not all of it, but all the sub-Saharan Africa, it's very, very hot. And so it totally failed.
Can we talk a little bit about crosslinks, like on their molecular structure? Because I remember like crosslinks are the difference between rubber bands and tires, but I was a little bit confused about like how they function.
It's a traditional crosslink is a covalent bond between the polymer chains.
Okay.
So I got my slime in there. Neighbor had a yard sale. Bought a plastic egg. It's probably Bakelite. So that is like heavily cross-linked because it was made from a multifunctional monomer. But like a rubber band still has double bonds and it reacts and then you get a covalent cross-link. And like what the cross-link is not important to us right now, right? But it's a covalent thing. Yep, I see you stretching your hairband. There we go. So that has a much lower cross-link density than that. That's what I'm wanting you to take away, right? The more cross-links I have, the less movement I'm going to have, the harder it's going to become. I need a bigger Tupperware now.
Is the egg just decoration, or was it?
They had fancy, it was like they were selling a whole bunch of Christmas ornaments and Easter decorations and stuff. And I'm like, ooh, it's red and white. It looks like my NC State stuff. And it seemed like a good thing to bring to class.
I have eggs like that. Like in my house, there's like the cabinet, and there's like a bunch of different like statues and stuff. And then there's like this one basket that just has these eggs, and I always were confused. I was like, are these real eggs or something?
And my grandmother always had ceramic ones, like fancy ones. And then she had one that, and the one she cared the most about was from her grandmother's farm. And it was like an egg you put in the hen house to try and get the hens to start to lay. And anyway, but because that was from her family, but she had little egg cups and decorations and stuff. Oop. Any other questions? I am totally happy to meet with students in small groups or one-on-one. I'm not going to come to campus tomorrow, but we can Zoom. Hopefully I'll be feeling way better on Thursday and that kind of thing. And so I'll be here on Thursday. Zimu, the TA, who I know you guys probably haven't seen, but he is super nice guy. And so, like, if you don't want to ask me, you can ask him. You can also go to the tutoring center. I didn't check to see who's tutoring, but there's always someone who is ready to tutor for this class. Okay. When I last looked, it didn't look like anybody had started the exam at all. Not surprising, but anybody have any questions? I got the Moodle roster synced. I'm always paranoid about because when they first started, it didn't work very well, but now it's seamless, but I'm still paranoid about it. No questions?
We may as well make sure we get it while we're here, though.
So today is just a fun lecture. Today is the history of polymer science. It does lead into our next section, which is synthesis. So we'll see if I can get through it or not. The bronchitis is, it's like I cough less frequently but more violently when I go. So I don't know if the trade-off is good or not, but anyway. Okay. 2020. We celebrated a century of polymer science and engineering. Which is not very long in the grand scheme of things, if you think about it. Now, how long have humans been using polymers?
Always. Forever.
Yeah. Right? We've used natural polymers before we knew what they were. It goes from before we were human, right? I don't know if anybody's likes archaeology and anthropology and all that stuff. They just showed the first wooden structure that was built by not humans. No, before them. It was I think it was in Africa, but yeah. So that they had joined some timbers together, and they knew what pre-human species it was from. I'm like, that's pretty cool. And wood is a polymer composite, right? Leather is polymer, right? All the plant fibers and all of that stuff, all polymers. Synthetic polymers, we've made polymers for longer than we knew what they were. Forgot to wear my grandmother's great-grandmother's Bakelite necklace today. And then, and we've also used elastomers since before we knew what it was. And pre-Columbian cultures are the ones who showed the West what elastomers were and how useful they could be. My Bakelite egg is not in my bag either. Okay. All right, let's get that. All right, there we go. Silk, wool, cotton. We've used textiles and fibers for thousands upon thousands of years. So, natural polymers we've used forever. Synthetic polymers don't go back that far. So this timeline only goes back to 1845. So from 1845 to around 1920, we made polymers, we used polymers, we didn't know what we were doing. We didn't know what they were, In fact, people actively argued against the possibility of macromolecules. In 1920, Buddy Herman Staudinger, put forth the macromolecular hypothesis, and which essentially he said polymers exist, macromolecules exist, large molecules exist. Before that time, standard thinking was nothing over about 5,000 molecular weight. Why was that the magic number? Who knows? But that's what they believed. So we're going to talk about a bunch of these guys, and they are all men. So one of the first semi-synthetic polymers was nitrated cellulose. This was developed by Schoenbein. I'm sorry. So cellulose, right? We get cellulose often from cotton. It's not the only source, but it's a really good one. So the nitrated cellulose was supposedly made by mistake. We talked about this before. There's some apocryphal stories. So the way it was told to me was he was working in his lab, and back then you would like make your own cotton swabs. Like you had sticks and you would wrap cotton around the end. And if you're making your own cotton swabs, if it's not really dirty, you're going to save it and use it again. Not like we just single use right now. So he supposedly wiped up some nitric acid, which is a really strong acid, and then set the cotton swab near an alcohol lamp to dry so you could use it again. And it went poof. So he realized something had happened. And what happens when you nitrate something, you can go from glycerol to nitroglycerin. So it often makes things more flammable or explosive. In this case, it also made the cotton processable. You could dissolve it in solvents, like diethyl ether, which was used a lot back then. So this semi-synthetic polymer, the nitrated cellulose, otherwise known as gun cotton, and you've probably seen this in a magic show, like where they have that paper that just goes poof, same kind of thing. So the gun cotton was used to make wicks for cannons in the Civil War. They wouldn't let women into combat or anything like that, but they didn't have any problem with them making the gun cotton and occasionally getting blown up from the process. This was dangerous work, right? And this is two ladies making gun cotton for cannon wicks. This is some Civil War trenches. And this picture I know is really hard to see on the screen. Oh, it looks better than it usually does. That's a Civil War hospital. During the Civil War in Europe, most surgeons would wash their hands and clean their instruments between patients because they were starting to understand germs and germ theory. But over here, we were like, no, there's nothing you can't see. That's, even though it had been told to American surgeons and doctors, they didn't believe it. So if you got injured in the Civil War, if you were the first or the second person operated on during the day, you might survive. Maybe first thing after lunch. Otherwise, you're a goner from infection, right? Because they didn't wash their hands, they didn't clean their instruments, and injuries, most people wouldn't have died from their injuries because the weapons were not what they are today, right? You get hit by a musket ball, that kind of thing. If you had extremities, if you got hurt in your extremities, today you would survive, no problem. back then you died of infection. And crush injuries, they didn't have anything to do except for amputations. And they didn't have great anesthesia. The whole thing is horrific, just absolutely horrific. One thing they did have was nitrated cellulose dissolved in diethyl ether with a little aspirin. Has anybody used a liquid bandage? Yeah? Where you get that coating? It's a similar formulation, but it's not diethyl ether. But they had this, they called it, however you say that word, colloid. I try and put a D in it every time I say it. Colloid, I say colloidin, but it's not, there's no D.
Colloid.
Yeah, I can't say it.
That's French.
Yeah. So that solution was nitrated cellulose, aspirin, which aspirin's like a miracle drug, and in a solvent. And they would put this on the wound. And so it kept the bacteria out. So if you weren't already totally infected and they did this, you might survive. And that is very similar to compound W. The wart removing, right? Which I believe the active ingredient in compound W is one of the active ingredients is still salicylic acid, which is aspirin.
Why weren't they using the aspirin as like a pain med for like during surgery?
It's not going to do anything for pain if they're sawing off your extremity with a hand tool.
That's true. If it is like a diuretic.
Yeah, it's an anticoagulant too.
Yeah, that would be.
So, they gave people whiskey and ether. And if they weren't careful with the ether, you didn't wake up. So,
Ether is in the stuff that's theoretically outside of space.
So, here's the first of our grumpy white men with small egos. I'm being sarcastic. They all named their stuff after themselves. So Parks made a plastic. He didn't know it was plastic, but he called it Parkinson. And he was taking nitrated cellulose and putting it into molds. And he was trying to, he was using, he wasn't nitrating it to the same degree that it was totally soluble, but he was able to make it so it was processable. And what else is going on at this time? We're moving into the Victorian era. This is really the first time that there's a decent sized middle class. There's people who have some money for things that aren't necessities. And you still have the wealthy and the upper class. And these middle class people are like, oh, I would like a really pretty brooch. Well, maybe I can't buy an ivory one, but I can buy this one. Hairbrushes, combs, toothbrushes was all, people wanted stuff. Victorians loved stuff. They were like big time collectors. And so this was, trying to go after that. So if you think about buttons, these were shells and, carved and, they were expensive. You could start making them out of plastic. You would be able to sell something at a much lower price point. Unfortunately, Parkinson had scale-up issues and quality control issues. It never really took off. Then we get to Hyatt. He was, and I'm confusing this. I can't remember if Hyatt was the one who had the contest or was the scientist that should have won the contest. But part of that Victorian middle class expansion was billiards. People loved billiards. It was the thing. It was the game. Billiard balls were made out of ivory. We were wiping elephants off the face of the earth to have billiard balls. And keys for pianos and harpsichords and stuff. But it was really the billiard balls. So there was a contest for someone who could come up with an alternative for billiard balls. So back then, you might have those big, fancy, elaborate slate pool tables, billiard tables with fancy felt, and you think that's where the money is? No, it was in the balls. And they had special cabinets that you could lock the balls up in because they were worth so much money because the elephants were getting rarer and rarer and rarer. So the contest was who can make a material that can replace the billiard balls. And I'm pretty sure Hyatt was the scientist. And he did it. But he never got the payout. It was like the equivalent of $1 million. I'll have to look up those exact.
Yeah, Hyatt and Bell did. I think they'll sell it.
Yeah. And this was still some derivative of cellulose. Yes. Okay, there we go. Hyatt. So he eventually made what we call celluloid. I don't know that I'm going to make it through my second class. It was better on Tuesday. There was more steroids on Tuesday. The first day you take the most and then it tapers. It is tapering too fast for me. But she did assure me that it was very unlikely that I was contagious on Tuesday, and now it's even 2 days later, so we should all be good. Okay, so celluloid is a regenerated cellulose, or so they nitrate the cellulose, and he used a plasticizer, and this allowed for the production of all kinds of stuff. And celluloid is still used today. Ping pong balls used to be celluloid. Movie film, right? And that's why, like, old reels of movie film, like, they're trying to find them out of everybody's garage and attic and basement and all that kind of thing, because if it doesn't get preserved soon from the early days of Hollywood, this material is going to disintegrate. It's not going to be, you're not going to be able to save it. It needs to be in carefully climate controlled stuff. But if you ever see that when they're talking about old movies, this is that material. Those are caviar spoons. You're not supposed to eat caviar with the metal utensil because then it can affect the taste. So they were made out of fancy, like mother of pearl and, fancy shells and stuff. Well, if you can make it out of celluloid, it's way cheaper, right? So I think you still see knives with celluloid handles. I think probably now there's a lot of other handles, but it has a nice feel. There was, so because he moved to camphor, which is not very volatile, it's like almost like mothballs. I don't know how they got it to not smell. He solved the problems that Parks had. And so this was a commercial success, while Parkinson was not. He also didn't name it after himself, which is refreshing. So, yeah, very, very, still made and used today. this is one of my favorite topics. I think we talked about this on the question day too. Chardonnay silk. I can't remember the guy's real name. It's Count blah 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 blah. And then, but he was they called him Chardonnay. Whatever. I'm putting a D in that too. Mother-in-law's silk. This was made commercially, I think, into the 50s or 60s. And I know that in Hunt, so we used to have a textiles library in our buildings, and it's now incorporated into Hunt when they built Hunt. But there is a fabric library. It's like a special collection. You'd have to get a librarian to help you access samples, and there's a hosiery thing as well. I know there's samples of this there. So this is called Mother-in-Law's silk, and it has a very dark meaning. So this is that nitrated cellulose. This is the first time we as humans have spun something into a fiber. It's pretty cool, right? This is the first, like, taking a solution and spinning it into a fiber. Any thoughts on why they called it mother-in-law's silk?
I'm sure it's bad, 'cause, like, the whole, like, connotation of, like, mother-in-law, evil stepmother, there's a whole...
This is very much the evil.
There's a whole misogynistic, like, premise related to the whole thing.
Yeah. So, this got its name because, you buy your mother-in-law a nice dressing gown, you know, old school PJs in the nice mother-in-law silk, set her next to the fire, goes poof, because it's nitrated cellulose, so it's super flammable. Supposedly it had a really nice hand. Like, it felt really good. And it was way cheaper than silk. But it was very flammable. It was a precursor to rayon. So rayon and cellophane are regenerated cellulose. So everything we've been talking about up till now is nitrated cellulose. They have chemically modified the cellulose so that they can process it the way they want to process it. Now they're adding another step. They are modifying the cellulose, processing it, and then converting it back to cellulose. So they have to chemically modify it to get it to be soluble so they can do what they want, and then they turn it back into cellulose, which is pretty cool. And it's pretty amazing that this was easier than making a polymer from scratch, right? But we didn't know what a polymer was, so this did work better, right? So cellophane, still widely used today. Rayon, still widely used today. Rayon is regenerated cellulose. I'm old enough that I remember the original Magnum PI with all the Hawaiian shirts. And that Tom Selleck wore the shortest little shorts. It was like, you look at those pictures now and you're like, ooh. But.
One day I'm not wearing my gaudy rayon Hawaiian shirt in this class. I've worn it like 4 times.
Yeah. So now, we're finally getting to fully synthetic plastics. So this is the very late 1800s. And these were phenolic resins. And you've seen this chemistry. So this is Leo Baekeland. And he named his plastic Bakelite. And this was the first fully synthetic plastic. And it was a huge commercial success. I think you had didn't you do the Bakelite? So my great-grandmother had a bunch of Bakelite jewelry that's like up in that corner. And I think my favorite is this microphone with all the flecks of different color. But Bakelite, the material of 1,000 uses. They had a good marketing campaign. And you've seen this from either the first or second set of slides. So this is a cross-linked resin. So we have a trifunctional monomer reacting with a difunctional monomer. So we're going to make a cross-linked network. So, once this is made, you can't melt it or reprocess it. It's hard. It makes good billiard balls. I think that bowling balls might have started as phenolic resins. I don't know if they still are or not. I also don't know if you cut a bowling ball in half, is it just a plastic ball or is it all high technology? Because there's a lot of sports stuff has way more technology than you know as a layperson. Again, yeah. So crosslink. So Bakelite was cool because they could start the polymerization and make it so it wasn't like runny and stuff, and then push it into a mold and continue to crosslink it. They had to make sure it was pretty polymerized, but still enough that they could mold it. Otherwise, they'd get too much shrinkage and it wouldn't mold correctly. Go ahead.
So because it couldn't be remolded once like set and stuff, so that would mean that it's thermostat, right?
Thermosets. Thermosets. That's a vocabulary word that's important for the exam, right? The difference between a thermoset and a thermoplastic. So there's the reaction. There's more cross-linked. And here we go. Here's my buddy Herman. So the macromolecular hypothesis was put forward by Hermann Staudinger in 1920, which is why we celebrated the 100 years in 2020. So he was told this, and I can't remember who this quote is from, but it was somebody really famous, and I've got to look it up. My dear chap, give up your ideas on big molecules. There are no organic molecules with a molecular weight of more than 5,000. Just clean up your products and they will crystallize and reveal themselves as low molecular weight compounds. They believed polymers were colloids, that they were smaller molecules that strongly associated to act like a bigger molecule. Not that they actually were a bigger molecule. Oh, okay. So, what was I going to say? So this sort of snotty attitude of clean it up and it'll crystallize was just really prevalent in chemistry. And that's one of the reasons to this day that polymer science is often not in the chemistry department. Because there was a very big divide between academic pure chemistry and applied chemistry. They didn't like the academics didn't like the applied chemistry. And so that's one of the reasons you find polymer science in chemical engineering departments, in material science and engineering. It makes sense in material science and engineering. But sometimes it ended up in mechanical engineering, which is odd, but because they were using the applied for something that, it's weird. Textile engineering makes sense, right? Go ahead.
What was Wyland?
Wyland? Thank you. We'll get through this DuPont stuff and then we'll call it a day. So, oh man, I haven't been this bad since Monday night. Which is why I got up and went to the doctor Tuesday morning. Okay. So Staudinger, we talked about him. Charles Stein. DuPont is still making money to this day off of the work and the vision of Charles Stein. Charles Stein initiated a program of fundamental research at DuPont. Back then, the 20s, the 30s, even into the 80s, that's really when I think it stopped. Major corporations did a lot of fundamental research, and that's just not true anymore. But if you look at what DuPont has done with this fundamental research, maybe they should be revisiting this. So he was the vice president for research, I believe. I think I have it on one of the later slides. And Wallace Carruthers was this young hotshot scientist. I can't remember. He was at Harvard. He was at Harvard at one point, but I don't remember if they hired him from Harvard or Yale but he was in the Ivies. And Stein hired him away from academia and was like, look, I've got money. You can do what you want. Go ahead. So he had pretty much carte blanche. That's how Stein hired him away. That is never going to happen anymore. Nobody gets that kind of carte blanche. Oh, yeah, we got money. You do what you want. That doesn't happen anymore. So Carruthers wanted to prove the macromolecular hypothesis using well-known chemistry and build polymers up step by step. So he started with condensation reactions, reacting an acid with an alcohol to make an ester. And he did it over and over and over to make a polyester. So obviously, this is just going to make a small molecule because what's the functionality? One acid, one alcohol, monofunctional. You get a small molecule. We need bifunctional. We need an AABB to make a polymer, right? And that's what he did. He used diacids and diols, and he made polyesters. That structure looks more like a nylon than a polyester. You want to know why? The ester linkage can hydrolyze pretty easily. So even though he was making these polymers and proving the macromolecular hypothesis, he could even spin them into really nice fibers. They spun great. Carruthers was distraught that this was unsuccessful because he'd spin them into fibers, polyester, right? But there's no ring. See, it's just an aliphatic polyester, just carbon and hydrogen. No double bonds, no ring. So back then, 20s and 30s, you certainly did not go out without pressing your clothes. You certainly needed to clean your clothes in some way. And so they could dry clean these. These fibers, if you dry clean them, they dissolved in the dry cleaning solvents. If you steam pressed them after washing them, the steam would make them decompose. And so Carruthers thought this was a colossal failure. No matter that he was, proving the macromolecular hypothesis, and he invented aliphatic polyesters, which we now use as resorbable sutures and use in other things. He saw it as a major failure. But he learned a lot about polymerizations. And so he's making these relatively low molecular weight, but polymers, aliphatic polyesters. So then he goes on to amides. He moves on to amides, and he makes nylons. And DuPont neglected to trademark the name. Oopsie. So no matter who makes it, they can call it nylon, but DuPont should have trademarked the name and owned the term nylon, like they did with Kevlar. Okay. So, and Teflon, I think, are both theirs. So, now we've got an amide instead of an ester, and this is stable. This is really stable. That's why we use nylons to this very day. So what has Carruthers invented so far? Aliphatic polyesters, nylons. He goes on. We're just going to look at his step growth polymers because that's how he proved that polymers existed. But he goes on and he invented what I call the prenes. Neoprene, isoprene, chloroprene. He invented all of those. The man was a tremendous scientist, a tremendous inventor, just a really amazing chemist. Keep that in mind because the story goes dark. So, if you've ever wondered about the numbers for nylon, it's the number of carbons. So the first number, you count the carbons between the NH groups. And then you count the other carbons. And you count the carbonyl carbons. I had developed the system. I would only count the CH2s, but I was not consulted, right? So this is nylon 6,6. You can have the nylon 610s, another one that's commercialized. Julian Hill was Carruthers' assistant. You know, I think he probably did most of the actual hands-on lab work. So he was instrumental in all of this. And here he is reenacting the invention of nylon. Pretty cool. You can see the strings, you know, that the high viscosity went up and stuff. So this stuff is so cool. So DuPont, they were masters at tech support and marketing. They made, back then, they made the polymer and sold it. They didn't make products, right? They were commercial, business to business, right? So, times were different. This is 1938. I'm making an announcement of a brand new chemical textile fiber derivable from coal, air, and water, and characterized by extreme toughness and strength. This is Charles Stein, VP for Research. We would not market something like this way today, right? We're not interested in things that are made from coal, air, and water. We want something more renewable, sustainable, right? This is not the way we'd be marketing something today. Better things for better living through chemistry. DuPont used that tagline for decades. So, they made this new wonder material. They had to figure out, well, we got to find a market for this so that so we can sell it to people. And one of the first things was stockings, which we now call nylons. But they didn't call them that then. They were stockings. Stockings used to be made of what? We'll call those tights. Actual stockings. Silk. They were expensive. They ran if you looked at them wrong. And we were about to go to war with who? Mm-hmm. Where did silk come from? Yep. And the Far East. So, but before that happens, let's stockings. So they have at the World's Fair, they demonstrated the new knitting machines that made nylon stockings. This is Marie Wilson's leg. She was a celebrity back then. They made a cast and then exploded it up to be 2 tons and 30 feet, 5 feet long. And that's her sitting in the little chair hanging from the crane. So there's her leg, and the knitting machines are down below. This is, again, the World's Fair in New York, 1939. So, there's the 2 young ladies playing tug-of-war with a pair of nylon stockings. pretty exciting. So, Wilmington, Delaware, DuPont's home, gets the first nylon stockings. May 15th, 1940 was Nylon Day. 4 million pairs go on sale, and the supply was exhausted in 4 days. I would be perfectly happy if I never have to put on another pair in my life. But, you know, back then, what had happened started in the 20s. Skirts got shorter and shorter. But you couldn't have bare legs. Bare legs were not socially acceptable. So you had to have tights or stockings of some sort. So, very high demand. Then World War II happens. And even before we entered World War II, we started preparing and we started sending things to allies and that kind of thing. 100% of the nylon production, all that DuPont could produce, went to the war effort. What were parachutes made of before nylon? Silk. Who were we at war with? Japan. We needed nylon. We needed nylon to help replace what we could no longer get. Here's Betty Grable. She was like the it girl, incredibly famous actress. She's selling her stockings. She auctioned them off for the war effort. Here's the post-World War II stocking sale. She sat down right on the curb in New York City and tried them on. Okay. So even during the war, it was not really socially acceptable to have bare legs.
Liquid stockings.
What did people do?
Drew with the pencil on the back of their legs.
Mm-hmm. Stockings back then all had a seam up the back. So young ladies that still wanted to wear their short skirts but couldn't get stockings and didn't want to wear something else, they would take an eyebrow pencil and draw the seam up the back of their leg so it looked like they had stockings on. So you can sort of understand this. Can you see those lines? Can you imagine standing in line for nylons? Look at this. This is a post-World War II stocking sale in San Francisco. I wouldn't stand in a line like that for a concert I really wanted to see. Especially not nylons. Yesterday, Macy's sold 50,000 pairs of nylons. An apology to those who did not get theirs. Yesterday, for the 4th time since early November, Macy's put nylons on sale. We had 50,000 pairs. We started selling at 9:45 in the morning and stopped at 3:12 when the supply ran out. I love the specifics in the ad. As you might expect, there were customers still in line who were disappointed. To them, we want to say we're terribly sorry. As the world's largest store, we have proportionately large shipments of nylons, but we have, by far, so many more customers than any other store, it's impossible to supply more than the smallest fraction of them at any one time. We will be selling nylons again. We wish we could tell you when or how, but we don't know ourselves. Please continue to be patient with us. Sorry, for the present, we have no more nylons. So Carruthers invented aliphatic polyesters, invented nylons, proved the macromolecular hypothesis, invented neoprene, isoprene, chloroprene. The man believed he was a scientific failure. The man was clinically depressed. This is what mental illness can do. This is how much mental illness can distort your sense of reality, because none of us think this man was a scientific failure. No one around him believed he was a scientific failure. But his internal demons, he couldn't overcome them, and he eventually committed suicide. And a contributing factor based on his writings was his view of his failure as a scientist. So, very tragic end. I believe he most certainly would have been awarded a Nobel Prize, but the Nobel Prize is not given out posthumously. And so he never received one. What age do major mental illnesses onset often?
18.
Yes, your age. It is young adulthood. Clinical depression, schizophrenia, bipolar, they all start in the late teens and early 20s. That's typically where the onset starts. And this is why I always tell this story. And it's just something you need to be aware of for yourselves and for your friends. And if you see someone that suddenly becomes very introverted, or the opposite, becomes very extroverted, or starts self-medicating with alcohol or drugs or whatever, if you see a big change in someone, say something. Go to do a CARES report. I have double-checked. I have asked again if somebody submits a CARES report about someone doing, like drinking in a dorm room, right? That could get you in a lot of trouble. It will not get them in trouble. It will only get someone to do a welfare check on them and try and get them the help that they need. And that's one of the first signs often, is that somebody's behavior changes pretty dramatically, or somebody starts drinking a lot more when they, it's a big change. It's not just that somebody goes out and drinks every weekend, right? That's part of being young, but a lot of times. So the CARES reports are a really nice safety net, and you can use that system. And again, no one gets in trouble from them. Nobody gets in trouble. And I'll tell you one more story. I had an advisee that's family hid their family history of mental illness from her. And she spent a year thinking that she had mono-like illnesses, not realizing her chronic fatigue and stuff were from clinical depression, and how it manifested for her was that way. And because she didn't know her family history, they didn't know to look at it. And so just, it's an important topic. It's important to think about mental health and to reach out if you see somebody that needs something or you need help yourself. So I'll tell you one more thing. Lighten it up before we leave, okay? One more thing about Carruthers. He realized there's two different types of polymerization. He developed these categories, which he called condensation, which is when most of the condensation polymerization, all of the condensation polymerizations are step growth polymerizations, I believe. But it means you condense out a small molecule. You're splitting out a small molecule versus addition polymerization where you don't make a small molecule. Go ahead.
I thought that condensation, polymerization, was because you make water.
But it doesn't have to be water.
Well, it doesn't have to be water, but I think that was
right.
The
That's
the reason why.
Because condensation, like dew on the surface.
Okay.
That's where the word came from. But often the common ones are water, methanol, and hydrochloric acid are probably the most common small molecule byproducts. And addition is really when you have the double bonds, and they polymerize really fast. And so that was the original, and you'll still see that classification. But most people have moved to step growth and chain growth. It makes a little more sense because if we make a polyurethane, there's no small molecule that splits out, but its kinetics, its growth, the way it polymerizes is the same as polyester, which is a condensation. So we call all of those step growth. And that's why that language is a little bit more modern. So we've got condensation or step growth, addition or chain growth, and then there's ring opening. We're not going to cover ring opening in this class. Ring opening, you have to know more about the mechanism because it's going to fall into one of those two categories, but you can't just tell by looking at it which one it is. So if we had more time, we'd talk more about ring opening. All right. So remember that counting the carbons, which one is nylon 610? C. Yep, C. Because the first number is between the NH groups, is the number of carbons between the NH groups, and the second one is the other, that includes the carbonyls. So nylons. Where do we use nylons? Carpet fibers, clothes, gear wheels, hot air balloons, parachutes, rope. And this is showing you that we don't always split out water. The small molecule can be something else, and HCl is very common. Happen here. And the nylon rope trick. I'll show you a video of the nylon rope trick later. This is, I think this is Carruthers. Doesn't look like Hill showing the nylon rope trick. It's an interfacial polymerization. So you have one monomer in the aqueous phase and one monomer in the organic phase, and they polymerize when they come together at the interface. It's really pretty cool. I used to do it occasionally in the classroom, but it sort of stinks and it's really wasteful. So now I just show videos usually. So anyway, polyurethanes, this is that example. So this is step growth, but it's not condensation because there's no small molecule that splits out. And you've seen this, and you've seen this, and we've talked a lot about this already. So that is where we're going to end today. And thanks for putting up with my coughing. It's flashing up there. Okay, now it's, I don't know. All right, so I am going to show you all of the mechanisms. I am not going to test you on any mechanisms, okay? So you have to be able to complete the overall reactions, and you have to be able to to look at a polymer structure and be able to predict what monomer or monomers it could have been made from. Okay. We are going for step growth polymers. We are only going to cover polyamides and polyesters. Okay. I cover those two, well, because they're really important. But if you understand those two, and you have resources like a textbook or the internet or something like that, you can look up any other polymerization reaction. Okay? So, and you can figure out, get a good idea of what monomer or monomer something could be made from, even if it's not an amide or an ester or a chain growth polymer. Just from learning those basics. So, step growth, any A can react with any B. Any acid can react with any alcohol. Any acid could react with any amine. Chain growth, we have initiation, propagation, termination, and we're going to look at some side reactions. So the actual mechanisms in chain growth, there's more. But the overall reaction is trivial, okay? There is a lot of homework and quizzes and stuff like that. There's a lot of practice problems in Module 5 specifically. Module 6 is chain growth. So there's quizzes because the overall reactions are easy. For step growth, we're going to practice a lot, okay? That's where students historically have needed the most practice, and that's why we're going to have a lot more assignments and that kind of thing. None of them have been updated in Moodle yet, okay? So I am like way behind because sort of as soon as I got over the bronchitis, my mom's partner, my daughter's grandfather went into the hospital. It's been pretty stressful, but he got off the ventilator yesterday, so we're really excited, and he is on the mend. But you guys were talking about sleeping. Hard to sleep, hard to focus. Mom calls, drop everything, answer the phone. So I am like way behind, but more in my other class than this class. Okay, so in Moodle, all of the assignment dates and that kind of thing are from last spring. All right, and it's set up for the online section, not for the in-person section. So I'll get all that stuff updated, but you can see the homework assignments and stuff like that. The first homework assignment, you can start with, because it's a goofy thing that I worked with some learning technology specialists to try and write something that it targeted a skill that people were very specifically missing, and that was really understanding stoichiometric inequality and why stoichiometric equivalence is so important. So we start off with I'm telling you a story about kids and their teddy bears, okay? So it's a goofy little thing, and then it ends with chemical reactions. So you can start taking a look at that one. You're only going to turn in the last problem. We'll talk through the other ones in class, but having read it and thought about it beforehand is helpful.
When that's gonna be due, so like we can mark it down in our calendars if it's not due yet.
I'll send an email. If try and read it before Thursday, the first assignment. Okay, so step growth synthesis. Step growth synthesis, the big thing is it's hard. Remember, we have calculated how hard we have to push these reactions, right? We need an extensive reaction of like 99% and greater to get some decent molecular weights. Go ahead.
Is this slideshow posted on?
Yes, it's in Module 5. I just skipped the first few slides.
Okay.
Because we've covered it multiple times. So we have to get to high degrees of conversions. In order to get to high degrees of conversions, we can't have any side reactions. We have to have an exact stoichiometric equivalence. Because you remember my pot beads, what happened when I had an extra purple one? I think it was purple. Right? It could only get to half as long. So any stoichiometric imbalance really inhibits molecular weight. Okay? And monofunctional impurities do the same thing. You end up with an end group that can't keep polymerizing. This is crucial. Reactivity is independent of chain length. If reactivity slowed as the chain got longer, we'd never make high molecular weight polymer. Which is why back in the day, they didn't think that there were giant molecules. Right? But reactivity is independent of chain length. Here's a slide I need to redo. Okay, so I use the term linkage when you can, for a functional group that can link two things together. I don't know how standard that is. It's pretty common in polymers, but I don't know how standard in organic chemistry that is. But so a linkage means that it's got two blank spots, right? So if I write down an alcohol as a functional group, OH, and then it's attached to something, it's got one blank, right? Or sometimes you'll see it in chemistry class written as an R. R just means it's something, right? It's like a variable. So
It means it doesn't matter whatever it is.
oh, it can matter a lot. But
in the case of it, what's being shown.
yes, so I usually just leave it as a blank to show that, you know, this is attached to something. But yeah, you can do it either way. And we could do this with just like, right, if we have a methyl group hanging off, right? All of these have one empty spot. Linkages have two, so they can link two monomers together, or what's left of the two monomers can link it together. So that's maybe not so standard language, but you're going to see a lot of polymer scientists saying this, right? So ester, polyester. Amide, polyamide. You should recognize these names because when you put poly in front of them, right, we talk about these polymers. Polyurethane, polyurea. Probably haven't heard of that one. We talked about this early, at this, like the first week of classes, I think. Sounds yucky. So they're called polyurethanes commercially. Polyanhydride, those are not hydrolytically stable. That means water can make them degrade. So you might not have heard of those. They can be important for drug delivery. In fact, the very first controlled drug delivery system was developed by Professor Langer at MIT and some colleagues at one of the hospitals in Boston. And he made wafers, polyanhydride wafers that were covalently bound to a chemotherapeutic agent, and they put them on inoperable brain tumors so that the chemotherapy was like right there. That was the very first controlled drug release. So polyanhydride's very unstable. And you see that? It's carbonyl, oxygen, carbonyl. If you flip it, oxygen, carbonyl, oxygen, that's a carbonate, quite stable. Very stable. Okay. So the big thing is we've got two blanks. The two you need to be able to recognize are ester and amide. I won't ask you the names of any others. Okay? Ester, amide. You've got to be able to recognize an alcohol, an amine, and a carboxylic acid. So carboxylic acid, acid chloride, alcohol, amine. So those are the four things. I'm going to take this away. Those are going to be our building blocks to make the acids, the polyesters and the polyamides. Mm-hmm.
I have a question. So are you going to just leave them like on test and like homework? Is it going to be written like that, or are we going to have skeletal structures and stuff like that, where it just sticks?
You're going to mostly have sticks.
Okay, cool.
The skeletal structures. Go ahead.
Will you say the name of not the ester and the amide again? Not the other two.
This one?
No, the other two.
This is what, the alcohol?
Yeah. My brain is just not processing it.
Alcohol, amine, carboxylic acid, and acid and then ester, amide. Amide and amide. You can say it either way. Doesn't matter. Okay. So those are the 6 functional groups that I expect you to recognize. Okay. Macrogalleria. Have we looked at macrogalleria? How goofy it is. This has a nice. Okay, I think this web page was created about 20 years ago. Okay, its user interface is so retro, it's about to be back in style. Let's put it that way. Okay, but the information is still good. See, you're supposed to be at the mall, at the Galleria, right? The macro Galleria. Level 4 is how you make polymers. So there's great information on polymer synthesis here. So there's the basics. Okay. And how about making nylon 6,6? It's got the mechanism. Okay. So there's a lot of really great information in Macro Galleria. You just have to sort of overlook the user interface. Okay. It's dated. We just call it retro now. Okay. Vintage. Yeah. Yeah, it was back, in 2003, it was like, ooh, frames, that's cool. Not so much anymore. Okay, so polyesters. So let me also say, we are going to, this is all going to go fast today. And then the next lecture, I'm going to repeat a lot of this stuff on the document camera. We're going to look at the mechanisms. We're going to slow everything down, okay? So if this is too fast today, it'll be slower on Thursday, okay? So polyesters, we react diol with a diacid to make a polyester, okay? That's the most common. Diol, diacid to make a polyester, and water, the small molecule of water splits out. Polyamides, we've got a diamine reacting with the diacid to give us our polyamide. Nylon, they're natural amino acids, we can call it a polypeptide. And again, the small molecule of water splits out. And so in general, we have a AA reacting with a BB, and then there may or may not be a small molecule splitting out. Because if you make a polyurethane, there's no small molecule splits out. So we can also do this with an AB type. So we can have a polyamino acid. It doesn't have to be a natural amino acid. Could be. It also could be a hydroxy acid. Hydroxy acid, so an alcohol can be called a hydroxyl or a hydroxy. So for polyesters, we've got a hydroxy carboxylic acid, that's AB type. We can polymerize a diacid and a diol. That's what I'm going to, those first two are the ones I'm going to expect you guys to be able to do. You can do ester interchange with an ester. And ester interchange, so that is really commercially important. I'm not going to expect you to be able to do that, but it's commercially important, so I want to make sure we talk about it. And I think I'm going to show you PET. That slide's made the cut. And then we're going to esterify. You can esterify acid chlorides right here with alcohols. So a diacid chloride can react with a diol. Acid chlorides, they react essentially like carboxylic acids on steroids. Okay? This is, moderately reactive. This is really, really, really reactive. Okay? This is going to really react. Okay? And then you can do ring opening polymerizations. That's really common. The lactone polymerization is really common for polylactic acid, co-glycolic acid, or polyglycolic acid. These are really important for resorbable sutures, degradable things. But we are also seeing more polylactic acid disposable items because in an industrial compost, polylactic acid will degrade pretty rapidly. In a home compost, it's going to take, it's not going to, a home compost is operating at a much lower temperature and doesn't have, you're not monitoring the microorganisms. It's probably not going to degrade in an amount of time that you want to wait. I don't know why that happened. So we're just going to skip this. Okay. So PET, not always, but often PET commercially is a double application of ester interchange. Okay, so you take the methyl ester of terephthalic acid, methyl ester, and you react it with ethylene glycol to get to this molecule. Methanol is a lot easier to remove than water is, so that's one of the reasons why this is done. Then this is going to do ester interchange reactions, the alcohol and the ester, to polymerize. So this molecule will polymerize if you pull out ethylene glycol. So to push a reaction, there's a principle you learned in freshman chemistry. So if I am removing one of the products, the equilibrium shifts to products. Anybody remember the name of that principle? Yeah. Yeah, French guy, Le Chatelier. So by removing this ethylene glycol, you're going to have to use vacuum and a purge gas probably in high temperatures to get rid of this. You remove that, you're shifting this reaction to the right, and you can get high molecular weight PET. Do I know why this is done commercially instead of a straightforward diacid polymerization? I don't know why. I also know, so Eastman is a huge polyester producer, and they make it straight from terephthalic acid and ethylene glycol, but a lot of times it's not. So I don't know when. We can skip that. Skip that. So this is showing you the actual interchange reaction, and this is the only time we'll see it. But we have a lone pair of electrons on the oxygen that attacks the carbonyl. So this is an alcohol doing an interchange with the ester. And so then this is going to pop off and be your leaving group. Okay. And again, it's just important to know that commercially often PET is not made from a direct esterification. It's done through these ester interchanges. Nylons, if you look at this, it's very similar. Except for now, instead of a diol, we have a diamine. Because look at this. Carbonyl NH. Carbonyl oxygen. They're similar, right? We just start getting rid. Now we've got an NH instead of an oxygen. So we're using an amine instead of an alcohol. Right? We need a diamine instead of a diol. Okay? Start thinking ahead. What's the big difference with having an amide group in terms of intermolecular interactions? What can an amide group do that an ester group cannot do? Hydrogen bond. Exactly right. So, amides are much more chemically stable than esters. If we made the equivalent ester as nylon 6,6, if we exposed it to steam, it would start to degrade. Okay? Aliphatic polyesters don't do well with hot water. The ester bond is going to break. This bond is going to break. Okay? So that's why, like, PET has that ring in the backbone, because that's enough to make it stable to water, because water doesn't want to get anywhere near that ring. Okay? So if we have the same ester, if we have a polyester and a polyamide, they have the same structure, except for this has been replaced with that. Because of the hydrogen bonds, it's going to have a higher melting point, a higher glass transition temperature, all because of those hydrogen bonds. Okay? So here's Julian Hill reenacting the discovery of nylon. We saw him in the History of Polymer Science lecture. Okay? We talked a little bit about naming nylons. You name it based, the numbers are based on the carbons, and you include the carbonyl carbons. That is always the second number. So there's nylon 6,6. What's the top one? Nylon 6, 12. The next one is nylon 10,8. What's the third one? 610. Nylon 6,6, obviously, commercially, we hear that one the most. Nylon 610 is probably, I should look up the production, but I would guess that's the second most produced. So, nylons, well, and you can do this with esters as well, but here, we're not splitting out a molecule of water, even though this is a condensation polymerization. What's our small molecule byproduct? Yeah, HCl, hydrochloric acid. So it doesn't have to be water that splits out. Okay. The nylon rope trick. Hopefully my video will play. So the nylon rope trick, you take a diacid chloride, and you want an acid chloride so it reacts really fast, and then you have hexamethylene diamine in water, and at the interface you're making nylon 6,6, and you can grab it with a pair of tweezers and pull it out. It's pretty neat. I used to do it in the classroom, but it's stinky and it's not very environmentally friendly to waste all those chemicals. So for a single demonstration. So now I show you a video. Not exactly the same thing, but close. And we don't
Panera's
have
toasted baguettes for $8.99? That's a big deal.
You probably know Vistaprint for business cards. Yeah, we print that. But did you know we also print that?
I'm going to try and make a polyamide.
Okay, and these British guys don't talk very fast.
I'm going to make a polyamide, not with a diamine and diacid, because that requires high temperature. I'm going to try and make it with a diamine and diacid chloride. So instead of having COOH groups, this diacid-like species, it's going to have COCl. And COCl reacts much more rapidly with NH2 than does COOH.
So I'll talk
and,
over it a little bit. I saw a video. I was shown a video once, years and years ago, where the professor
diamine is dissolved in water, by the way.
Was doing the nylon rope in a huge lecture hall. There was a
and the diacid chloride, for two reasons, is dissolved not in water.
He reached in and he grabbed the fiber and then pulled it over like there was a bar and ran to the back of the room pulling the fiber up. And I cannot find that video. It makes me mad every time I show this one because he's not that exciting. But if you go back and watch this one, he does a really nice explanation, but it's too long. So let's get him. Let's get going, guy. So he's going to reach in with the tweezers. And this is sort of neat because he's got this spool that he winds on. Most of the time people just do it on a glass rod.
And it's formed an interface. You can only form an interface because that's the only place where the liquid is coming into contact. The two reagents come into contact. Most of the reagents,
Why does it not?
Either in the water, or the other part of it's in the hexane. Not
Sorry?
Why does
its
it?
counterpart, the only contact goes in the interface. As we pull this far out from the
Because
interface,
it's pulling
the
from the
interface
whole
is really also
interface
gets formed.
into a. So if you, it's actually like
On we go.
forming a tube. It's hollow.
This reaction's going on at room temperature. It's between acid chloride and amine rather than acid and diamine. So it takes place very readily for that reason. Also, we're getting some additional assistance from the diamine because some of the diamine is actually being wasted in a sense, and it's soaking up the hydrochloric acid which has been given off in this condensation process, but removing it from the scene of crime and enabling us better to form this polyamide.
And this is
Now, I don't want you to think
1.75 times. It's going slow.
But they're all sticking together to form this sort of coherent fibre from this nylon. Something nylon 610 actually. Looks very flexible, doesn't it? That's because it's swollen with hexane. Nylon 610 is not very flexible. And I'm going to tighten this thing up so I don't touch anything more. Anyway, we could go on further. We can go on doing that actually until one or other of the reagents is consumed.
I think it's so funny they're using a glass. I don't know. So there are lots and lots of nylon rope trick videos available on YouTube. And, you know, any.
What happens if you don't pull it up?
It's going to format the interface, and the monomer is not going to be able to reach one another.
The Uniform Code of Military Justice specifies court-martial for any officer
don't
who sends.
care about that today. Oh, come on. I'm going to go back to. So if you think about it, right? So this is called an interfacial polymerization. You've got one monomer in one phase, the other monomer in the other phase. If the polymer is blocking the two phases, the reaction's going to stop. So it'll get thick enough that the monomers aren't getting to one another.
Is this how it's commercially produced?
I don't know. I would think that's not the case. It's I would assume that to do this type of interfacial polymerization, commercially you would be doing it for a specific reason. So there's a type of polymerization technique called emulsion polymerization. So instead of having two layers, you've got an actual emulsion like salad dressing where you shake it. And so that can get you like sort of certain size little polymer particles and that kind of thing. And there's reasons why you would want to do that, like latex paint as an emulsion. But I would commercially, you don't want to polymerize from solvents unless you absolutely have to, because handling all that solvent is expensive and, you know, it generates a lot of waste and, you know, anyway, it's just, so if they can do this from the melt or do this a different way, they're gonna avoid the solvents. And then this technique has two types of solvents, so it's like twice as much. So I'd be really surprised if it was typically done commercially that way. Okay, so just like the polyesters, we can do an AB type polymerization, and that's a lot more common because amino acid, that's going to polymerize and be an AB type polymerization. And so we can make peptides from natural amino acids, and we can make peptides from non-natural, you know, we can just polymerize an AB type polymer. We can polymerize a diacid and a diamine. We can polymerize a diacid and a diacid chloride like we just saw in the rope trick. Interchange reactions are not common, they're just not done. And ring opening polymerization is really common for nylon 6. So ring opening polymerization. One of the most common non-natural amino acids that has been studied a lot, initially anyway, I guess it was the Kevlar. I'm doing the no mix. If you polymerize this, you get something very much like Kevlar, but not Kevlar. And this is what people were initially focused on. And for whatever reason, doing the diamine plus the diacid is what was commercialized. Okay. So if I start drawing out those repeat units, the only difference is the amide is flipped over. Right? But that would be AB type, AABB. Right? In the textbook, in the electronic textbook, there's a really nice little thing about Kevlar, and Stephanie, I don't know how to say her last name, Kwolek maybe? She was the inventor of Kevlar at DuPont, and she is one of the first female polymer scientists that had, tremendous amount of success. And she's only recently passed, I think, the last few years. I'm like 90% sure that she's died. I seem to remember that came out. Anyway, I'll have to look her up again. But she was at DuPont her whole career, more or less. And she, the article, the little blurb in the ebook has some quotes from her talking about what it was like to work as a woman in science at DuPont in the 70s, 60s, 70s, I think it was the 70s. And she said that she got really fortunate because nobody wanted to work on this and they just left her alone. So she wasn't bothered. She wasn't, so she had a good experience. But it was definitely rough for women and probably underrepresented minorities back then.
Why did people not want to work?
I'm not sure. Maybe they thought it wasn't going to be successful, or they were just more interested in what they wanted to do. It's hard to know. But obviously, Kevlar has been a huge success for DuPont. Huge. It's off patent, so they didn't make the same mistake. They trademarked the name Kevlar, where they didn't trademark nylon. So anybody can make nylon. But Kevlar is DuPont only. But now the polymer can be made because it's off patent. But it's going to have to go by a different name.
So it'll be like a Kleenex tissue.
Right. Right. Yep.
Can you normally patent polymers?
That's a complicated question. But yes, in general, you can patent polymers. If you make a novel material, you can get a patent on the material, and that is the most valuable type of patent to have. You can also patent a process, and I'm sure they did all of it. So they would have patented how they made the polymer and the polymer itself. And so let's say they come up with a new way to make Kevlar, and it's a lot cheaper. They could then patent that new way, and nobody else could make Kevlar that way. even though the material patent is off, it's expired. So when we're talking about chain growth, I'm going to talk to you about polypropylene and some patent feuding that is, I think, still going on like 50 some years later. I swear it could be a movie if it was done right. We need John Grisham to come write it, but it's pretty crazy. So we'll get into that in the next module. Yep. So we can go past these. Now, one of the nice things about polymerizing in a diamine with a diacid is a amine is a weak base. A carboxylic acid is a weak acid. So if we have a diamine and a diacid and we dissolve them in something that's polar but not water, when they form the salt's going to fall out of solution. So if we were to put these in ethanol solutions and then combine them, what precipitates out is going to be 1-to-1, right? We're going to form that salt. If we separate that salt, we know we have a 1-to-1 ratio of those monomers, of the amine to the acid. So it's a way of getting, having that exact stoichiometric equivalence. Okay. There's your nylon salt, nylon equilibrium. Kevlar. Kevlar does not melt. It's not a thermoset. It just decomposes before you can melt and reprocess it. So it's not a thermoset in that it cross-links, but it decomposes before it melts. So we have to be able to process it, right? Somehow. And what they do is they protonate it. So I was told that DuPont has I was gonna use the letters, but a size exclusion chromatograph, which is a way of measuring molecular weight and molecular weight distribution, that runs with sulfuric acid, this really acidified solution, so that they can study the Kevlar, which that's just incredible that you have something. I don't know how they could ever get the machine to run, but they have to, because this is so rigid and it can hydrogen bond so tightly and pack so tightly together, and you get ring pi stacking, and anyway, it likes itself. It doesn't want to melt. It's happy, and so somehow you've got to disrupt that to get it to be processable in any way. And I have always just been amazed that this would ever manage to get commercialized. And when it first came out, it was incredibly expensive, and it's gotten a lot cheaper over the years, but it was incredibly expensive. And when I was in high school and skiing, so I skied competitively through high school and college, and it was a big deal when we started getting Kevlar in our skis, because it made them lighter. Stronger, stiffer, and lighter. And ski technology has totally changed now, but yeah, it was a huge deal. It was really exciting. And a lot of racket sports, a lot of different sports were like, it became sort of the thing in the late 80s, early 90s for sporting goods to have Kevlar. You don't see it as much. It's not as trendy and exciting, and also I think there's probably a lot of other things.
I was going to ask, has it been replaced by carbon fiber?
Yeah, a lot of stuff has.
Plexiglass?
Yeah. Yeah. Has the strength of steel with 1/5 the weight. It's pretty exciting, right? When that first came out. And it's used in bullet-resistant vests. Still is used a lot, but Spectra is also used. Polyurethanes are a cool example. Jumping. Because they don't split out a small molecule. You just get a rearrangement. This isocyanate is always such a strange functional group. N double bonded to C, double bonded to O. Isocyanate. These are quite reactive. So there's the urethane linkage. If you replace this diol with a diamine, you're making a polyurea, and still no small molecule is splitting out. Okay. Network formation. You guys should all remember this from the squigs, right? We want to make a network. Are we using bifunctional monomers, a mixture of bifunctional and monofunctional, or multifunctional, where the functionality is greater than 2? Multifunctional, yep. You got to have 3 or greater, right? What's going to happen in B? Can you make a high molecular weight material? Yeah, we're going to make a lot of oligomers, right? And then A gives us polymer. And you guys have seen this? This is making bakelite, and I remember my great-grandmother's bakelite necklace wear. Okay. So here, this molecule is phenol. This alcohol activates, the carbons that are highlighted in red. I don't expect you to remember that. Okay, but that's trifunctional. And when it reacts with formaldehyde, it polymerizes, and it polymerizes more. And you can see here, right, you're going to split out a hydrogen from both rings and the oxygen from the formaldehyde to make this network. Okay? Ooh, we went fast. I thought we were going slow. Okay. We're going to do those review questions later. Okay. All right, so Module 5. So these are the, oh, that's the video. These are, the slides we just looked, and then these are the doc cam slides. These doc camera slides, you might want to print out the first half, because that's what we're going to do on the document camera. Okay. I'm not sure that's the current. Okay, anyway. But the filled in ones are in this as well. You can see my notes to myself that I haven't done. What I wanted to do was pull up this. Okay. So, our elementary school teacher, Mr. Brown, wants his students to practice following directions. Told you it was goofy. So he developed several activities for his students. He had all his students put one hand on their hip and the other was free. Then Mr. Brown told his students to form a chain by linking their free arm through the loop formed by the other person. Okay? Hand on hip, right? In scenario B, Mr. Brown had his students form a chain by holding hands. In this case, only boys could hold hands with girls and only girls could hold hands with boys. So to form a chain, they had to alternate boy, girl. In activity A, several students would not put down their teddy bears. So they had one free armed or one looped arm, but not both. What happens to the length of the chain as the number of students with teddy bears increases? Shortens, yeah. There are 40 students in the class. 3 students won't let go of their teddy bears. How many chains are formed if every student who can link with another does? There's 2 correct answers. Boys and girls don't matter in this one because they're doing this. Can they form one chain?
Yeah. They can form 2 chains. 2 chains at least.
Yes. Yeah.
Could be more.
And it matters if everybody with a teddy bear does this, right? Or if it's a mix, right? Some have this.
Assume they're all facing the same way, yeah.
Yeah. Right? So now, let's think of activity B. There are 40 students, 20 boys and 20 girls. Can they form a single chain? They can actually form a circle, right? And what would the extent of reaction be if they formed a circle? 100%. There are 40 students, 14 boys and 26 girls. Can they form a single chain?
Oh, not all of them.
Yeah, you gotta have everybody.
Yeah, you can't all do it.
Right.
14 or maybe 14, like 12 would be out.
Or would it be 10 would be out if you had like the end, at the end of each chain.
Well, remember that. So we're trying to mimic step growth, right? We got A, B, B. So you're gonna probably have some dimers, trimers, and that kind of thing. So you're gonna have multiple small chains.
Separate the girls with 13 of the boys and then just put 1 to 1 in. That would react fully, wouldn't it?
Right, but you'd still have leftover girls. No matter what you would do, you'd have leftover girls. The average length of your chain is going to be low because there's not stoichiometric equivalence. Make sense?
Because you'd end up with like wouldn't you end up with like a little like 10 or something ish groups of like girl boy or like 5.
If it was it doesn't it's a statistical thing, right?
Yeah.
So you're going to get it if you did this over and over, you'd get a distribution of chain lengths and you get a distribution of like what's your longest chain and that type of thing. Yeah. All right. As the ratio of boys to girls changes from 1 to 1, what happens to the length of the chains?
The potential length, assuming it reacts fully, would increase.
Would
increase.
As we deviate from 1 to 1.
It would get shorter.
You're going to get shorter. Not the number of students. Right, the ratio of boys to girls.
Okay, well, how I was reading is as the U ratio gets closer to 1 to 1.
Oh, yeah. If it's getting closer to 1 to 1, then you're getting longer. But as it changes from 1 to 1, how I meant it, but what happens? So as we deviate away from 1 to 1, the length of the chain is going to go down. Everybody good with that? Yep. To form the longest chain possible, what should the ratio of boys to girls be?
1 to 1.
1 to 1. Right? And what happens if it's not 1 to 1? What happens on the end? The chain.
You're going to have like, the chains are going to be, each side of the end of the chain is going to have like.
Yes. So if we're in scenario B, every chain is going to end with a girl, right? And then and then we can't react. Okay. Oh. There are 40 students in the class, 20 boys and 20 girls. None of them will put down their teddy bear, so they only have one free hand. What is the longest chain that can be formed? 2, right. We're making a small molecule. We have monofunctional monomers. So the longest is 2. Okay. Here's our next scenario. The black circles can react with the blue circles to link together. No loops are formed. Consider the following. I have a black-blue dumbbell. I have a double black, double blue dumbbell. And I have monofunctional black and blue. So consider C. This is the blue-black dumbbells. We're contaminated with double black dumbbells. What happens to the length of the chain as the number of double black dumbbells increases? Decreases. And what's on the end of every chain? Mm-hmm. Consider D. There's 2,000 dumbbells. 1,000 black, 1,000 blue. Can they form a single chain? Mm-hmm. Now we've got 980 black and 1020 blue. Can they form a single chain? No. Why? Yeah. Yeah. We're going to end up with blue on the end of every chain, right? And then this is sort of a repeat. To form the longest chain possible, what should the ratio of black dumbbells to blue dumbbells be? 1 to 1. Consider E. Can we make a chain? No, right. We can make a dimer. Can't make a chain. Okay? So I created this in response to a couple classes not missing this on the exam. So and this has helped. It might be goofy, but it has helped. Okay. Now we're going to look at actual chemical structures. So, question 6. Consider F. This is a hydroxy. See the OH, the alcohol, acid. There's our carboxylic acid. The hydroxy acid was contaminated with some diol. What happens to the length of the chains as the amount of diol increases? Sorry? It shortens, decreases. Yeah. Okay. Because eventually we're going to have an alcohol on every end, right? Consider G. This is a diacid reacting with a diol. There are 4 moles of monomers, 2 of the acid, 2 moles of the diol. Exactly. Theoretically, not in real life, but theoretically, could they form a single chain?
Yes.
Mm-hmm. Even if we're just a little off, we've got 2.05 moles of diacid and 2 moles of diol. Could we make a single chain? No way, right? As the ratio of diol to diacid changes from 1 to 1, what happens to the length of the chain? Yeah. To form the longest chain possible, what should the ratio of diacid to diol be? 1 to 1. Okay. Consider this one. Can we make a chain? No. Right? We're just going to make a small molecule. If the R's are methyl groups, we're making acetone. No. We're not. Sorry. It's an ester. Right. Yeah. Not making it. So I put something very similar to this on an exam, and people made it into a polymer. I'm like, no, I need to address this. So if I put that or something similar on an exam, you guys are going to realize it's a small molecule, right? Okay, so 9 is complete the reactions above. So you will do only question 9 as homework, okay? And I'll get that into Moodle eventually. So, and we are going to end right here today. Thursday will be on the document.
For one position, you do the same for
Recording has begun.
Oh, there we go.
Makes sense.
Okay. There seem to be markers that write. It's a good day. Okay, so before we talk about synthesis, I want to talk about leaving groups. We're gonna make esters and amides, and we're gonna make them from alcohols and amines and carboxylic acids and acid chlorides. In these reactions, we'll actually have 4 reactions. In those reactions, you have a leaving group that becomes part of this small molecule byproduct. Okay? And what the leaving group is for the acid chloride, it's CO minus. And for the carboxylic acid, it's OH minus. CO minus is a better leaving group, so this reacts faster. Okay? I'm not going to ask you that, but it's like that's why these are so reactive, because the CO minus is an even better leaving group, because it'll pop off. Okay? Does that make sense? And then once you realize what the leaving group is, it's easy to start to see what the small molecule byproduct is going to be, because it's going to grab a proton, not a hydrogen atom, but just a proton from the alcohol or the amine. So it's going to grab a proton and make HCl. It's going to grab a proton and make water. Okay? So the leaving groups for the carboxylic acid and the acid chloride, if you can remember those, that's what leaves, it will make these reactions simpler. And if you don't learn the mechanisms at all, you can solve all these problems sort of by thinking of them like logic puzzles, and it's easier if you remember that's where this splits.
It's been like a year since I've had chemistry. Will you remind me why the OH has the negative on the front and Cl has the negative on the back?
Because it's on the oxygen. Because you always write the negative or the positive on the actual letter that represents the element that it's on. So if I had written it HO, I would put they're the same thing. But you're used to looking at alcohol as OH. So I wrote it that way and put but these two are exactly equivalent. If I had the chlorine and I drew the bond and wrote the hydrogen, I'd put it, or if there was some reason why I didn't have it here, I'd put the minus on the other side. So. Okay. So we're going to start off with some slides and then go to the document camera. Okay. Does this sort of look like the squigs? Okay. So the blue crescent reacts with the red circles to form a linkage. We're easing into this chemistry. Okay. Complete the following reaction. I've got a cartoon on the next slide. So is this going to be an AABB type reaction or an AB? Yes. AA. You got 2 monomers. There's 2 crescents. We'll call those A's. There's 2 balls. We'll call those B's. So this is AABB. Okay? The linkage is the crescent ball fusion. How many linkages are in that polymer per repeat unit? There's one in the middle. There's another one that's harder to see. You see the second one? Who sees the second one? Look at the wraparound. Right? So you've got We've got one that's written right here together. We got one right, there's half the linkage and there's the other half of the linkage. So there's 2 linkages per repeat unit when you have an AABB type polymerization. So that means there's going to be 2 esters or 2 amides per repeat unit if it's an AABB type polymerization. Every time you form a linkage, you split out a small molecule. If it's that type of reaction. If it's a urethane or a urea, you don't. But otherwise, for amides and esters, every time you form, I'm going to say it again, every time you form a linkage, you split out a small molecule. So when we have an AABB reaction, we react N times. Means we're going to have, we have N monomers. There's 2 A's per monomer, 2 B's per monomer. So we're going to, every time we make a linkage, 2 linkages per repeat unit, N number of repeat units, we're going to have 2 N small molecules. It'll get easier. Okay? So we did this one already. What if I change the stuff in the middle? It does not matter in this class. It might matter in an upper level organic class because you could have something in the middle that activates or deactivates a functional group. That's way beyond the scope of this class, okay? Doesn't have to be stereochemistry. It can be other things as well. But if it is a monomer and it polymerizes, you don't have to worry about what's in the middle. Because if it inhibits the reaction, you're never going to make a polymer, right? Because we got to get up over 99% completion. That makes sense to everybody? So if it is a monomer that polymerizes, you don't have to worry about the stuff in the middle at all. Okay? Always write down the stuff in the middle exactly as you see it. Because, you change it. You leave out the double bonds. It's not right. It's a different chemical structure. You make the ring bent instead of straight. It's a different polymer. Okay? The classic example is, I'll give you the reaction for Kevlar, and somebody writes the answer as Nomex, or vice versa, because they're not paying attention to the ring, what's in the middle. And the only difference is one is bent and one is not. Okay. All right. AABB or AB type polymerization? AB. So how many linkages per repeat unit are going to form? Just 1. Exactly right. If a small molecule is split out, how many are split out per repeat unit? 1. Exactly right. Okay. All right. Here's my first question for you guys. First formal question for you guys. We're polymerizing this hydroxy acid, AABB or AB? AB, there's only one monomer. It's that easy, right? Hydroxy acid, so there's an A and a B. Okay, we have the right conditions. We have N of them. It polymerizes. What's correct? You guys can keep thinking about it while I write this, and I start writing something down. Have you got anybody figured out that it's a trick question? There's your hint. It's a trick question. You guys say A and B are right? What? C?
Definitely C and D.
C and D? Anybody like A and B?
No, wait. Yeah.
They're all right.
Yeah.
They are all correct. A and B show you the end groups. We rarely in polymer science and engineering show you the end groups because they don't matter for the most part. It's not always true. But for the most part, they don't matter. They're such a small part of the polymer. If this thing weighs, 10,000 grams per mole, the little OH on the end, right, 16, 17, and the little hydrogen on the end, 1 gram per mole, it's not contributing a whole lot, right? It's not that important. So usually you don't write the end groups, but this is really very more correct than these. But it's not needed. We don't need that level of detail. If N is large, it doesn't matter if it's 499 or 500, because there's a distribution of molecular weights anyway, right? Doesn't matter. So these are all correct.
Why doesn't it matter the order of the R?
So glad you asked. Okay. So for the first one, okay, I have written out many repeat units on the board, right? So the first, for A, we've got oxygen R carbonyl, right? I can write down oxygen R carbonyl, oxygen R carbonyl, oxygen R carbonyl, all the way across the board, right? That is a repeat unit. It's complete. That is normally how I write it because it shows you, I can see the monomer easily the way that's written there. The disadvantage is that it's harder to see the ester, right? Because the functional group, the linkage is on the wraparound. So you have to think about, the oxygen's attached to the carbonyl, that's an ester. So that's a downside of writing it out like in A. If we do B, R carbonyl oxygen, R carbonyl oxygen, R carbonyl oxygen, right? It's the same repeat unit. But now we can see that ester really easily. So what did I leave out? I left out, I could start carbonyl oxygen R, right? That's also fine. So there's 3 ways we could write this repeat unit. We could put the brackets in, and they're equally valid. Equally valid. If I slice through the linkage, I can get what the monomer was. And we'll talk about that more. So like having it this way, you can quickly see, oh, this must have been a OH group and this must have been an acid. If that makes sense. But the advantage here is, right, we've got that carboxylic acid together. It's easier to see that. So you can be like, oh, it's polyester. Okay. Trick question. They're all right. This is an example of AB, right? Okay. So we're going to slow down. Chair is awkward. Oh, look at that. Some of these document cameras have a little preview window right there, and that's easier, but I need to get in the habit of looking up. Okay. So, here, maybe I'll see if the colors show up or not. Okay, so if I'm just doing the overall reaction, I don't have to really think about the mechanism or anything like that. So what I do, remember I had those leaving groups written right there? So the first thing I'm going to do is I'm going to find the acid or the acid chloride. I'm going to figure out what the leaving group is and cut it off. OH minus is going to grab the proton from the alcohol, so I'm going to cut that off too. So right now I can see HOH. So right away, and there's N. So right away I can write down that I have N water molecules, okay? Now I'm going to write down what I have left. I've got oxygen, whatever's in the middle, and the carbonyl group. Okay? That's what's left. When you do a chemical reaction, you can't create or lose anything, right? So I have accounted for that hydrogen, that OH in the water molecule. There's N of them. Now I've got OR carbonyl, N times. So I have N of these, but they're not individual. Now they're linked together in a chain. The carbonyl and the oxygen are going to form the ester. The other way to think about that is carbon needs how many bonds? 4, always 4. 1, 2, 3. I need to add 1. That's the wraparound bond. How many bonds does oxygen need? 2. Okay. So you want to know carbon, oxygen, hydrogen, chlorine. Carbon, hydrogen, oxygen, chlorine. Did I say nitrogen? We can make a table. Number of bonds. Carbon, 4. Oxygen, 2. Nitrogen, 3. Then the easy ones. Hydrogen, chlorine. Those are what is going to be important for this class. Okay. Others are also important, but for here, these are the ones we need to know the most. Okay. So let's look at the actual mechanism. So alcohol has 2 lone pairs. Right, on the oxygen. There's 2 lone pairs on the oxygen. Carbonyl carbon, especially in an acid, is going to be it's going to be low on electron density, right? Because the oxygen of the carbonyl and the OH group of the acid, they're both going to pull electron density away from that carbon. So the lone pair electrons can come in and be like, here, have some of my electron density. And when that happens, we end up with a transition state where this the electron density from the double bond flips up. So we have a transition state where we have the OH attached to this R group, attached to the carbonyl, right? I've got that carboxylic acid in red. colors are sort of showing up. Okay, so the new bond that formed is right here, right? And this carbon is fine. This oxygen has 3 bonds, so it has a plus charge. This oxygen only has 1 bond, but it has 3 lone pairs, so it has a negative charge. So it's a Zwitter ion, right? Because if we start with neutral things, this has to sum up to be neutral, right? Can't create charge, or it can't magically disappear or be created. So if we start with something neutral, and we can't add or take away elements. So this, not very stable, but it's an equilibrium reaction, whether it goes back this way or goes this way. So then one of the electron density from one of those lone pairs comes down. It kicks off the OH minus, which is going to grab the proton, which gives the oxygen both electrons. So now this oxygen has 2 lone pairs. This one has 2 lone pairs. There's a double bond. And this right here is making the water right there. So then we end up with OH.
Which ones break off again?
This is your leaving group. Which is right here. Okay, so this oxygen came from an alcohol. And then we have okay. So again, I won't test you on the mechanisms. I'm going to test you on the overall reactions. I think it's really good to see the mechanisms. I think it helps make the overall reactions make more sense and require a little less memorization. And it makes sort of working on these like a logic puzzle easier too. Okay. And those of you who are in or took or will take organic, it's a good refresher or review. Yes. It's right here. It's the same as this one. Those two are the same. These two are the same. So where's our ester group? Where's our new ester? There's our ester. So these slides are in Moodle. I updated them this morning, so they're what I have printed. And they also have all of it filled out at the end. Okay. Okay, so here we go. Here's AABB polymerization for a polyester. If R is CH2CH2 and R prime is a ring, we're making PET, but we don't care what's in the middle. It could be a triangle. It could be a rectangle. Sometimes I write rectangles instead of putting in some chemistry. It doesn't matter. We don't care what's in the middle. We care about the functional groups, okay? So, let's approach this sort of like it's a logic puzzle. We're going to rearrange the pieces and get our polymer and our small molecule byproduct. So the first thing to do is cut off the leaving groups. So those leaving groups are OH minuses and they're going to want a proton. They're going to get the proton from the alcohol. So by drawing those lines, I can readily see I'm making 2 water molecules, right? N times. 2 water molecules N times. Does that make sense to everybody? I got 1 here and 1 here, 1 in the middle, 1 in the wraparound. So first thing I can do is I can write down 2NH2O. Okay. Now I'm just going to write the whole alcohol in blue and the whole, what's left of the alcohol in blue and what's left of the acid in red, okay? So I've got oxygen, R, oxygen. And then I have carbonyl, R prime, carbonyl. How many bonds does carbon want? 4. How many bonds does oxygen want? 2. So if I put a bond here, now carbon has 4 bonds, oxygen has 2 bonds. If I put a bond, wrap it around, carbon has 4 bonds, oxygen has 2 bonds. This is not right without the bracket. I have made a mistake. Where is my mistake?
It can't be R surrounded by 2 O's and then R surrounded by 2 C. Like does it need to be?
Nope.
Like,
no, it's got to be. It has to be that way because it's that way in the monomer. Go ahead.
We don't just have that; we have N of that.
That's right.
It was like, is it that simple, or is it?
Yep. That's all I was going for.
We didn't give our units.
Well, yeah, we got to say how many times it repeats. Go ahead.
So how did we know that we're only taking the hydrogens from the first molecule, and then but we're taking the whole OH from the second one?
From chemistry. Okay. So the nice thing is for esters, it's not going to matter which way you do it. You'll get the right answer. But this is the leaving group. OH minus from the acid is the leaving group. And then if I change this OH to a chlorine, you don't have to change anything else, right? So there's where you slice for the leaving group. The proton is what you're getting from the acid or the amine. So if you remember that you're slicing off the leaving group of the acid or the acid chloride, it makes all the reactions very similar. Okay. Mm-hmm.
Is there a reason we would do A, B polymerization or A, like why have 2 different ways to make the same? You know what I'm saying? Like if we're making polyester.
If we were making, there's a subtle difference. Why is that out of focus now? Come back. Why? There it goes. Okay. This is very subtle. So see how this ester, it's oxygen carbonyl. If I wrote it down again, I have carbonyl oxygen. Here, it's always going to be carbonyl oxygen, carbonyl oxygen, carbonyl oxygen. Okay. So if the 2 R's are the same, all you're doing is you're taking the handedness away and they're all like this. Okay. So the difference between nylon 6 and nylon 6,6, that's it. You have the linkages like this, or you have the linkages like that. Okay. So it can change the way they crystallize. So nylon 6,6 and nylon 6 have different crystal structures and stuff like that. So it's stuff that you can't easily see just from the structure. A lot of times it's the way it polymerizes. A lot of things that look like AB polymerizations are going to be made from ring opening. But that get your question? Okay. I think I have now gotten this. That's right. We'll look at this the transition state one more time. Okay? So I'm going to put the lone pairs on those oxygens. And again, this is a little bit electropositive carbon because the electron density is getting pulled away by the oxygen. So these can come in and attack that, which flips up 2 electrons onto that oxygen. So we get, I'm going to start right here. So here I've got OH. And this has a negative charge, right? Because it's only got one, it's got 3 lone pairs. I'm just going to write all of the diacid in red. Oops. Sorry, making it messy. And this has a plus charge. So that Zwitter ion is not going to be stable. And once it forms this transition state, it either goes backwards or comes down to the products. So the lone pair reforms the bond. That kicks off the leaving group, which grabs the proton, which gets rid of the positive charge on that oxygen. So then we have H, 1 water molecule, plus I'm going to start writing here. I've got O, the R group. Oh no. Oh, we're going to light blue. So right here, this is the new bond. This is the new bond. That's the ester. So we've been making esters from reacting a diol and a diacid. We can also do it with a diacid chloride. If we used a diacid chloride, what would the leaving group be? Hydrochloric acid, HCl. Because I could change this right now. All I have to do is all the red OHs, I write a Cl for chlorine. That's all I have to do. Everything else stays the same. Now we're going to look at nylon 6,6. We've got a diacid chloride and a diamine. We're going to do the overall reaction first. And then again at the end. Okay. Often you'll have an amine written as NH2. I encourage you to cross off that 2 and rewrite the second H. Okay? Just makes this process a little easier. It's written out here. Okay, so what's our leaving group? It always comes from the acid or the acid chloride. What's our leaving group? That's our small molecule byproduct. So take away the proton. We've got Cl minus as our leaving group. And it's going to grab a proton. So now I can easily see HCl, HCl, right? Everybody sees that? So how many do I have per repeat unit? 2. So overall I have 2 NHCl. The number in the front. When the number is in the front of the molecule, what does it mean? This is as easy as it seems. It's the number of the molecule. So that's how many HCl's I have. When I have the bracket and the number in the lower right-hand corner. Exactly, the number of the repeat units. If I write the number in front and I have my thing with the brackets, is it right? No. Okay. Common mistake. Okay. Trying to steer you away from some of the common mistakes. Okay. So I have carbonyl. 1, 2, 3, 4. CH2 4 times carbonyl. NH. 1, 2, 3, 4, 5, 6. NH. CH2 6 times NH. How many bonds does nitrogen want? 3. So I'm going to add the wraparound bond, which means it has to come over here. Now this carbon has 4, and I need the one in the middle, because that carbon now has 4 and that nitrogen now has 3. What am I missing? Brackets. And what else? Yeah, right? The number of repeat units. Okay. I'll give you the first amide bond right there in the middle. Where's the other one? On the ends, yeah. I call it the wraparound bond. Okay. So one is there, and one is there in the middle. If we had used a diacid instead of a diacid chloride, what would the leaving group be? That's the small molecule byproduct. So yes. What? OH minus. Yep. That's the leaving group. This is what you need to be able to do. It's not looking so bad anymore, is it? Okay. Okay. Now we're going to do it a few times just as one-offs. Okay. The lone pair of electrons from the nitrogen attack the carbonyl of the acid chloride just like before. But we're not going to go through all that detail, okay? So what's going to happen? The Cl minus is going to leave. The proton is going to grab the proton. So then I'm going to write down HCl, okay? Plus what? So I'm going from a monomer to a dimer. So I've got carbonyl, CH2, 4 times carbonyl, NH, CH2, 6 times NH2. And what did I forget? I forgot the chlorine on this side. But now what did I forget? The new bond. The new bond in the middle. So there's my new bond in the middle. What's N equal? There's the repeat unit. What's N equal?
1.
Just 1? Yep. Just 1. Okay, I've got this molecule on the top of the next page. Okay, right there.
Question?
Yes.
Oh, why did you not, on the last one, why did you not put the leaving group on the end as well? You just did the far left, like you did for the prior.
Because I only have 1 each of those, not N.
Okay.
So it'd have to form a circle. Doesn't happen much. Okay, now we're gonna go from a dimer to a trimer. We got Cl minus as our leaving group. We got a proton coming off. So I've got HCl. Ooh. And now I'm getting some long molecules, right? I've got the acid chloride, CH2 4 times. I've got the first amide we made on the last page, CH2 6 times. Here's what I'm connecting right now. Carbonyl, sorry. CH2 4 times. Acid chloride on the end. Here's that new amide bond. What's the repeat unit? Right. So there's a repeat unit, right? We could even do that. Or that. Go ahead. Right here? Usually when you're writing out an amide, you don't write it. I'm trying to show where the new ones are. But yeah, so either is okay when you're writing out the letters like this. If you are doing a skeletal structure, you have to have it. Because you don't have a C. Mm-hmm.
Where is the HCl coming from?
Right here. I love all these questions. One, I can tell you're paying attention. And I think that based on the questions you're asking, I think everybody's getting it pretty well. So, feeling better about it than you did at the start of class?
Yes. I still don't completely understand why we can't do both ends.
We can do both ends. I'm just trying to show you how slowly it builds up step by step. Okay? So we're adding monomer by monomer, and but if for the overall reaction, it's all reacting. Yeah. So, right. So and if you look at this sort of code, right, we've got BB, AA, BB. Now we're adding another AA. So just trying to show it all step by step.
Where is the CH2 coming from?
Oh, right here.
Okay.
Remember the skeletal structures? Go ahead. because I counted. 1, 2, 3, 4. Yeah, so a lot of times I write it down because I miscount so often. It's the simple things that trip me up. Basic multiplication, yeah. So the next thing I'll tell you is if you don't like these skeletal structures, take the few seconds to rewrite it. Right? You know, this long one isn't the best example, but let's just look at this molecule. It's like, okay, I hate these, so I'm going to rewrite it. I'm going to do NH. I see 1 CH2, 2 CH2, 3 CH2, right? And I can keep going, or I could have counted and written it as brackets. But if you struggle with the skeletal structures, just rewrite them. Okay? The other thing you can always do is you can circle and say equals R. Chemists do that all the time, right? So that equals R equals R prime. So now I could write this is the same thing, equals R prime. So now I can just write down NH2 R prime NH2. Okay. If you are doing that on something we are grading closely, like an exam, make sure you define R prime and R or whatever it is, because you won't get full credit otherwise. And I'm sorry, speaking of the exam, we released parts A and B, so you should be able to review it, parts A and B, but C did not get released because some people didn't get things turned in, and we're working on how we're going to handle that. So, didn't get turned in and didn't get emailed to us at the time of the exam. So, that's why I didn't talk about the exam first thing today. Stalling a little bit, but you can review parts A and B of the exam already. Okay, so this one, once this adds on the end, since I've scribbled all over this one, let's just look at this. Okay, so we've got a trimer. There's monomer 1, 2, 3. We add 4. And here it's written out not in skeletal form, right? So we've got BB, AA, BB, AA. So we can rewrite it with a bracket and a 2. Sometimes N is small. If N is small, you need to have the things on the ends. Okay? So show the tetramer in the form of R sub N. We have 2 repeat units. And so the way we can write it is right here. See that? There's the red, the BB, there's the A, and we have 2, and then you can see the H and the Cl sticking out. If N was 500, I wouldn't need the H and the Cl. But since it's 2, I need those. Well, here. Make sense? Somehow it looks like I've lost people.
Can you show the last one, previous one? where the repeat unit is?
So there is there, there is there, there is there, and this just got added on at the end.
So what is the repeat unit? Is the
So the repeat unit, like I had up here, right? We can do it in different ways, but let's start with the carbonyl. We have that whole monomer and then this whole monomer. Since it's a nylon, we really should do it this way. Because nylon 6,6, the first number is the number between the NH. So we like to go from left to right. So that's probably a better way to do it. But it's all correct. So what I was just saying is you just literally flipping this over. It's the same.
So the NH2 came from the addition on the right hand side of the top. But the reason it comes, but you take the H from HCl. Why do you need the M group for that one, but not necessarily the top? Or like the other side? Like why do you need that one?
So if you just have one of these molecules and one of these, it can only react once, not twice. So we only make one HCl. So one of these still has NH2 on the end. Okay. So what we've looked at so far, we've added either an AA or a BB, and we would go up by only half. We'd go from a dimer to a trimer, but that would only be 1.5 repeat units. You have to add both, one on each side, to go up to 3 repeat units. Does that make sense? So if we want to do that here, we're going to lose the acid chloride on this end, and we're going to lose the acid chloride on that end. It's going to grab a proton, and it's going to grab a proton, and then we can write down. So this end was just not involved in any reaction, right? And then we have CH2 6 times NH. I'm going to write all this part in black. Okay, that came from right there. 2 repeat units. And then this got added on. Okay, I'm missing my small molecule. HCl, but I've made a mistake. How many HCl's? 2. So for every repeat unit, to get a full repeat unit, I need to do both of those, right? I need to put one on each end to go to 3 repeat units. So every time I make 1 repeat unit, I make 2 HCl's. I make 2 small molecules. Mm-hmm. Yep. So I could cross off all of that, just put the H and the Cl on the end and write 3. And then we should do the overall again, but I have some practice questions. Yeah.
So is it 3 repeat units because one of those is A and the other is B, and then we already have 2?
Yeah, so essentially you've got 1 there, we've got 1 here, and then we've got the okay. Now I'm going to ask you to go backwards. Okay. One of these polymers was made with AABB and one was in AB. Which is which? AABB. That's right. AB. So how many linkages in the top one per repeat unit? 2. And only 1 in the bottom. Okay. So going backwards, what monomer or monomers could these have been made from? I sliced through the linkages. One linkage is the wraparound, one's in the middle. Do I have 1 piece or 2 pieces? 2 pieces. So that tells me that it's AABB. It was made from 2 monomers. Make sense? The bottom one, if I slice through the linkage, I'm slicing the wraparound bond. I only have 1 piece. AB. Okay. So if I write what I have, I've got carbonyl, ring, carbonyl. That's the first piece. And then I have oxygen, CH2, CH2, oxygen. That's not the answer. We're halfway there. We're more than halfway there, but it's not the answer. How? Yeah. Exactly. Right? Because oxygen needs how many bonds? Oxygen. 2. Right? And so the oxygen and the amine, we always add back a proton. Here, we've got a choice, and we don't know. It could have been made from. So what can we add? An OH, and we can make a dicarboxylic acid. What answer would be equally as valid? A Cl. We could have had that be an acid chloride, and those could have been Cls. Equally valid. No way to know. When it's an AB type, it's probably not an acid chloride because it probably would not be stable enough to make it. It would react with itself. That makes sense. If you put an acid chloride on an AB type, I'm not going to mark it wrong, but it's usually not right. Okay. So this is one where it can be hard for people to look at. So if I write the carbon there, and I write a carbon here and a carbon here, then that one needs 2 hydrogens. This one needs a hydrogen. Sometimes that's a lot easier for people. It took me seconds. Just go ahead and do it. Okay. So I'm going to do the exact same thing I did. I'm going to rewrite this. I've got NH. I've got carbon with a hydrogen, carbonyl, and then I just write this. Okay, I guess I should have done CH2 and then the ring. Okay. Sorry, I made it messy. Nitrogen needs how many bonds? 3. I'm always going to add what back to a nitrogen or to the amine or the alcohol? I'm always going to add the proton, right? So it's just going to be NH2. What do I add here? I've got a carbonyl. The carbon only has 3 bonds. I know I need to add another bond. What am I going to put on? An OH. Any questions?
When would it be more likely that, like for the AABB one, you said that the thing attached to the carbon could be an OH or maybe it could be chlorine, but probably not. When would there be a time where you would know like this is
So on the AABB, it's equally valid. Here, the OH is a better answer. On an AB, the OH is a better answer. If you don't remember that, I'm not concerned. Okay. Let's make Kevlar. I'm going to fix this structure for you. I'm going to cross off the 2's, and I'm going to put an NH up above. Okay? I can even add the carbon, the letter C back, right? All right, take a few seconds and see if you can complete that. As you finish or you get stuck, look over at your neighbor, see if you got the same thing or not, or if they can help you. Go ahead.
I have a question. So for when you're adding like the 2N, do you put the 2 like in front of the N or like with the byproduct? 2, if it has it.
It's just sort of, it's like writing a variable. You always put the number before the variable, so 2N.
Okay, I just
Yeah.
want to know.
Just like, it's like algebra. It's, it's not wrong to write it the other way. N times 2. But we don't say it that way. Does that make sense? Okay. What's the small molecule? HCl. How many do we have? 2N HCl. Everybody got that far? Okay. Because we slice off the leaving group, and we slice off the proton at once. HCl, HCl. Okay. Then what? What?
The CO and your ring, and then the CO, and then just move on to the NH. And the ring.
Okay. Everybody get that far? And what's missing? Brackets. Also, don't forget the wraparound bonds. And then, and great. And you see how the ring is, we've got the attachment point 2 carbons attachment point, so it's straight across the ring. If you do it this way, that is not the same polymer. This is Kevlar. This would be Nomex. Okay? So that is not right. All right? That's another mistake students have made in the past. Okay? Not as common as some of the other ones. Do you have a question?
Yeah. So why is Kevlar's tensile strength so much higher than, or I guess it's not so much higher, but higher than Nomex?
It's straighter.
Okay, that makes a lot more sense.
So it packs together and crystallizes. That kink in Nomex makes it more comfortable to wear.
Okay.
And that's why it's used in like firefighter turnout suits.
Right.
And not instead of Kevlar. But Kevlar is going to have the better tensile strength.
Is Nomex more fire resistant than Kevlar, or is it just more comfortable?
I don't know 100%, but my understanding is that it's more comfortable and that they're similar.
Okay.
In other performance.
I guess it makes sense because you need like your whole body covered, so you would need it to be more flexible, so you can move your joints. Otherwise, you'd have firefighters just like.
Yeah.
It's more expensive too.
Nomex is?
Yeah.
Is it? It's newer. It's been around forever though, so it's got to be off patent. So it's not the patent. It might just be more expensive to produce. I don't know. One more. AABB? AB. Correct. Okay. We're running short on time, so you guys tell me what to do. Cut off the OH and the H. So I'm going to have how many small molecules?
H2O.
Okay, and then if I write down carbonyl, CH2, CH2, oxygen. Now what? I need the wraparound bond?
Yeah.
To make that linkage. Yeah, thank you. Okay.
So for that 2CH2, do you write that CH2 bracket parentheses and 2, or no? If you only have
You could. There's nothing wrong with that. So, did you hear did you get what she was asking? So, could I do same thing? Or doing it as the skeletal structure. Those are all the same. And let's say you are making a series of polymers and you're changing the number of CH2s, you would probably write it this way, right? So that you could very easily see that you're just adding them, right?
When we write a product, do we not write it staggered? Like in the up, down?
You can, the skeletal structure, you 100% can. Students usually don't. So no. I think people who write answers in skeletal structures have usually have or are taking organic, and so they're just more comfortable with it. So it's all acceptable. I've had TAs in the past who didn't understand skeletal structures, and I've had to go back and fix it. But yeah, no, it's all good. Okay. So there is, in this slide deck, there is this table. Okay, we're not going to go, and there are these review questions. Okay, so for polyesters, we have the AB type reaction, so there is no second monomer. We have AABB, where we have a diol reacting with a diacid or a diacid chloride. This has got your small molecule byproduct. It's got your polymer. If you can go to, I have N of these and it polymerizes, and then figure out what it polymerizes into. And for this table, if you can, if you just had this column and you could fill in these columns, you are good to go. Okay, does that make sense? There's a bunch of some review questions. And that is what we're covering for step growth. We are going to have a bunch of practice and a quiz and, that kind of stuff. So start looking, don't bother with the quizzes that are in Module 5, but start looking at the homework, okay? We will be moving forward, covering chain growth polymerizations and weaving in going over the homework and stuff. So your quiz, we're going to talk about problem 9 from your homework that you were supposed to have done for today. And your next homework, resume. The same alternate correct answer as a diacid chloride, right? But almost nobody does that on the first two. That's why I have this third and fourth one. A diamine and a diacid chloride react to form a polyamide with a D, or amide, or nylon. I even take peptide. Okay? So a diamine and a diacid chloride to form a polyamide. And what's the small molecule? HCl. A diol and a diacid chloride react to form a polyester and
Water.
Oh, it's an acid chloride. HCl. Because it's an acid chloride, the Cl minus is the leaving group, not the OH minus. Kevlar, a polyamide, is polymerized by a step growth or chain growth polymerization? Step growth. Lycra, a polyurethane, is polymerized by step growth or chain growth? Step growth. But not condensation. That's the tricky, because it doesn't split out a small molecule byproduct, but it's still step growth. Polyvinyl chloride. See the pattern? Poly linkage. Poly, monomer name. Polyvinyl chloride is polymerized by step growth or chain growth? Chain. So on an exam, I wouldn't ask that without giving you the structure of that one. This Kevlar one would be okay because it says polyamide. And then I won't be asking you questions about polyurethanes, so I wouldn't give you that one on an exam. A hydroxycarboxylic acid. So that means it has an acid on one end and a what on the other end? An alcohol. The hydroxy is the alcohol. Polymerizes to form a polyester. An amino acid polymerizes to form a polyamide. Polypeptide would be acceptable. Protein, not quite as correct, but acceptable, right? 200 level class. Okay, what monomer or monomers could the following be made from? Were they AB type or AABB? Okay, what about the top one? That's an amide. Oh. That's an amide.
So, AABB?
It is. This one is AABB. How can you tell that? Go ahead.
It has like I'm just gonna call them R. It has like the R section that's like the chain of like C's and H's, and it's surrounded by like two of the same thing on each R. So it's like ester, R, ester.
Yeah. So there's the amide, and it's carbonyl NH. But this one is NH carbonyl. Right? That's what you're getting. So it's flipping over. So if I slice through this linkage and I slice through that linkage, the one is on the wraparound. One, I can see it's in two pieces, and that this is going to be from a diacid and a diamine. Does that make sense to everybody? So before I draw that out, what about this one? This is going to be an AB. And it only has one linkage, and if I slice through that, I can see it's oxygen, R group, carbonyl, right? Because it's now the linkage is not splitting the wraparound. So let's start with this one. So I'm going to start with the oxygen. Then I wrap around, I get the R and the carbonyl. This is incomplete, right? Because carbon needs how many bonds? 4. So I am going to add an OH to make a carboxylic acid, right? Oxygen needs how many bonds? 2. And we need this to be an alcohol, so I'm going to add that hydrogen back, right? So here I've got carbonyl, 1, 2, 3, 4, CH2 4 times. I'm going to put R group there, carbonyl, so it's easier for me to fit. And then this is 1, 2, 3, 4, 5, 6. So this is nylon 6,6. So I have NH, R prime. And then, like, if this was an exam, you would want to do R prime, right? You need to label what the R and the R prime are if you're not writing out CH2 parentheses sub 6, right? Repeat 6 times.
Isn't it NH, R prime, NH?
Yes. It's amazing what your hand will write when you're not paying attention. Okay, so now carbon needs how many bonds? 4. So I can make this an acid or with an OH or a acid chloride. There's no way to know, right, from the polymer structure. There's no way to know. And this nitrogen needs how many bonds? 3. So I just need to put back a hydrogen on both of those. Any questions on those? Go ahead.
So like on those, we had to like kind of like infer that there was like a small like molecule that was like split off.
Mm-hmm.
If this were like a test, would you say like what monomer or monomers can be made from like the same phrasing, but you would give us a small molecule? So that, no? Okay.
No, but I would accept that the hydrogen's going to be the same, right? You're adding a proton in here for the alcohol or the amine, you're always adding a proton. And then if you make an acid or an acid chloride, they're both correct. They're equally correct. So, yep. All right, so complete the following reaction. The first thing I'm going to do is I'm going to cross off the 2 on the amines and write out the second hydrogen. Okay? I find it easier because I like to do my trick of slicing off the leaving group, which is OH minus. When it leaves, it is going to grab a proton. So now I can see H, OH, right? H and the OH. So what's the small molecule byproduct? H2O, water. How many do I have? 2N, because I have 2 per repeat unit plus. Now I can write this part and figure out how they go together. So I've got NH and the ring and NH. And I have a carbonyl and the ring and the carbonyl. So I've got my 2 leftover pieces. I need to join them to form the first amide. The second amide is going to be that wraparound bond. And I need my brackets. And what did I left off? The number of repeat units. It always goes in that lower right-hand corner because out front, it tells me I have 2 N water molecules. So if N is 1,000, I have 2,000 water molecules. Here, if N is 1,000, I have 1,000 repeat units and 1 polymer. Go ahead.
In number 10, do we need to put N in front of the reactants?
No. No, because it's not a complete reaction. Yeah. Yeah. And I won't ever mark you off if you do that, but you don't. It's not a complete reaction, so you don't have to do that. It's just asking you what monomers or monomers could it have been made from. It's not the whole backwards reaction. Any other questions? Now we got sort of toggle between screens because I didn't print this one out.
Should we turn this on?
Sometime, yeah. You can do it now or you can do it later. Right? And you can turn this one in too. This is the module 5, the first homework, and the only one you're going to turn in is problem 9. Right? We talked through the rest of it, remember in class? Was the goofy one with the kids and the teddy bears and the dumbbells. Okay. So, we've got a hydroxy acid that we just had on the quiz. We've got a diacid reacting with a diol. And we've got an alcohol reacting with an acid. So we've got 3 reactions, and problem 9 just says complete the reactions, right? Assume you have N of each molecule. Don't forget any small molecules that were produced. Okay. So the first one, F, I have N of the hydroxy acid. In this class, the reaction conditions are always perfect, okay? When you start taking upper level, beyond organic 1, you've got to really worry about what the reaction conditions are as to whether the reaction will go or not, but not here. It's always perfect. Okay, so our leaving group is the OH minus. It's going to grab the proton from the alcohol. So I know I'm going to have a small molecule water byproduct. I'm doing this N times. So how many waters do I have? N.
Does it matter if you put the N before or after the H2O?
It does. You got to have the N in front because that's telling you have N of those molecules.
Okay.
If you have it behind it, it's like really hard to know what it means.
Okay.
Yep. And if it's low, it's like you're saying you have N oxygens. So it's, yeah. Okay. Now I need to make that into the polymer. What do I need to do? Anybody want to shout it out? I need the wraparound bond. Cool. Parentheses. And it's got to go down here, right?
It really doesn't matter which order you put those 3 in, right? Because
which
you RC
right, correct. That's what I had written on. Remember, I had all those repeat units. So as long as it repeats correctly, you can have it any which way. Yeah. And a lot of people like to write it as R carbonyl oxygen because you see the ester as opposed to having it on the split. Which I totally agree with, which is like right here, this example. Same molecule. If R is the same, it's the same molecule, right? G we've got our rectangles. I could make that stripe so it's not the same. Could be the same. Okay. What should I do first?
Cut off your small molecule.
Okay. So I'm going to cut off the leaving groups. And the protons the leaving groups are going to grab. So how many leaving groups am I going to have? 2, how many? N times, right? And it's the small molecule is going to be H2O. And then I'm going to write down what I have left. There's the one ester group, which makes the carbon have 4 bonds. The second one is going to be on that wraparound. Parentheses, number of repeat units. You guys feeling pretty good when we do it like sort of like a logic puzzle instead of looking at the mechanisms?
So when you cut up your living group, for this one you cut up the OH first, but some, like the previous one, we cut up the edge only. So we still cut off the OH. But for the G, for the first monomer, you cut off OH and H. So
I cut off, here's OH, and this is another OH. It's a diacid, so I'm cutting off the OH minus on both sides.
So if you cut off OH that side, you cut off the OH.
Yes. Yeah, you're going to do the same thing for every acid and for every alcohol. You do the same thing over and over. Okay, now I've got ROH. It said everything has N of them. Oops. N, R, carboxylic acid. Okay, here. I put this on exam one year, not thinking it was a trick question. It ended up being a trick question. Everybody tried to make it into a polymer. I'm like, it's not a polymer. Can't make a polymer if it's monofunctional, right? Okay, so still, the OH minus is still the leaving group on the acid. It's still going to take a proton. I have N of these, so what am I going to end up with? Yeah, I'm still going to have NH2O, right? From there and there. And then I write down, I've got R. Oh, sorry. And then I'm going to flip this over, right? So I've got my carbonyl and my R. So that new bond is right here. No repeat units. So there's no parentheses, because 2 monofunctional things, 2 of the yellow squigs can only react once with one another, right? We got 2 yellow squigs. That's all they can do. What's missing? This isn't a balanced chemical reaction. What's missing? An N right here.
If you put parentheses but not like the line through them, just so that it kind of like is like, this is the thing. Is that fine?
Yeah. It's like extra information. You don't need it. But if the N is on down here, that's bad. If it's on the right-hand side, not good. Okay? How you guys feeling? I got one half-hearted thumbs up. What?
I like this stuff.
You like this stuff? Are you, what's your major?
TE.
TE? Cool. Yeah, I think there's lots of ways to think about it. Okay, so we did our quiz, we did our homework. You can turn both of those into Moodle today. I gave you till next Tuesday to do the next homework. We'll have another quiz on Thursday. And then I went and looked at the schedule. We're behind. So it says review for exam 2. That's today. So we're like a class and a half behind, maybe. Okay, but what's important is that we get the 2 exams in before Thanksgiving. Okay, now these next 2 exams, they used to be 1 exam, and when I moved to the online format, we didn't have to do 1 big really hard exam. We could break it into 2, and so they're not going to be they're worth less than the first exam. Because I used to have it structured that the first exam, then the second exam was worth a little more, and the third exam, during finals, was worth the most. And so that's still true if you add the second and third exams together. So definitely less to study, less content, and all of that. So, and we'll do the same format where we have the exam open for 3 to 5 days, okay? Yeah.
Do you know when you're planning on opening the second exam?
I'll know on Thursday. But so I'm thinking that we can be done with. We could probably be ready to review on Tuesday, and then open the exam, maybe Wednesday or Thursday, and have it open through the weekend. Not this weekend, the next weekend.
Will it be in parts again, or will it just be?
It'll be in 2 parts. 2 parts. And I can give you that exam template again. Did you guys like that?
Mm-hmm.
Last year, people were really excited about that. I try not to make the exams surprising. Go ahead.
Do you have an estimated date when we'll get the grades back for the last test?
It should have been today, but I didn't get it. So, after we get the 3rd part, I'll import them into Moodle. We'll see if it works correctly. Last fall, we had a freak out because the grades came into Moodle lower. I don't know how. Like the numbers were wrong from Gradescope going into Moodle. I don't know. I don't know. Never figured it out. But people were freaking out, and I'm like, "What do you mean?" And then I'm like, the numbers aren't right. This is anyway. So hopefully, it's in the spring. It went just fine. So we're going to assume it's going to go just fine. But you can see A and B right now in Gradescope, but nothing's been sent to Moodle yet. And in Moodle, it will add them together and give you and put it into the slot for exam 1.
Will that be like our final grade on the test, or will there still be like a curve after that?
What I do is I don't really curve anything. I just lower the grade cutoffs.
Oh, okay.
Yeah. So I sort of lower them on each exam. Not that it matters. It only matters on the final. But usually my grade cutoffs are, aside from the A+, I don't lower that one. But usually the A cutoff is 86 or something for an A minus. I'm usually 4 to 5 points lower at the end of the year. Yeah. So, and then if we have a really low class average, it'll shift lower, right? You know, it's sometimes I make things too easy or too hard, and that's why I do it this way. It's really hard until you get a lot of practice to gauge how long a test should be and how hard it is. The hardness seems to be a lot better, especially when I give you a lot more information before the exam. Get that sort of dialed in. But yeah, the time. And I'm a really slow test taker, so I'm very empathetic to those of you who are also slow test takers. And so I always try and make time not so important on the exam. But I also, since now you're doing it at home or in the library or wherever, I also don't want you to have enough time to like Google everything, even though you're not supposed to, you know, that, anyway, go ahead.
Just to clarify, are you saying that the exam grade itself isn't like lowered, but your like final class grade is?
Yeah, the cutoffs. Yeah. And you can put any grade cutoffs you want into Moodle. And so mine are usually 4 to 5 points a little down. And then I tend to have the letter grade be bigger and the plus and minus be smaller. Does that make sense? So like if the letter grade is 5 points and then so if the B range is 5 points and then the B plus range is like 2 points or 3 points and then the B minus is 2 points or 3 points or something like that. And then the B range tends to be the biggest as opposed to some of the other ones. Yeah. Anyway. Because I bring those cutoffs down. I rarely, if ever, get complaints anymore about, oh, I thought I was getting this, right? Doesn't usually happen. Okay. So, yeah, essentially, I think we'll be ready to review for exam 2 a week from today on Halloween. Okay. Am I going to see any costumes? Maybe? No? One year, the last time, it's been years since Halloween has been on one of my class days, but the last time 2 Chainz came and sat in the front row. It was exciting. I had to ask who it was, but made me feel old. Okay, so what are we doing? We are going to start chain growth. That's what we're going to do. Any other questions about step growth?
Is our next homework like pretty self-explanatory?
Yes. It's a list of polymers like polyester, and it gives you example. So the next homework is you've got to use the internet, because I'm showing you that just because we've studied polyester and polyamides doesn't mean you can't do other polymers with a little bit of help from the internet or a textbook or something like that. So it's going to ask you about polymers, other polymers. Okay, so polyurethane, polycarbonate, polyanhydride. And I put some more in Moodle. I put some additional So there's this, and this is that review section. It's right after the start here section in Moodle. So there's skeletal and line drawing information, molecular forces and bonds. And here is some additional, I just put this in, and I swear I put some extra stuff in there, another thing, but I did not, I guess. Oh, right here. This is the intermolecular forces. I have another chapter I can add in here, but I don't think you guys actually need it. But if you wanted some more information, so yeah. So there's some additional information in this section, in this review section, and then I just need to download our slides, which is 6. It annoys me that they moved it from down here to up here. Anyway, chain growth polymerizations. What are the 3 reactions? Initiation, propagation, termination. There's our friend Carruthers. So addition and chain growth are essentially synonyms. We've seen this before. Seen this one before, I think. Okay. So we've covered this step growth. Chain growth, we have an active site at the end of the growing chain. I've always tried to think about how do we visualize this and what would the active site be? But let's say we had 100 people in the atrium, and I hand the first person a running baton, right, like a relay race. That's the active site. So they can hand that to the next person and form a chain, and the next person and the next person. But only where you have the baton can you add on a repeat unit. Does that make sense? And so then if I put out another baton, another chain could start. Until something causes them to lose the baton, right? They drop it, the chain is dead, it cannot grow. 2 batons come together, that's it, they fuse, no more. So anyway, that's my best way of trying to visualize it. So we add them one by one by one, but the chain grows super fast. So what's going on in the reaction vessel is most of the monomer is sitting around. You have a few actively growing chains. Everything else is just sort of sitting there. So we are going to focus on monomers with double bonds, specifically this type, vinyl monomers, okay? The dienes are pretty neat, but there. And then acetylene is cool. You can polymerize that and make a semiconducting polymer. It's not super stable, but it's pretty cool that it can conduct electrons. And then these rings actually have a chain growth mechanism. And I just put them up there. We're not going to cover those, but I put them up there to let you know that you can. So we already know that there's initiation, propagation, termination, and then there's side reactions. Side reactions are typically chain transfer reactions. So we have to somehow get the active site on the first chain. The active site on the first chain is when we initiate the chain. The first monomer. The first monomer with the active site is that's the process of initiation. Chains grow. That growth process is called propagation. Chains die. That's termination. And then we can transfer the active site to something other than a monomer, the next growing monomer. That chain transfer is our side reaction. Okay? It can be a good thing. It can be something we planned for. It can be a bad thing that we want to try and control. It all depends. Okay? So we have the three main reactions: initiation, propagation, termination, and then chain transfer. And then, because it's confusing, we're going to talk about three types of chain growth polymerizations: free radical, anionic, cationic, and coordination polymerization. Coordination polymerization requires a catalyst. And that's how we control tacticity. Remember, before exam 1, tacticity?
This is a real B&H birthday story. We've been known for our customer service since 1973.
Okay, so this is, I'm glad it's working. This is free radical polymerization. It's a nice animation. It was produced by a company. I think they sell monomers. Yeah, it's going to show us. Okay, so I really like this flow chart and how it works, but it's a little bit different than our textbook, so I haven't done a lot with it. But so we have initiation, propagation, deactivation, and then there's two ways you can deactivate: termination, and for free radical, we can terminate with combination or disproportionation, and you're going to see those in a minute. Or you can do chain transfer. And that can lead to reinitiation, or it can lead to dead chains. Okay, so this is a nice way of thinking about it and presenting it. It's just not totally in line with our textbook. They're both fine. Okay, but I wanted to show this. Here's our monomer. Got a pi bond, that double bond. They're going to trick you with little arms. But he's not happy because he's by himself. He's a happy initiator. Yeah. So somehow the initiator has to get activated. Once it does, that was the initiation step. Getting the active site on the first monomer. The active site is the little hand. So when it adds another monomer, the active site moves to the end of the chain. Propagation. So every time it adds a monomer, the active site is moving to the end of the chain. Termination by combination of the two chains. Now one of them's ripping off an arm, and the other one's left out. That's deactivated. That's disproportionate. So this was really a chain transfer with the chain transfer agent.
Michaels helps turn your ideas into I did it.
Okay, so this one, yeah, so this one only has termination by combination.
Polyethylene, PVC, and polystyrene are polymers, also known as plastics. They are all being produced with the help of Nourion's organic peroxides via a process called free radical polymerization.
So the company that made this commercially produces the initiator. Okay? The last video, I believe the company makes monomer, but I'm not sure about that.
Let's take a closer look at how this polymerization process works and what these plastics have in common. Since polyethylene is one of the most common polymers, we will use this as an example. The raw material used in the process is ethylene, which is the monomer in this case. While monomer means one part, polymer means many parts. So polyethylene basically means many ethylene parts. But how do we get from one part to many parts? It actually takes 3 steps. The first step in the polymerization process is the initiation. When heated, the organic peroxide breaks apart in 2 radicals. These radicals start the reaction with ethylene. One free radical opens the double bond of an ethylene molecule and forms a new radical.
You have that radical.
Then this new radical opens another ethylene monomer, and this process continues, making the actual polymer. This second step is called the propagation.
So, what's the issue with the way they're visualizing the carbon and hydrogens? It's straight. What else? So the backbone would be at least in a zigzag. Because anybody know the bond angles around a carbon? 109. It's like 109.4 or 104.9 or so. It's something like that. But it's tetrahedral, right? And that's why we talk about tacticity. If a carbon was actually like this in a plane, there'd be no tacticity. So those hydrogen atoms, even if you had the carbon in a straight line, that's, fine for the visualization. But the hydrogen atoms, like you should have some going backwards and some going forwards, right? Because it's not, all those hydrogen atoms are definitely not in a plane. So that's my one big caveat about this video.
Now there's only one step to go to turn a monomer into a polymer, the termination. The polymerization reaction stops once the last radical on one polymer chain meets another chain with a free radical. Then they combine, and the polyethylene is finished. The production of PVC and polystyrene follows a similar reaction. Only the monomer, process temperature, and pressure are different. The production of PVC starts with the monomer vinyl chloride. The difference between an ethylene and vinyl chloride is that one of the hydrogen atoms is replaced by a chlorine atom. For polystyrene, the monomer is styrene, and here the difference is that one of the hydrogen atoms on the ethylene is replaced by a so-called phenyl group.
Look how tiny it is. Right?
We have just shown that while these 3 important polymers are different in composition, they all share the same origin. Nourion, we help make polymers.
Most people.
We help make polymers.
So when I was a kid, the American Plastics Council did all these commercials, and it was "Plastics Make It Possible." That's a good catchphrase. And they had a lot of like medical things and stuff like that. Plastics make it possible, like trying to show you that there's good things that come from plastics. And yeah. So some fun videos to get us sort of thinking about the 3 steps. And we're going to start with free radical polymerization. Okay? And I'm going to do the same thing as we did for step growth. We're going to go through this real fast. We'll slow down and look at the mechanisms on the document camera. Okay? So the mechanisms for chain growth polymerizations, we have to think about initiation, propagation, termination, and whatever chain transfer. Sometimes termination is chain transfer. So there's a mechanism for all of those things. And then we've got free radical, anionic, cationic. We will not look at mechanisms for catalysts, okay? For the most part. Just barely touch on it. So there's all kinds of reactions. But the overall reaction, I've got N. I've got, ooh, a new marker. The little things that are exciting. I was just going to write a CO. Okay, if I have N of those and I polymerize that, I can be like the frowny face, right? The frowny circle, right? So I've got a double bond. I just have to open it up, and that's my wraparound bond, okay? I usually do it on the document camera. I'm like, double bond, wraparound bond, double bond, wraparound bond. So all I have to do, there's no leaving groups. There's no small molecule byproducts. There's no atoms shifting around and moving different places. All I have to do is take the double bond and make it the wraparound bond. So now I've got carbon, CH2, CHR, the wraparound bond, parentheses, and the number of repeat units. So as I show you all these crazy steps and mechanisms and all of that stuff, remember, that's easy. The one thing I will ask you to be able to do is to recognize, if I give you the mechanism reaction, if I give you the individual reaction with the, the arrows and stuff, to recognize what type of chain growth polymerization it is. So that's essentially, you're telling me what the active site is. Is it free radical? Is it cationic, anionic, or is it a catalyst? And then you need to be able to tell the difference between initiation, propagation, and termination. So like if I gave you this bottom one, the top is the activation of the initiator. If I gave you that bottom one, you would say initiation, free radical initiation. Okay? So it'll be, so being able to recognize that, not being able to draw it, is a lot easier, right? And knowing how all of this chain growth steps, we need to know all of this to do the kinetics, chain growth kinetics. So even though this is what I'm testing you on for the synthesis, understanding all these steps is really important for our next section, okay? So propagation, here the chain is growing, it adds, and now the active site moves to the end of the chain. This monomer adds, and when we have this, the active site goes to the end of the chain. And we do it over and over and over. For free radical, we can have termination by combination. 2 radicals come together and form a single bond. I probably should have asked you guys if you know what a free radical is. Anybody know what a free radical is in organic chemistry? Go ahead.
It's basically just an electron.
An unpaired electron, a solo electron, right? Electrons want to be in pairs in their orbitals. They want to be in pairs, right? So if you have an unpaired electron, it's highly reactive. So a free radical is an unpaired electron. So if you have two free radicals come together, they can pair up and make a single bond. That's why we can have termination by combination. Okay? Termination by disproportionation, what happens is one of the two chain ends, two growing chain ends come close to each other, but somehow they don't form a single bond. One of them rips a hydrogen atom, not a proton. This is a little unusual. It rips a hydrogen atom off, and so now it's a dead chain because it took the proton and the electron, and so now it has a pair of electrons, and so it has that hydrogen on the end of the chain. That's what's happening right here. This one is ripping this hydrogen atom off, and now this is all dead. Well, now we have a radical on this carbon and a radical on that carbon. Those two, that's the two radicals, they come back to make the double bond. Okay? That's disproportionation, which is incredibly hard to say in front of a class full of people. Today, it's not going so badly. Okay?
Wait, where did that second H go?
So this one ends up over here. See it's CH2 and then the X.
Wait, why does the arrow point it going in the other direction?
This electron, it should be, this is from Coleman and Painter, and they were not organic chemists, and these arrows are just to guide the eye. They're not following organic chemistry rules. On the document camera, we will follow proper organic chemistry rules. Okay? So. Chain transfer, we can get long chain branching, and we'll talk more about the branching on the document camera. But this right here, this is a chain transfer agent. This was added to help control the molecular weight of the polyvinyl chloride. So this is added. This chain transfer reaction is planned. It's a good thing, right? You're adding a chain transfer agent. You're using it to control your polymerization. Your chain transfer agent can be active enough that it can initiate another monomer, which we saw in the first movie. It can be that when you transfer to the chain transfer agent, that free radical is pretty stable and it won't initiate another monomer. And there's, you want to do those things based on what you want your end polymer to be. Okay, so this is how free radical polymerization is highly energetic, hard to control, and so this is a means of trying to control things. So, short chain branching. This is the dog biting its tail. Okay? So you remember how we just looked at that disproportionation? If the free radical's here, it's just the end of the chain is looping back on itself and it's grabbing a hydrogen atom, usually about 5 carbons back. And so it grabs the hydrogen atom. So it wraps around, it grabs this hydrogen atom. So now that is dead, but now we have a free radical a few carbons back. Oops. We have a free radical 1, 2, 3, 4, 5 carbons back. So that can add a monomer. When it adds a monomer, you got this little branch hanging off the side. This is super common in polyethylene. And so this is one of the reactions that makes low-density polyethylene as opposed to high-density polyethylene. Okay? So these branching, having that branching in polyethylene gets you a very different material. And so if you don't want this to happen, you need to control it. If you want it to happen to a certain extent, you've got to have your conditions so it sort of promotes this to the level that you want it. And you can do, and the same thing can happen with long chain branching as well. Here's an initiated vinyl chloride radical. It adds a monomer. So there's propagation. It can keep adding until it goes and goes. Termination, we've got combination. Two of them come together. And then we have termination with chain transfer. When you have termination by combination, on average, what happens to the molecular weight when you have termination by combination? But a specific amount. What on average? It doubles. It doubles. So at some point when we were looking at talking about molecular weight, I'm like, you can have a bimodal molecular weight distribution. And this is, if you have termination, this can be your termination by combination and your termination by chain transfer or disproportionation. So these bimodal peaks in molecular weight distributions actually occur. Go ahead.
Is it just like a random, like this many terminate by this and this many terminate by this? Is that just like a random? It's determined by probabilities, and so some are more probable than others as opposed to just true randomness. And we can't predict those probabilities. You need to know the chemistry of the monomers and stuff at a level that I've never learned. So it would be something you look up. And then there's some using chain transfer agents as a way to get around it, right? To not have to worry about combination and disproportionation. And this is really only a concern in free radical polymerizations because can two anions come together and make a bond? No, we'd have 4 electrons, 2 negative charges. So no, right? We can't have termination by combination for our anionic polymers, or anionic or cationic. For ionic polymerizations, there is no termination by combination because like charges repel. Like charges repel. So you can't. And you'd either have no electrons in the cationic or you'd have too many electrons in the anionic. So, anionic, I stole these mechanisms from Macrogalleria, so they're correct. They're not from Coleman and Painter, okay? So we have the negative, the lone pair attacks the carbon, that flips the lone pair from the pi bond up onto the next carbon. So this is the initiator, butyl lithium, and then so now it's initiated, the active site's on the first monomer, and it's going to keep polymerizing. And so termination for anionic polymerization and cationic polymerization is typically by chain transfer. Termination is by chain transfer. So there's a special class primarily of anionic, but you can do cationic, but it's commercially they're mostly anionic, called living polymerizations. Living polymerizations are cool because you prevent chain transfer and you prevent termination and you prevent any side reactions,
And you've got, if you can stabilize that active site enough, you can polymerize all of your monomer and chuck in new monomer. Now you got a diblock copolymer. Maybe you can go back to the first monomer, and then you have a triblock. Or a new monomer, have a triblock. So living polymerizations are really cool because, one, you can get incredibly narrow polydispersities. Two, you can make block copolymers. And for a polymerization to be living, it's really controlled. So you just have a whole lot of control over your polymerization. And it can get you access to polymers and architectures and stuff that you might not otherwise be able to do. So classic example is styrene butadiene block polymer. And it's usually commercially what's made is styrene butadiene styrene triblock SBS rubber. So you have the living polymerization of styrene, and then the styrene anion can polymerize the butadiene. Unfortunately, the butadiene can't initiate styrene, so you have to make this one and use a coupler to get it to make the, which is shown here. So you polymerize the styrene. This can initiate the butadiene. This cannot initiate styrene. This can't get the styrene monomer to polymerize. So you have to put in a coupling agent. You couple the two of them together, and then you have styrene, butadiene, styrene. And that's it's a neat, right? You've got polystyrene, you've got butadiene. So it's a hard rubber. It's used in shoes, tire treads, and wherever durability is really important. Cationic polymerizations. This is almost true. If you just turn the arrows around, you've got, from anionic, you've got a cationic polymerization. So the arrowheads in reaction mechanisms always go the way the electrons flow. Okay? Might not have known that. And there's two barbs on the arrow. Tells you there's two electrons moving. So when you're looking at free radical reactions, the arrowhead should only have one barb, because only one electron is moving. Okay. But anyway, so we have our cationic initiator. Now the two electrons from the pi bond flow towards the initiator. That forms a new single bond. That means this carbon is a carbocation, which means it's going to grab two electrons from the pi bond of the next monomer. That makes this bond right here a new single bond. And then the active site moves to the end, and you keep doing that so you get your polymer. So anyway, we'll look at them a little more slowly on the document camera. Coordination polymerization, we have some kind of catalyst. Why do we care about this? Because the catalysts allow the monomer to coordinate with them in a specific way. This is cool. I should have stopped, but we'll finish. This is really cool because you can control tacticity. If the monomer can only coordinate to the catalyst in a certain way, see why it's called coordination? The monomer coordinates to the catalyst. If it can only fit, you can think of it like a lock and key. If it only fits a certain way, you can control the tacticity. And that's a big advantage of the coordination polymerizations. Okay? Tacticity. Okay, so we didn't do the end of lecture note review questions, but that's okay. We'll do them together, step and chain growth. So we'll do the document camera on Thursday. Oh, chain growth synthesis, the overall reactions are pretty easy. Double bond, open it up. Double bond, open it up. Think about the video, the goofy video with the frowny faces and their little arms. They get activated. They open their arms up and start smiling, right? So that double bond opens and becomes the wraparound bond. Double bond, wraparound bond. Double bond, wraparound bond. Now, I gave you these all as skeletal structures to make you look at them as skeletal structures. What can you do if you don't like looking at skeletal structures? Yeah. So just put your CH and your CH2. Those are really the only ones you need, right? Because the side group is going to be the same. You're just going to write the side group down exactly as it is. So we've got CH2 double bond CH with the side group. This is polystyrene. Oops. I just wrote a B for whatever reason. Polystyrene. So I'm going to draw the wraparound bond. I've got CH2, CH with the ring. Right? I got a carbon here. This is a CH3, right? Because the end, it just ends. And this is going to be a CH2. Double bond opens up and makes the wraparound bond. CH2, single bond, methyl group, carbonyl, oxygen, methyl group. We need the wraparound bond, the parentheses, and the number of repeat units. This is polymethyl methacrylate. You don't have to remember the names, but it can be helpful in life, right? What's PMMA? What's its trademark, or what's its trade name? Plexiglass. Okay. What's this one? Anybody know? Yeah, it's this. Yeah. So it's not ethylene when it has the CH3, it's 1, 2, 3 carbons. So F is 2. What's 3? Prop. Yeah. So it's propylene. We say propylene because we like the way it sounds better than propene, which is what it should be. Okay? It should be ethene, so polyethene and polypropene, and the monomer should be ethene and propene. But we don't like the way that sounds, so we just add the "ul" and then the "ene" on the end. So we say ethylene and propylene. It's non-standard. All right. So you get the pattern now, right? CH2, CH with the side group. Then you add the wraparound bond, parentheses, number of repeat units. Polypropylene. What's this one? What's the name or the trade name on this one? Those are fluorines. Getting there. It's Teflon. It's Teflon. So it's poly, tetra, because there's 4, fluoro, ethylene, PTFE. Okay? We'll put those carbons in if that's easier. So now we have CF2, CF2, wraparound bond, parentheses, number of repeat units. Is tacticity important for this one? No, yeah,
Because
correct.
it's all the same. It's no different, basically, than a.
We have to.
Methane bonds.
Right. So we have to talk about tacticity, we have to have a carbon that's attached to 4 different things. So this carbon is. This carbon is. Yeah.
For tacticity, carbons bond to tacticity doesn't matter.
Yep. So you have to talk about tacticity. We have to. The carbon has to be attached to one half of the chain, the other half of the chain, and 2 different things, or there's no, or it's not attached to 4 different things, and there's so no tacticity here, no chiral center, no tacticity. This one, so isotactic polypropylene is what we know and use. Atactic polypropylene is goo. It's not a commercial product, as far as I know. Okay. Yeah.
Okay, I probably should know this, but if it's just like the line going off, is that how you know that you add a CH3?
Yes, because
So
the
it's always gonna be
the end is always a carbon. And how many bonds does carbon need? 4. So it needs 3 hydrogens. Does that make sense? Yep. Okay, so I can put my CH, I can add my CH2, CH. Okay, what's this one? Anybody know this polymer? That's chlorine, PVC, polyvinyl chloride. So we've got CH2, CH with the chlorine, wraparound bond, parentheses, number of repeat units. Easier than the step growth, right? Okay. So at the end, we'll go backwards. Okay. But let's.
At the end, aren't we going to do the other synthesis growth one?
We're going to do it right now. Okay. We're doubling up on quizzes today. Sorry. I was going to do this one at the beginning of class and that one at the end of class, and I screwed it up. So this is Step Growth, Module 5, Quiz 2. If you submit the wrong picture to the wrong thing, Zimu's clever. He'll figure it out. Okay, so just make sure you submit to both quizzes. So, here we go. Complete the following reactions. So we've got a hydroxy acid, and we've got a diamine reacting with a diacid chloride. So can you guys go ahead? Oh. Yeah, it is switched. I'm like, switch it. Anybody need more paper? Okay, so I couldn't remember how many carbons were in there, so I just wrote it as an R. All right, so what's the leaving group? Okay, the small molecule byproduct, I heard a lot of people say H2O. Okay, what is the leaving group? OH minus. What is it going to grab on its way out the door? Yep, the proton. I'm gonna do this reaction n times. So I have how many? Then I write down what I have left over. What's my next step? Say it. Wraparound bonds. Okay. And how do I know I'm doing the wraparound bonds in the right place? What do I check?
Or the ester.
Right. So if I remember what an ester is, I can go, okay, I need a carbonyl oxygen or an oxygen carbonyl. How many bonds does carbon need? 4. How many does oxygen need? 2. Yeah. So those are the ways to sort of like check what you're doing. And then by this point, we always remember our brackets, right? And our number of repeat units. Mm-hmm.
Does it matter if you have the double bond to the oxygen on top or the bottom? Like going up or down?
Doesn't, no. Because these are single bonds,
Yeah.
so it can rotate. Nothing.
What happens if you take the OH from the other side?
That's not the way the chemistry happens, but it will work out okay.
But it won't look the same at the end, though.
You basically just move the brackets.
Yeah.
1 over. The repeat unit is what we're looking at here.
Yeah, because then you have, so if I write down the next repeat unit, it's going to go OR carbonyl, OR carbonyl, OR carbonyl, right? N times. So what you're saying would give you the brackets here. So it's the same, it gives you the correct result, but it's not the way the chemistry happens.
And for the purpose of this class, is it okay?
Well, because we're not going to be grading on the mechanism. Yes, but it's better to do it this way. If you make a mistake, you're in this case you're very fortunate that it's not going to matter. Now, if this was a chlorine, it would screw you up if you were trying to take off the whole OH on that side, right? So it's also to your advantage if you do it this way because the chlorine is there. Oh, and I see that when I wrote this down, I wrote down the wrong thing. So that is. I was trying to write it out from the little picture while you guys were looking at the next page. Got it wrong. Okay, so now I've got my diacid chloride. What's my leaving group? Yep, so it's that Cl minus. And what is this Cl minus going to grab? Yep, the proton. Okay, so my small molecule is going to be HCl. How many am I going to have? 2N. So how many linkages per repeat unit am I going to have? 2. Exactly right. Okay, I go.
Does that always correspond?
AABB polymerizations are going to have 2 linkages per repeat unit, except for carbonates. So I asked you to do a carbonate reaction in your homework that's due on Tuesday, but you're not responsible for that for the test. And that's just the way the carbonate is formed, that you end up without 2 of them. But in general, AABB type polymerization, you're going to have 2 linkages per repeat unit, where an AB polymerization, you're only going to have 1 linkage per repeat unit. Go ahead.
How did we get OH from H2N? Is this the second one?
This is the second one.
Yeah, it's H2N. It's like R instead of OHR. OH.
It was H2R.
I'm sorry? I'm not following.
It's not an alcohol.
Oh, it's an amine. I'm fixing it. The small molecule is still right. This is wrong. Good catch. And again, like, so you see the little picture on the right-hand side? That's what I was trying to write from. So because you guys were working on the second one by the time I'm like, oh, I need to write this down. Okay. So yeah, plenty of screw ups today. All right. So now we've got this piece from that monomer, and we've got this piece from the other monomer. If these are written closely enough, you don't actually need to write the bond in there, but I've got a gap, so I need to put my bond in right there. And the amide is NH carbonyl. Need the wraparound bonds, repeat unit, parentheses, right? Number of repeat units. How do I check my structure?
Carbon has 4.
Yeah.
Nitrogen has 2, and nitrogen has 3.
Yep. Exactly right. So the way you double check your structure is you make sure carbon has 4 bonds, nitrogen has 3, oxygen has 2. That's how you double check. Did you? They're the same. Yeah. How many of you caught they're exactly the same? Good. You're the ones who finished faster. Okay. So let's slice through the linkages. There's the middle linkage. And then the second linkage is on the wraparound. Okay. So we've got the amine piece and the diacid piece, or the diacid chloride piece. So if we write down the amine, I've got NHCH2 6 times NH. We can check my structure and see if I drew it right. 1, 2, 3, 4, 5, 6. Okay. So even this one, it is the same. Okay, we just said nitrogen needs 3 bonds. So we need to make this NH2. And then we need to write down our acid, diacid. We got 2 choices. What are our 2 choices? OH or CO. What do we want to do? OH. And carbon has 4 bonds. And then if you didn't get to this one, that's no big deal, right? I couldn't get it on the screen all at once. So that was the one. If you were already finished with those 2, you could do this one. So here we've got oxygen carbonyl. That's our ester. So that's where we're going to make the slice, right? So now I write down carbonyl, 1, 2, 3, 4, CH2, 4 times oxygen. Oxygen needs a hydrogen or a proton, right? We got to put that proton back on. We got to put our OH minus back on.
Can you go back up real quick?
Mm-hmm. Oh, Okay, so I'm going to tell you a little story. Everybody good on this? Okay, so we've got two quizzes to submit today. I'm going to tell you a little story. Oh, you can submit it, and then because I always have you just submit one page, and then we can try and do the other one if we have time before. Okay. So at the very end of class on Tuesday, I talked to you briefly about coordination and polymerization. Showed you this slide. Coordination and polymerization is crucial because that is how we can control tacticity. Okay? So we're going to talk a little bit about polyolefins. Olefin is sort of an old term for hydrocarbon. So a polyolefin is a polymer that's made just from carbon and hydrogen. Okay? And it's saturated, though, so there's no double bonds. See this picture on the left? See the lower left-hand corner? Those are stairs for people. That's a walkway for people. That's a polymer bubble.
Like it's bubble blown from that.
Yes, that is the polymer is being extruded from a ring and blown. So it's a melt, not melt blown, which is a non-woven, but it's a blow. It's not blow molding. But anyway, they are, yeah. So I can talk to you about how this all works and how it cools and stuff. I have no idea how you get it started. Like when you've got the molten polymer coming up from the bottom, how do you get it to get up there? And eventually, so it's got hot air at the bottom, and it's stretching biaxially. And then it goes up, and then it's blowing cold air. So now it's a solid film, and you can take it onto a roller and make it into trash bags, or you can have it slices one edge and unfolds and make gigantic plastic sheeting, or all kinds of things. So, I mean, polyolefins are, like, the way they can be processed is really, it's cool. It's pretty amazing. So polyethylene can be rotomolded into my whitewater kayak. You can take, that's polyethylene film, right? All kinds of different things. Here's polyethylene sails and nautical ropes. Years and years ago, I did a swiftwater rescue class, and they were talking about, all the rescue ropes are polyethylene, but now there's some Spectra ropes that are being used. I'm like, well, that's still polyethylene, but okay. And I knew what they meant. And I'm sitting there and I'm like, why don't they use nylon? Because one of the disadvantages is the amount of give that's in a polyethylene rope. So
it's dynamic, right? Not a static rope.
Depending on the situation for whitewater rescue, it could either be a dynamic or a static load, depending on what you're doing. So I should have known this. The instructor looked at me and was like, you can't use nylon. Anybody know why you can't use nylon?
It doesn't respond well to water. It doesn't respond well to water.
It's good in water. It's pretty. It doesn't degrade. It's pretty good. The density of polyethylene is less than 1. The density of nylon is not. I'm like, oh, it doesn't float. So, yeah. Okay.
It's one of those, oh, right.
Yeah, it's like, yeah, that's a total facepalm, right? So ethylene, propylene, butylene, methylpentene, isobutene, these are all polyolefins. The first polyolefins, so you remember our last history of polymer science and engineering lecture, we really only talked about step growth polymers. But in the 1930s, Fawcett and Gibson of ICI Chemical Company, this is like the UK version of DuPont back in the day, right? This was the UK's major chemical company. They polymerized low-density polyethylene using a high-pressure process. When we're talking about this process in kinetics, I'll tell you that they blew up their lab. Okay? And this was one of those serendipitous discoveries. They made a mistake, and then they made this cool stuff. So, in the 50s, that's when their first catalyst for low-pressure polymerization was discovered, and they were discovered almost simultaneously by a German investigator, Ziegler, and the Phillips Petroleum Company in the U.S. And I can't remember those scientists' names. So high-density polyethylene was first produced commercially in 1954 by Phillips Petroleum in the U.S., and it was using a metal oxide catalyst. And then it was done by the German chemical company, Host, using Ziegler's catalyst. Nada was an Italian scientist, and he initially collaborated with Ziegler, and they were friends. But you'll soon learn that they did not stay friends. And so they first produced polypropylene. Nada was the first one to produce polypropylene that was useful. Okay? And then in the 90s, Exxon developed what we call linear low-density polyethylene, which is actually a copolymer. So you're controlling the amount of short chain branching. So this is where they blew up their lab. This is the ICI guys. Okay, so they were doing high pressure reactions, and they thought they were doing something that they were not doing. And their pressure reactor had a leak, so it was actually not as high pressure as they thought it was. And then there was some contamination, which was the peroxide, which polymerized the ethylene. And they opened up their reactor, and they're like, what is this white material? And they tried to characterize it, and they're like, it's a fabulous insulator, and we needed insulators, right? Electricity was becoming a thing. And they didn't really know what it was or really understand it. But they wanted to pursue it.
This is useful.
Yeah, this is cool. We want to do this. Well, the big bosses were like, okay, you can keep going a little bit, but you still need to be doing what you're supposed to be doing, what the big bosses wanted them to do. So then they try and reproduce the reaction that led to the weird white solid.
Did they blow their lab up again?
And that's when they blew the lab up. They did this. That's when they blew the lab up. Then the bosses were like, no more. You need to be doing what we told you to do. They didn't listen, and they kept pursuing it.
But were they like on the DL now?
Yeah, but this would never happen today, right? You blow up the lab, you don't get to keep pursuing the research you were doing that blew up the lab on the sly, hiding it from your bosses. That is not going to happen, right?
Depending on what it is, sometimes those are just, all right, not what we wanted, but keep going.
Yeah.
Be a lot more careful.
So the pressure reactor blew up because pressure relief valve failed. So not exactly their fault. But they eventually sort of figure out what they're doing. There's the pilot plant, the pilot reactor, and it's on railroad tracks. So that gives you an idea. See those little wheels? Those are little wheels that fit on tracks. So it's, as wide as train tracks. And they made low-density polyethylene. And eventually it would become used as insulation for cables, which was hugely important, right? This is pre-World War II. Without polyethylene and the insulation, you wouldn't have the fighter planes that they used in World War II. Also, after polyethylene, they started making a lot of other things, and one was plexiglass. And that wouldn't have flown with all glass. It wouldn't have been as efficient, right? They needed the plexiglass for the cockpits and stuff.
This is like a dumb question, but why did they put it on that little rail cart?
Oh, the pressure reactor? Well, it was a way of moving them around and that kind of thing. I mean, it's really heavy, right? It's a big insulated, double-walled, it's made to have really high pressure reactions, so it's like an intense thing. They're not supposed to blow up, right? So low density polyethylene, major market for it, cable cladding, garbage bags, agricultural, landscaping, all kinds of things. We're going to skip that. So high density polyethylene has little to no branching. Low density polyethylene typically has short chain branching. If it has long chain branching, they usually don't. That's not what you want commercially usually. And we've seen this before, right? If we want to make film wrap, do we want high density or low density polyethylene? Low density, right? If we want the milk jug, we want high density. And we've looked at this slide bunches of times. Polypropylene. So ICI, they developed a free radical process to make polyethylene. And it's low density polyethylene because it's really hard to control free radical polymerizations, and it had branching and all that stuff. They tried to make polypropylene, and it did not work. Did not work at all. You cannot polymerize polyethylene free radically. It's because the radicals are too stable. It won't work. So the first metal oxide catalyst and the first linear high-density polyethylene was Hogan and Banks, and they were from Phillips Petroleum. Then we get to Ziegler and Nata. So Ziegler has developed a catalyst, a different kind of catalyst. It's called a Ziegler-Nata catalyst now, but he developed a different kind of catalyst that was based on titanium that would polymerize polyethylene, and he was studying it. And Nata reached out to him and was like, I want to know more about your catalyst, or he published, or I don't know the exact timeline. And so they collaborated. They talked to one another. Ziegler happily talked to him about his catalyst, and Nata started studying and doing research on the catalyst. He tweaked it, and he also started using propylene monomer instead of ethylene monomer. So eventually, Ziegler and Nata got the Nobel Prize. And in Ziegler's acceptance speech, he said the development began at the end of 1953 when Holzkamp, Briel, Martin, and myself in almost a few dramatic days observed the gas of ethylene could be polymerized at 100, 20, or even 5 atmospheres, and finally at atmospheric pressure very rapidly in the presence of certain easily prepared catalysts and give a high molecular weight plastic. So the free radical polymerization was done at very, very high pressures, hundreds of atmospheres. So the fact that they got this down to atmospheric pressure was a big deal. So the number of methyl groups per 1,000 carbons, that's telling you how many branches you have. Does that make sense? If you have a CH3 carbon, that's got to be at the end of a branch or the end of the chain. So if you have 30 per 1,000, that means you have branches, right? And then Ziegler has many fewer, right? It's gone down an order of magnitude. And then the metal oxide from Phillips Petroleum, it went down even another order of magnitude. So they're making more and more linear polyethylene, fewer branches. So Nada, this is the middle of 1954, and his Italian coworkers, they got the original specs of the HDPE catalyst from Ziegler, and they used it to polymerize propylene. And they obtained a partially crystalline propylene. Eventually, they found out it was mostly isotactic. Okay. So Nada and his co-workers tweaked the catalyst and increased the isotacticity of propylene from 50 to 70% to 80 to 90%. Pretty amazing, right? So they're really controlling the tacticity. So I usually just read this one because this is a good part of the story. Okay, so in 54, May of 54, Nada and however we say that, Cantatini's chief patent lawyer. So we've got every country had their own big chemical company, right? Back in the day. So that's the Italian one. So Nada and the chief patent lawyer from the Italian company went to see Ziegler. Nada and his coworkers had successfully polymerized propylene using Ziegler's HDPE catalyst, but they supposedly didn't tell Ziegler. Probably the patent attorney's influences there. They simply asked the question, have you polymerized propylene? Ziegler recalls that he said no, but we've made ethylene and propylene copolymers. I'm focusing on ethylene. On the other hand, Nada and the lawyer say Ziegler's answer was no, it won't work for propylene. Ziegler categorically denied he said this. The beginning of June of 1954, Nada and the Italian company filed for a patent on polypropylene. Not long after this, Ziegler and Martin synthesized polypropylene and also filed for a patent. As you can imagine, the trust and friendship that had existed between Ziegler and Nada fell apart, although they had subsequent agreements struck between them concerning royalty sharing and that kind of thing. And the two men stopped talking to each other. The irony is, neither Ziegler nor Nada won the product patent case, the patent for polypropylene. So like for the material, not the process of making it, but the material. Okay, they didn't get it. Who got it? Phillips Petroleum. Okay, so there were 3 separate patent applications on the creation of polypropylene filed in the early 50s. One was by Phillips Petroleum, one by Nada, one by Ziegler. Each one dealing with a catalytic low-pressure polymerization of propylene. Nada was the first to publish his findings, and Ziegler and Nada were awarded the 1963 Nobel Prize, in part based on this discovery. The battleground now became the U.S. courts. because it's the biggest market. That's where they cared the most. Okay. So, who deserved the product patent? Okay, this is a lawyer's dream come true. It's a big discovery period. Everybody has a major chemical company with deep pockets, right? This is going to go on. So it is a cash cow. It didn't hurt the bank balances of a myriad of expert witnesses consulted either. Coleman and Painter talked to one expert witness who said, I put my kids through school on polypropylene, and now I'm putting my grandkids through school on it. Not only were there three major players, the U.S. court system, the U.S. Patent and Trademark Office involved, but other companies, smelling possible spoils, entered the fray and muddied the waters. Believe it or not, the case was not settled until 1983. No, 30. 30 years after propylene had been discovered. Finally, an appellate court settled this particular dispute, the product, not the process, but the product patent, in favor of Hogan, Banks, and Phillips Petroleum. This is, of course, only part of a much larger and more complex story involving many other patents in this broad polyolefin field. As far as I know, they're still fighting. Yeah.
Are the originals oh yeah, they're dead. Okay.
Well, these are roads.
Oh.
I
thought those were dates on the end.
Yeah. No, those are their, yeah. So those are their lifetime. 1903 to 79, 1898 to 73. I think that's right. But the street, so in Italy, so Coleman and Painter always joke, you can tell how important someone was based on the size of the street they have named after them. So in Italy, maybe it's the opposite in Germany, I do not know. Here is Nada. That's Nada's road. Here is Ziegler's. So propylene, it's used all over the place. When I was a kid and skiing in Maine, polypropylene, polypro was the rage. It was the high-tech long underwear. You put it in the dryer, it'd melt. A lot of Nalgene is polypropylene. It's very chemically inert, so it makes great chemical storage bottles and that kind of thing. Shovels, chairs, old school luggage. That's pretty funny. Containers, parts, all kinds of stuff. There's coordination, polymerization. So the 20s, macromolecular hypothesis. Oops. 40s, ICI develops low-density polyethylene. So 20 year, the metal oxide and Ziegler-Natta catalyst. A little longer than 20 years. 1990s, the metallocene catalyst. This is linear low-density polyethylene, ultra-high molecular weight polyethylene. And so we're really overdue for a big breakthrough. But so this is really just synthesis of polyolefins. But I'm thinking maybe I should put Spectra on there. It's not really the same thing, but it's another big breakthrough with processing polyethylene as opposed to making it. So.
How do they process Spectra? That's so different.
It's a special spinning process, and I just read it in the ebook, and I can't remember. But the big deal is that the chains are so aligned in the fiber direction, and that's what gives its incredible tensile properties. and high strength. So you've got the chains they're forming almost extended chain crystals instead of folding back and forth. And so it's a lot stronger. And we will cover that. That will be right at the end of the semester. So, okay. So I'm not going to get to the document camera today, but we do have time to do our second page of our quiz. This is chain growth. Chain growth 1, but the PDF says 2. I gotta look at that. I went through all of the assignments and updated everything, and I thought I caught all those typos and changed the file names and fixed everything, but no, always messes it. So just try and get started on the first couple, and then we'll just go through them real quick. Looking at what you did earlier might help you. Okay, so we have time to look at all this. Now we're taking the wraparound bond and making it the double bond. We're just going backwards, okay? Polystyrene, take away the wraparound, make that a double bond, right? PVC, take away the wraparound, put back the double bond. So this is polystyrene again. So we get rid of that wraparound bond and add in the double bond. So double bond and the ring.
Are we gonna have to be able to draw skeletal structures?
Nope. Although the ring is way easier as a skeletal structure. So, yep, so you can just write it, sort of as that double bond without the carbons, or you can write it out all the way. So I'm just going to cross off that wraparound bond and add in that double bond. So I've got, see, that's easy to write. Right? I can do the same thing here. Very easy to write. But carbon, double bond, CH2, double bond, and the chlorine. CH2, double bond, and the methyl group. This is polyacrylonitrile. That's the only one we didn't have on the what's the first page. Okay. Same thing. Cross off the wraparound, add a double bond. So I've got the double bond to a and then this. This is weird, right? This side group is a weird one. Let me write it out without the skeletal structure. This is one case where even though you're not supposed to write carbons on skeletal structures, lots of people put the carbon here because it's just so weird to see a single bond going into a triple bond. It's just really...
Might be easier also if you put it at an angle. Assuming you don't care about cis trans isomerism.
Yeah.
If you put the triple bond, just make it obvious there's a...
Yes, right. But one of the advantages of skeletal structures is you're trying to show the correct bond angles. So that's why you keep it straight. So this is a nitrile group. So this is polyacrylonitrile. You guys feeling good about the chain growth structures even before we did the mechanisms and stuff on the document camera? If you take the few seconds to write them this way, most people don't have any trouble, right? The only trouble people usually, people who struggle with the chain growth synthesis, the overall reactions, it's usually they have a hard time with skeletal structures. So either get more comfortable with the skeletal structures or rewrite it. It won't take you that long to rewrite it. Okay. Any questions? We're out of time.
Have you decided when the exam tube is going to be over?
We didn't get as far as I wanted to today, so I'm thinking Friday, a week from tomorrow.
Oh, so not tomorrow, but next week.
Yes.
Okay.
Yeah.
I can do
Has there been any update on the
Yes, but I did not get to it today. I should be able to get all of that pushed back to Moodle today. Oh, so then, because I'm not good at simple arithmetic, exam 1, if you add up the 3 parts, it's out of 104. So I didn't change this to convert this to a percentage or anything. So everybody's got a few extra points, right? So the average was 82. Again, that's out of 104. And so because the average is in the normal B territory, the grade cutoffs would be sort of the standard, if that makes sense. Yeah.
Okay, I'm just looking online. It's like, you don't want to work on it some way, but Moodle's version of the grade is weird because it says I have a 62.5 as my grade.
Yeah.
But I'm looking at my percentage, it's like 71, 94, 96. And that doesn't add up.
Yeah, okay. So I pushed it to Moodle this morning.
Okay.
And I didn't look at it in Moodle. It's not the first time.
I just guessed Moodle being stupid.
Yes. So don't look at your scores in Moodle. Okay? Let's add up your scores, add up ABC, and then so we got 396s, right? So average was an 82. So pretty good. Nobody's way down here. So everybody, even if you're down on this end, everybody in here can still do really well on this in this class, okay? We got 3 more exams. It's all good. Okay. So let's say the average was 72 instead of 82. I would have drawn the line on here and said, okay, well, so from 70 to 80 is a B kind of deal. Does that make sense? But since it's an 82, 80 to 90 is a B like normal. Okay? Yeah. Any questions? So again, thank you for pointing out that Moodle screwed up the numbers again. So Moodle likes everything to be a percentage. So I don't know. I will get it fixed in some way, which will probably involve tech support. So that because it's a way easier and there's much less margin for error if I hit submit from Moodle to the grade book for final grades. Like it will sit, you can submit from Moodle to my pack and get your grade, and that is much safer than me trying to do the drop down in Moodle over and over. Okay, so physics has an exam next Tuesday. That's what I'm hearing.
So does differential equations.
So you have two?
No, I have differential.
No, you have, okay. But how many of you have an exam on Tuesday? How many of you have a project due over the weekend?
It looks like it doesn't look like
Thank your buddies, right?
He just posted that this morning.
It says do something.
He just posted this.
Whole project. This part of it.
Someone is having a project due the weekend that got posted today.
Yeah.
Apparently.
That's making me feel better about being wishy-washy on my exam dates because I like try and be flexible. Okay. So we'll see how far we get today. So now I won't rush through everything. If we're slow, we're slow. Okay. It means we will be rushing at the end of the year. But okay, so we need to go through and look at some of the mechanisms of chain growth reactions. And that is going to be helpful. And so it'll only be a few points on the synthesis exam because we're really focused on the overall reactions, but it will be really helpful in understanding kinetics, which is our next section. Okay, so you know that academic regalia comes from the Middle Ages when they were running around in cold, drafty monasteries and castles and stuff, and it actually is quite warm. So, and the hoods that we get, I took mine off. But like if you earn a PhD, you get hooded and you have a hood that you wear over your academic regalia. And that comes from the same Middle Ages because it was a hood that they wore to keep warm in the drafty monasteries and castles.
Basically, you've learned more, therefore you get to be warmer.
Right. Yeah.
Encouraging people to pay us more money.
So, anyway, it's when we used to do commencement out in the yard in the blazing hot sun in May, it was a little bit miserable at times. But my hat worked really well in the rain. I had a bag over it because I didn't want the felt to get wet. But I'm like, this big brim. I'm like, I didn't get wet at all. All right, so we're going to start with free radical polymerization. It's the hardest. The anionic and cationic polymerizations, they're pretty straightforward after this. Okay, so The overall reaction, we have a double bond, we pop it open and make the wraparound. Double bond, pop it open, make a wraparound bond. So I'm going to open that double bond. I'm going to have CH2, CH with my side group, the wraparound. Need the parentheses and the number of repeat units. We've got this down, right? Don't even have to study this one, right? Everybody's good? Okay. The mechanisms are more complicated. Here's your organic chemistry little lesson of the day. If I have a single barbed arrow, means 1 electron moves. If I have a regular arrow with 2 barbs, means 2 electrons move. So you can, just looking at things, you can learn quite a bit. Okay. This is our initiator, benzyl peroxide. How many of you have heard of that? How many of you have it at home? Where is it? Where do you find it?
I want to say, maybe wrong. I want to say it's like plain alcohol. No, it's not.
It's in the medicine cabinet, or where your skincare is. Snack me, acne. Acne medication.
I was thinking of something else. A different type of peroxide.
Oh, hydrogen peroxide.
Yeah, hydrogen peroxide is used as a substitute for rubbing alcohol in wounds.
Yeah, except for you're not supposed to use it. It's like old school. It's damaging to your skin. It will kill the bacteria, but it also kills the healthy cells. So you're discouraged from using hydrogen peroxide.
You're also discouraged. You should be blowing on it ever.
Yes, yes, that's gross. Don't blow on it.
Yeah, because you're gonna make it worse.
This is off topic, but are these slides on?
Yes, they say something like update or something, but they're there. Okay, so I'm doing 2 little single barbed arrows right here. See, oxygen, oxygen. Oxygen, oxygen, single bond is never stable. So that's called a peroxide. You can also have per acids. They're not stable. They can be explosive. I mean, this is not stable chemistry. So if you heat this, it'll split apart. If you shine light on it, it'll split apart. And that's nice because you can trigger the initiation by activating the initiator. And that was in one of the videos I showed you when we were looking at the PowerPoint slides. One of those companies that made one of the cartoons was a peroxide maker. So see how my little arrows only have 1 barb? So a bond always is the sharing of 2 electrons. So this is called homolytic cleavage. Homo, same. So it's an even split. Okay, so now I just need to write what I have left. Right? So I've got the ring, carbonyl, and oxygen with a radical. My reaction is not complete. What do I need? It's unbalanced.
You need 2 of these.
Right, I need 2 of these. So I could write this whole thing down again, or I can put a 2 in the front. Right? Because there's this half and that half. Okay, so this, unpaired electrons, highly reactive. Unpaired electrons are always highly reactive. So this unpaired electron is going to be like, hey, give me an electron. And 1 is going to come from this double bond. That is going to make a new bond. And then this one's going to go on to the last carbon. So now we've got that end group that's left over from the initiator, CH2, CH, side group, active site. There's my radical. Okay. This step is the initiation of the initiator, or the activation of the initiator. This is not initiation. This is getting the initiator in its active form. This step puts the active site on the first monomer. That is by definition the initiation step. Okay? Getting the active site on the very first monomer is the initiation step. Okay?
So when you have the lone electron on the carbon, you don't need like a fourth bond?
No, because you're showing that it has an unpaired electron.
Okay.
Okay? So if you don't have 4 bonds, you need a radical, a cation, or an anion. And you have to know what should be there. Because if it's got 2 electrons, it's an anion. Because carbon shouldn't have that many electrons. Does that make sense?
Yeah.
Did you have, okay.
Can we circle back? I kind of forgot. I need to think about the question I'm about to ask.
Oh, okay.
What are the arrows pointing to from the O and the double one on the H? Or like,
Oh, those are, so that is 1 electron from here and 1 electron from here is coming together to make this bond. Okay, so those 2 electrons come together. That's why it's just pointing into the empty space. Does that make sense?
I've thought about it.
Yeah.
So last time we saw this like weird little video where the smiley face is how like this. Is this what we're seeing here?
Yes. So this is the first frowning face. The initiator came. Here's the initiator, and now I'm happy face. So I've got an active site right here, and I'm the only one in the chain. So that's initiation.
And is it usually the case that the initiator would be like a completely different kind of
weird thing hanging off the end? Can be, doesn't have to be. Especially if it's an anionic initiation. It could be something more regular. The end groups, because polymers are so big, especially chain growth are so big, they don't matter.
could it ever bond to the other side with like the carbon H and R?
Yeah, that's sequence isomerism. It's not, you're going to see me always write it this way, okay? Because the side group usually is helping to stabilize the active site. So when we talked about sequence isomerism, we really just talked about size because we hadn't gotten into synthesis. But it's also because it's typically more stable when you're polymerizing that the active site be with the side group. Go ahead.
When we draw like the brackets, say this is a polymer, we draw it around the 2 C's and the H's and the R, right?
Mm-hmm. Yep. My handwriting's terrible. Yeah. So we really can't, there's no brackets yet because we only have 1, right? Okay. So I have this written on the top of the next page. And they're sticking. Before COVID, I used to lick my fingers all the time. Now I try not to. I hate it with plastic bags, right? Like trying to get the produce bag open. I really don't want to lick my fingers in the grocery store. Okay. All right, so here's what we made. This is the initiated. So we've got 1 repeat unit, right? 1 there. So it's the same reaction. This free radical is like, hey, give me an electron. So 1 goes from there. And so now we're going to form a new bond right there. And this one's going to go here. So I'm going to write defining that as R, because I don't want to, I can't define it as R. R prime. Okay, R prime. Oh, okay. CH with the R. This is what we started with, right? We got our new bond that we just formed. CH2, CH with the side group, and there is our radical. We did our first propagation step. And now the active site is moved to the end of the chain. It sees another monomer. It says, hey, give me an electron. It says, okay, gives you one electron from the double bond. The other electron from the double bond goes out onto the end of the chain. So now I have what was left from the initiator, CH2, CHR, CH2, CH side group, new bond formed right here, CH2, CH side group, active site. This active site can say, hey, give me an electron. It gives them an electron, and then the other one goes to recreate the active site on the very end. Do it 1,000 more times. You got a nice high molecular weight chain. Where are the active sites? Where the free radical is. Yeah. So the active site always moves to the end of the growing chain. So, easy enough. Yep.
Where is the R prime including just the double-bonded O, or is it also including the single-bonded?
Yeah, I didn't do it right. We need all of this. Here, I'll circle it. In the filled-in ones, it's got the whole thing written out. So. No. What you're going to be expected to do is if I give you this, I want you to say, oh, that's a free radical active site and that's propagation. Okay? And I want you to be able to recognize what it is, not do it. That makes sense to everybody? So 100% on the exam, I will have some of these reactions, maybe 3. And then you'll have a pull down that says what type is it, anionic, cationic, free radical, catalyst, or coordination. And then there'll be a second one with a pull down that will say initiation, propagation, termination. So people usually don't have a hard time with that. Yeah, this is complicated organic chemistry. You don't have to draw those arrows. Okay. Termination by combination. This one's easy. 2 radicals come together and they're like, hey, let's share.
That sounds like a healthy relationship.
Yeah. Or let's pair up, right? So that's when, right? We got an active site and we're gonna join two chains together. So what just happened on average to the molecular weight? Doubled. Yep. When we are calculating the number average degree of polymerization, it is important to realize that if we have termination by combination, we have to double it. Okay? So this is important to understand when we get back, right? So the active sites are the free radicals, and they come together and form a new bond. This is the easy one. What's now gone? Exactly right. So there are the free radicals are gone. The two chains have become one. There's no active site on a chain. Go ahead.
Are free radicals and active sites the same thing?
As I'm describing free radical polymerization, yes. But the active site could be an anion or it could be a cation. Okay?
Will we have to be able to distinguish between them?
Yes. You know the difference between a dot, a plus sign, and a minus sign?
Yeah. What, I feel like this is like kind of like a stupid question for at this point, but like, as someone who hasn't taken orgo, what defines a free radical?
Unpaired electron.
So why isn't that the minus?
Yeah, so there's no, if carbon had 2 electrons, it would have a minus sign because it would have an extra. In carbon's outer shell, it has 4 electrons. It's sharing one with the R group, it's sharing one with the chain, and one with the hydrogen, and now it has one sitting there. So it's not charged because it has 4 electrons in its outer orbital. How'd I do?
I liked it. I consider that like when you have an electron, like a little pair of something, that's always something with a charge. Because I consider like technically an electron is like one like radical or whatnot. It's like a half. But whenever I think of an electron, I think of always carrying a charge. Because whenever you're doing chemistry, it's always in pairs.
Yes.
You rarely do it individually, but
Yeah.
it does happen. It's just very
Free radical chemistry is really reactive.
Yeah.
And that's why you don't usually learn much about it in Orgo 1.
Yeah.
It's usually Orgo 2. Because it's not like when you're building up your organic chemistry, a lot of this doesn't fit the rules they're teaching you.
Yeah. Because most of the rules they teach you in Orgo is really like the first thing, and in chemistry in general, it's just positive, negative. You just know those. Radicals, they're going to toss that at you at like Orgo 2, like something harder.
Yeah. But we've got to learn it because it's super important for polymers, right? There's a lot of free radically produced polymers. And it's how polyethylene is still it's a commodity plastic. It's still, low density polyethylene is still produced free radically. So, disproportionation. Okay, I get this one wrong a lot, so let's find the filled in slide. So the filled in ones are like this, okay? So you can get all of these. Okay, so it would be better if I had written this one like over here, okay? Because what's going to happen is this radical is running into this hydrogen. And get a new color. Okay? So this hydrogen, this is the one in question. So this radical is like, it bumps into that hydrogen and says, "Oh, hey, I'll take, come on, we're going to make a bond." And so one electron, so this is a hydrogen atom, a proton and an electron. Usually we're talking about a proton leaving, right? We don't usually have a hydrogen atom that moves, but because this is radical chemistry, free radical chemistry, it's different. So when this hydrogen atom leaves, the other electron that was in this bond flips down here, which means now it can pair with this electron from the active site. Okay? So this hydrogen is moving here. The electron from this bond goes here. The other one goes there. So, got the chain. Got that CH2, CHR. This hydrogen is gone. So I've got CH. Now, there's my new bond. Okay? Because the active site electron and the one from this bond made the double bond. Plus, we've got another chain. We've got that hydrogen. It made a new bond with this. It's got a hard name and it's got a hard mechanism, okay? Disproportionation. Essentially, this is ripping an electron, this is ripping a hydrogen atom off, but it's only one carbon in, and so it can make this double bond. And that's how the chains terminate. That's how this ends up and this ends up with no radicals. This one's harder. But if you start with active sites and end with no active sites, it's termination, right? That's what you've got to be able to do. But this, where the active site on one chain is ripping a hydrogen atom off of a carbon on the other chain, if it doesn't happen on the second carbon, it's going to do it's going to do branching. Long chain branching, which I'm going to show you in, I think, 2 slides. Go ahead.
So if it's not changed, you can just like put the chain, we don't have to like finish writing.
Yeah, just mimic whatever's done up here, you know. But you're never going to have to probably write this out. So, but yeah, it's just sort of like, it's showing you, I'm just trying to highlight the rest of the chain. You could do like brackets and, you know, but I like this because it's really just showing me, oh, I'm just looking at the end of the chain. Mm-hmm.
Is there any specific reason a reaction like determined by combination for this proportionation, like one or the other? Like, can you choose, or does it just happen?
You know, I don't know. I think it's like a statistical thing. It depends on the rate of this reaction versus the rate of this reaction, what the rate constants are. And it probably really matters like how easy it is to rip this hydrogen off. But yeah. Well, you're making the same polymer, but this one is doubling in molecular weight and this one is not. And this is one of the reasons. If you want a lot of control and you need specific molecular weight and stuff like that, you're going to try and not use free radical polymerization. Although, we're not going to cover it in this class. I'm talking about it in my PhD level class right now. There are ways to do, it's more modern. There are ways to control free radical polymerizations a great deal. But it really only was developed about 20 years ago, and I assume it's been commercialized by now, but I guess I don't really know that.
Is free radical polymerization a hot reaction? Like when you're making plastics and stuff, is it really heat intensive?
Yeah. It is exothermic. I don't want to say always, but I believe it is usually exothermic. It's usually done at high pressure, so that you have a higher concentration, because like these monomers are typically gases. So if you want a higher concentration, you increase the pressure, right? And like these reactions can run away from one another because, well, we'll talk about it during kinetics, but that's how the ICI guys blew up their lab, right? The reaction it went so fast it was out of control, and their pressure relief valve failed. So, chain transfer is essentially disproportionation, but we've got something that's willing to give up a hydrogen atom. Those of you who are in organic, it's often a thiol. Okay? The rest of you don't have to listen to that. Okay? It's often a thiol. So this can be, so the chain transfer general reaction, this could be another chain. It could be what we just saw here. It could be a chain transfer agent. It could be you are putting something in there to control this, so that how you're going to help control the molecular weight and that kind of thing. So it's nice to just know the general reaction, and that's essentially what we just looked at. This free radical says, hey, I want that hydrogen atom, and then this is going to become the radical. So we've got our chain, CH2, CHR. We've got our new bond and the hydrogen from the chain transfer agent. Plus, now we have whatever our chain transfer agent was, or the other part of the chain, or whatever it is, it has the radical. If this radical is relatively stable, is stable in terms of radicals, it might not be able to initiate a monomer. And then you're controlling the reaction. Okay? If it can initiate a monomer, then you've just limited the molecular weight of this chain, right? And this is going to start and polymerize another chain. Or if this is another chain, it's going to make a branch. There's lots of options. So we think of chain transfer as a side reaction, but it can be something that you are using to your own benefit. Okay? It doesn't have to be, side reactions don't have to be a bad thing if you're using them, if you know what they are and you're using them to your advantage. Okay? Okay. Short chain branching. This is an intramolecular reaction. Intra, what word do you know with that prefix?
Multiple.
Sports. Intramural. Intramural is within, right? Within NC State. So an intramolecular reaction is within the molecule. There's no other molecule. Okay? Intra.
Where is this in the slides?
Say it again.
Where is this in the slides?
Oh, it's in Module 6 in the second Moodle section. I think it's the second or third thing in the list.
No, I have it open.
Oh.
It's not in the slideshow.
Oh, it's in the filled in. It should be in the filled in. Or that's why I wrote I needed to update it. This is in Coleman and Painter. This is in Painter's ebook too. This is his figure. So the end of the chain. So if we're talking about intramolecular, what do you think the concentration of polymer chains is? Is it high or relatively low? If the end of the chain is more likely to run into itself than to run into another chain. Yeah. So the chain concentration is relatively low. Oh, it's written right there. Oh, okay. All right. So this is the dog chasing its tail. Okay? It wraps around, and this is called backbiting. That's what this is called, backbiting. It has wrapped around, and it's bitten its own hydrogen atom off the end, off the, a few carbons back. And it's usually sort of, see how this ring is sort of working, like looks sort of like a benzene ring? Carbon likes these 6-membered rings. It's the bonding angles make sense. There's no ring strain. So it's usually, this backbiting reaction usually happens where you end up with a branch with 1, 2, 3, 4, 5, or 6, or 7, but it's short. So this hydrogen transfers to the end. Now we have a CH3, but the radical is 1, 2, 3, 4 carbons. It's on the 5th carbon back. So if I just take this molecule and rewrite it, here's my branch, there's my new hydrogen, there's my branch, and it can polymerize off of this active site. Make sense? So this is how you get short chain branching. This is very common in polyethylene. These branching reactions are super common in polyethylene, and low density polyethylene has these. Okay? As the reaction, as you produce more polymer, you can have an intermolecular interaction, like interstate, right? We're going from state to state. So it's from molecule to molecule. But it's not just finding the end, right? If it finds the end of another chain, if 2 chain ends find each other, then we've got combination or disproportionation. We've got a termination mechanism. Here, this one runs into the side of another chain, and it's like, I'm stealing that hydrogen atom. This is from Coleman and Painter, and they don't do their arrows right. Anyway, but he's just showing the whole hydrogen atom is moving. So now you have the active site here. This chain is dead. Here's the active site, and it's in the middle of the chain, but it can polymerize. This radical can add, and so now you're going to have long chain branching. Because you got a long chain here, a long chain there, and you're growing one somewhere in the middle. Make sense? Okay. So I always show this. One, because it's important to understand, I think, why polypropylene doesn't polymerize free radically. Polypropylene, you cannot polymerize free radically because it's an alpha olefin. So let's say we've got the radical on the polypropylene. What's going to happen is it's going to say, hey, give me a hydrogen atom on the methyl group, not up here. And then that is going to, it's going on to this carbon. I messed it up, sort of. Okay? So this is going to grab the hydrogen atom, and then the other electron is going to go onto this carbon. So now we have the active site right here. Got the active site right here on the monomer, but it's not across the double bond. And we've got the new bond and the hydrogen This hydrogen is right here. Okay? This monomer with the radical there is very stable because it's resonance stabilized. That radical can flip here and move. So that radical is resonance stabilized. That radical is sort of smeared out across 3 carbons. So this is much more stable of a radical than an ethylene radical. That makes sense? So if your radical is stabilized, it's not going to want to polymerize the way it should. So the big takeaway here, polyethylene cannot polymerize free radically. And it's more general than that. No alpha olefin can polymerize free radically. This is called an allyl radical or an allylic radical. I'm not going to ask you that. You don't have to remember that name, but so you've heard it before. It's an allyl radical or an allylic radical, and they're not going to polymerize. This is called inhibition. Okay? So this radical is just going to terminate. It's going to combine. If you get one that did add across the double bond, it's going to combine really quickly with this one. And there's the rate of chain transfer is faster. This is faster than adding a monomer the proper way. So you're never going to get polymerization. This is why kinetics can be really important to understand. Because if this happens faster than propagation, there's no polymer. Make sense to everybody? Okay. So it also will it will combine with itself. Then you've got this. So if you start to polymerize, you end up with something like this. If it just finds itself, it ends up like something like this, but you never get propagation. It's the polymerization is inhibited. Okay? So, how do we define an alpha olefin? If we have a CH2 alpha, meaning next to the double bond. So for propylene, R is a hydrogen, but it doesn't have to be. Any CH2 next to the double bond cannot polymerize free radically. That's why Ziegler and Nada fought, and the patent wars were so intense and all of that. Okay? That's free radical polymerization. Okay? That is the hardest one. You ready to look at anionic?
Why is it considered next to the double bond if it's bonded to two singles? Is it just like in the actual molecule it would be?
So it's not this carbon, because that one's participating in the double bond. It's alpha. It's next to the carbon that's participating in the double bond. So anionic polymerization. Look at that overall reaction. Everybody can do that, right? Double bond, pop it open to make the wraparound. No problem. So I've got CH2, CH, side group. I used a different letter for the side group. Often, most things, if they polymerize free radically, they don't polymerize anionically and they don't polymerize cationically. Usually, if one monomer goes one way, it doesn't go another way. And I sort of misspoke there. So if it polymerizes anionically, it usually won't polymerize cationically. And then it may or may not polymerize free radically. So, and then what did I forget? My wraparound bond, parentheses, number of repeat units. Overall reaction is the same no matter what the mechanism is. So, overall reaction, no big deal, right? Anionic polymerization. We've got to have an anionic initiator. It's almost always going to be something that's charged. See that minus sign? Okay. So, the way this is going to work is instead of having a free radical, an unpaired electron, attack the monomer and flip an unpaired electron on, what we're going to do is we're going to have something that has a lone pair that it wants to share really badly. Okay? So nitrogen likes to have one lone pair, not two, because it doesn't like to have a full negative charge. Which if it has two lone pairs, nitrogen, it means that it's got a full negative charge. Because you can start to think about this in terms of why nitrogen wants 3 bonds, right? We keep saying that. If nitrogen wants 3 bonds, that means it has three electrons it wants to share and 1 pair. Oxygen wants 2 bonds. So that means it has 2 electrons it wants to share to make bonds and 2 lone pairs. Makes sense? Right? So this one of the lone pairs from this sodium amide is going to go and attack the carbon. Now, see double barbed arrow. Now, both electrons from the double bond are going to flip to the end carbon. So, I've got NH2, my new bond, CH2, CH with the side group. I have a full net negative charge. What did I forget? What? No, I've only added 1 monomer. Yeah, the Na plus, right? So that's the counter ion. So if I add up all the charges on this side, it sums to 0. Negative plus equals 0. I cannot create a charge, right? So I have to have that counter ion. Na plus. So this and that sum to 0. It's just like you can't magically add a hydrogen atom. You can't, right? If it's a balanced chemical equation, if you have 0 net negative charge across the whole thing on the left-hand side, it has to be the same on the right-hand side. So this is initiation, right? I'm getting the active site on the first monomer. Now I have this on the top of the next page because I'm going to add a monomer to that. Oh, look, I have a blank page. This is when the kitten decided that no paper should leave the printer. You can see it all got jammed up. Go ahead.
What's the difference between having a negative sign and just an extra electron like we had in the last?
So it's really about the sort of the Lewis dot structures. So if we have carbon, carbon has, in its outer shell, it has 4 electrons. And they hybridize to all be the same, which, right? So it has 4 electrons. it wants, everything wants 8, right? The octet rule. So if it shares with the hydrogen atom, those are paired. It can take this one and do this. Okay, so I've got a double bond. And so if my, I'm going to write FP for FR, there's my free radical, okay? It says I'm going to share this electron. So one of these is going to go here. The other one is going to go here, okay? So if I get rid of this, I get rid of that. So now this carbon is a free radical. And this is bonded. No, we got the free radical initiator, okay? It's there. So now that's bonded. Okay. So this, there's no charge. One electron, the free radical ended up here. Let's reset it to back to polyethylene. Okay. It doesn't polymerize anionically, so let's make this an R group or an X or whatever. Okay. So now I'll get another color. So the initiator we have on the screen, I've got and a net negative charge. It does not want to have 2 lone pairs. It only wants to have 1 lone pair. So now this time, the whole 2 lone pairs are going to be like, hey, let's share. Which means both of these go here. So this negative charge goes away. Well, oh, I guess I just erased this. All right, so it's now sharing its 2 lone pairs. It's got NH2. Or it's sharing 2 electrons from there. These 2 have moved here. So I erase those and I move them here. So carbon has 1, 2, 3, 4, 5 electrons that it's not shared, right? It's getting, then it's got those 2. So it has to have the negative charge. And it can go, when we look at cationic, it's going the other way. The 2 electrons from the double bond are going to the cation. So it's all about like what did it start with and what does it end up. So the free radical has no charge because carbon still has 4, but now it has 5 electrons. Does that make sense? You thought Lewis dot structures were never going to be useful when you learned them in freshman chemistry. They are useful. They're very useful, actually. Okay. So this is 2 electrons, the negative charge. It's going to attack that. It's going to put the 2 electrons from that double bond onto that carbon. Then we got to write what's left from the initiator, CH2, CH side group, that's right there. The new bond, CH2, CH with the side group, and the negative charge. And I can't forget my counter ion. So this is propagation because we are adding a repeat unit and getting the active site. The active site is moving to the end of the chain. We're adding a monomer and moving the active site to the end of the growing chain. The biggest mistake people make when I ask them what type of, initiation, propagation, termination, and then anionic, cationic, free radical coordination. Biggest mistake people do is they look at the counter ion and say that this is cationic instead of anionic. So you got to look at what's the active site on the chain. Okay. So then we can add another one, and we can add another one, and it's just going to keep propagating, which I did right here. Mm-hmm.
What is that sodium doing?
You really can't have. You always have to have a balance to your charge. So it's just it's the counter ion. It's the balance to the negative charge.
So you just put it in the formula just to balance it out.
Well, so it's like sodium chloride. So it's ionically bound to this. It's not covalently bound. Does that make sense? So I could just write it without the charges and have it be a sodium on the end. But if it's in solution or something like that, it's going to fall apart, right? Because it's an ionic bond and not a covalent bond. And carbon doesn't want to have ionic bonds. So it's going to be so loosely affiliated. That's why you sort of just write it as sitting nearby. Yeah. It's near. It's like you're still connected to a former friend that you can't quite get rid of them. Like maybe it's your roommate that now you hate. They used to be buddies, but now you hate them. So they're always around. Okay. So why can't we have termination by combination?
Because unlike normal math, you can't add two negatives to your positive. No, you can't add two negatives to your positive.
Yes. If I have two, it means I have two carbons, right? There's my, so I'm going to have 4 electrons. So then I'd be making a double bond, and it's already bonded to 3 other things. So it just doesn't work. And besides that, there's a simple phrase. Like charges repel. Right? Like dissolves like charges repel, right? So there is no chain transfer by combination. There is no disproportionation because it doesn't want a hydrogen atom. It only wants a proton. Anionic polymerizations will terminate with any proton donor. So you can't do them in the atmosphere because there's moisture in the atmosphere.
Oh, so it would just
Grab the proton from water. Mm-hmm. Yep. So what happens? The negative charge says, hey, I want a proton. And this proton's going to be like, okay. And then the 2 charges go back onto the nitrogen. Because that carbon wants the proton way more than that nitrogen does. So we've got CH2, CH with the side group. We got the new bond with the new proton. So now this is neutral. This was neutral, this was charged. Now, we still have our sodium plus, and we have N H2 minus. Anybody remember what the initiator was?
You get the initiator back.
We got the initiator back. This can go on and initiate another monomer. Any proton donor will do. Carbanions, you guys have heard that word before, I think, right? Carbanions are not stable. Carbon does not want a net negative charge. It also does not want a net positive charge. Remember carbocation? You guys have heard that word too. Yeah, carbon's not happy with the charge. It wants to get rid of it. Did you have a question? Yeah.
Yeah, this is not this, but I just remembered. So it's kind of left field. Are we gonna go over the homework?
We're gonna see what time we have. So it's looking like no, but the video is available to you. Okay. Okay. So essentially, this is, you can think of this as any proton donor, you can think of it as a chain transfer agent. And so you're terminating through chain transfer for most for ionic polymerizations. Living polymerizations are really neat. This is straight from Macrogalleria. So chains that don't die. So what's neat about this is you have this reaction in a stable environment, and the reaction is stable enough that you can polymerize until all the monomer is gone. If you did that with a free radical polymerization, there'd be so many crazy side reactions, and there's just no way you could do that. So this living polymerization is really cool. So we've got our initiator. We start polymerizing, and you polymerize until all the styrene is gone. You still have an active site on the end of the chain. So now you chuck in a new polymer. I don't know why they don't have double bonds. Okay, you chuck in your new polymer, and it starts polymerizing. And you polymerize that till it's gone. And in this case, you want styrene, butadiene, styrene, but because the butadiene is more stable than the styrene anion, it won't start it. But now you just throw in a coupling agent, and now you've got your styrene, butadiene, styrene, which is called SBS rubber. And it's another rubber that's not covalently cross-linked. It's used in shoes and a lot of applications where you need a tougher rubber. So, living polymerizations are the best way to make block copolymers for di-block, tri-block. Multi-block copolymers you're usually doing through step growth. It's a different type. This is pretty neat. You can start to think about different types of initiators. So you can initiate anionic polymerizations with sodium metal. Sodium metal is it's a really neat metal. It gets deactivated in the atmosphere, so it's like not really safe to have open in the atmosphere, exposed to moisture and stuff, but it also gets like a coating, a passivization layer. But if you've got it in an inert atmosphere, you can take a spatula and scoop out sodium. Like, it's a metal, but it's so malleable that you can scoop it with by hand with a metal tool. So it's pretty neat. And then, well, especially in light of it's Halloween. So when I was an undergraduate, there was a dorm at that would always manage to usually buy silicone. It comes in a metal can. It's all sealed up and stuff. And it's in a kilo or 5 kilo cylinder. I think it's 5 kilos. Anyway, it's about like this big. This dorm would always used to have what they called the sodium drop party, and they would liberate sodium from a lab or somehow finagle ordering it, doing something. And so what they would do is they would put it in a really big can and put all these holes in the can and drop it off the Longfellow Bridge into the Charles River. This is not safe. You should not do these things. But yeah, it goes, right? And sometimes you can see some of the colors because when sodium burns, it's green. So sometimes you can see the colors, and you have to make sure that there's no one boating down below and that kind of thing. But
reminds me of, I was reading on someone said they accidentally made, I think it was chlorine gas.
Yeah, that's easy to do.
Yeah, it's got his hands on, I think it's Fritz Haber's notebook. He's the guy who
the Haber.
Quite a few very useful farming methods, but also got the very unfortunate title of Father of Chemical Warfare.
Yeah. But you can people unintentionally make chlorine gas all the time, and if with just household products. So if you take bleach and you mix it with certain cleaners, you'll release hydrogen gas and chlorine gas. It's really bad. But when it's most common is when people are they think, oh, I want to really clean my cat box. I want to sterilize it. I'm going to bleach it. It combines the active ingredient, why am I drawing a blank on the name of it? That's in bleach combines with the urea from the cat urine, and it releases chlorine gas. People have hurt themselves doing this. It's a bad thing. So if you ever smell that pool smell, and you've done something, you've combined some things at home, just leave. Get out of the house. Leave the room. Get your pets. Just, your roommate, get out of the house. Because we all really know what chlorine smells like. And if you get more than sort of what's coming off a pool, it'll start to burn the inside of your nose. And you need to get out. Get out. And you shouldn't actually go for your pets. What you should do is get out, leave the door open, and call them. Because they're smart and they smell better. They have a better sense of smell than you do. They will get out on their own. So, oh look, this is, I remade this anyway. So you get this sodium metal makes this. If you use sodium metal with styrene monomer, you get this. It's going to grow in 2 directions because it's got 2 active sites. So it grows in 2 directions. So it grows twice as fast because you're using a different initiator, which is sort of cool, which is how I got off track with the sodium party and everything. So this is going to grow really fast, but you can have different shapes. You could have, like if you wanted to make a star polymer, you could have a central core with 3 spokes. 3 negative charges, or 4, right? Or 5. And grow from that central core and make what we call a star polymer. Where here, if you only have 2, it's just going to grow twice as fast. So we are running out of time. So cationic polymerization is essentially all we do is turn the arrows around from anionic polymerization. It's pretty straightforward. So we are going to finish up, and we'll do our last quiz on Thursday. So I think you guys are getting what you want. We're gonna delay the exam a little bit longer than I had planned to. Yeah, we can make it open over the weekend for sure. So, and I'll make sure to get the updated lecture. So you're saying these aren't the same ones, so I'll make sure I get the new ones posted. And I found some things I need to fix in it too. So we'll see you Thursday. There is a quiz we'll do on Thursday. It's right here. And then, yeah, we'll review after we do the quiz. Okay. So we have to finish cationic polymerization. We're gonna finish our new stuff. Then we're gonna talk about everything else and review. Okay? So cationic polymerization. Overall reaction. We know that one, right? We got that one down? Yeah. Double bond. Pop it open. Make it the wraparound bond. So we've got CH2, CH, and a side group. Make the wraparound bond. Add the parentheses. Number of repeat units. Okay. Overall reaction. Anionic, cationic, free radical. Even catalyst. Same overall reaction. Okay. Now, cationic polymerization. We need a proton donor. We need a good proton donor. Okay. We need a proton donor that's strong enough that the 2 electrons from the double bond are going to be like, ooh, I'll take that proton. And then we make a carbocation on the other carbon. Okay? So the 2 electrons from the double bond go and say, oh, yeah, I'll take that. That means that this carbon has a positive charge, because it's down an electron. So this whole big thing is our counterion. All right. So let's make this proton. That's going to be green. Okay. So there's our new proton. There's our new bond to our monomer, CH2, CH with the side group, and it has a positive charge because both electrons from the double bond grab the proton. Okay, both of them. Then all we're missing is our counterion. Okay, so that whole thing is the counterion. I just rewrote it over there. So again, how do we define initiation? This step is initiation, but how do we define it?
Initiation isn't the second part of that step where it actually starts polymerizing?
When it's polymerizing, it's propagation. One of you? Hmm? It's a carbocation. That carbon has a plus charge. When you get the active site on the first monomer, that's the definition of initiation. Not so important to us right now, but that's what's important when we do kinetics. So might as well get it down now. Okay. So now let's look at propagation. Essentially the same thing. That carbocation, not very stable. This is not stable. Carbon does not like to be a carbanion or a carbocation. Doesn't like it. So, what's going to happen? This is like, I need some electron density. So the two electrons from that double bond are going to form a new bond here. They're going to share their electrons with this carbocation. So we've got the part we already had, the first monomer. Okay, then we have the new bond. It's attached to the second monomer. Yes. No, it's supposed to be a Y. I even wrote it there. Yep. I'm trying to show, I started with R, then I did X, and now I've done Y, because usually the side group is not the same for free radical, cation, anion. Okay. Okay. Where's the new bond? Should be easy. Yeah. There's the new bond, right? I guess it doesn't show up. The colors don't show up so much. It's supposed to be pink. Okay. What's the active site? The carbocation is the active site. And what is wrong with my equation, my chemical reaction? Yeah, missing the counterion. Okay. Then we can just do it again and again and again. Right? So this right here can react with another monomer, and it can do it again, and it can do it again. Same reaction over and over and over. Oh, that's weird. This one's all filled out. So chain transfer and termination, any lone pair donor, Just like with anionic polymerization, any proton donor, doesn't care, not picky, because carbanions and carbocations are super reactive. So they'll take any lone pair or any proton, okay? So if this gets exposed to water, that means you can have an OH minus, that's going to react, right? And then we're going to have the terminated group. Oh, I guess I didn't quite fill it out, right? This is going to go and attack that. CH2, CH with a Y, OH. Oh. We've got another anionic polymerization. How come we can't do termination by combination? Yes. Like charges repel. All right. So that is our polymerization mechanisms. Okay? But we're going to learn one more thing that I, for sure, will ask you some low point value questions on in the exam. Okay? If I have an electron withdrawing side group, it likes electron density more than carbon. It pulls some electron density towards itself. Is that going to facilitate anionic or cationic polymerization? Whoever answered, thank you for answering. You're saying cationic? So remember, yeah, yes, but so remember, if we have a carbocations and carbanions, incredibly reactive. The way to stabilize them is either to give them a little electron density if it's a carbocation, or pull some away if it's a carbanion. So if we're going to have a negative charge here, do we want this to be a withdrawing group or a donating group? Electron density withdrawing or donating? If this is going to be a carbanion. If we're gonna have minus, right? Do we want to pull some of that minus charge away to the side group or push more minus charge, make it even more negative? Pull it away. Pull it away. So this is going to facilitate anionic. I don't know why I always dot a capital I. Anionic polymerization. Does that make sense? It's seeming like we weren't quite there.
It just seems like if you're pushing more electrons to it, it would get more negative, wouldn't it?
It would get more negative, more unstable. Yeah. So that's the thing, okay? Carbanions and carbocations, we don't want them more reactive. They're already like over the top, unstable, reactive. So we're trying to stabilize them so they will react with a monomer and not anything, like not whatever it comes in contact with. So if we have an anionic polymerization, it's going to get stabilized by having an electron withdrawing group to try and pull some of that electron density away from the anion, from the carbanion, and into the side group. That will help stabilize the carbanion and make it stable enough to polymerize.
So you show the partial positive and partial negative there. Does that mean that carbon is partial positive?
Yeah, so it's a little bit electropositive. And this is going to be electronegative. So yes, so when it becomes an anion, instead of like a full net negative charge sitting on that carbon, it's going to be a little less. So right now, this carbon is a little electropositive, but once it gets the active site on it, it's got a full net negative charge. But if this side group can now pull some of that electron density away, this is going to be a little less than a full net negative charge. Some of you are not buying it.
It works because it's anionic because it's negative, like naming-wise, and then it's getting more negative because you're giving it more electrons.
If we did that, it would probably be too unstable to polymerize. So we need to pull some electron density away so that this carbon is now stable enough with the negative charge that it can actually polymerize.
How do we know that the side group is going to be withdrawing?
So that's something you learn in organic chemistry, and I'm not going to ask you about that.
Okay, so I just have to remember this.
Yeah.
Know the difference between knowing the withdrawing groups and the donating groups. I hate it. It's very complicated. It's like very simple once you learn it, but it's like also finicky because they'll throw you questions of like, you have these two different functional groups. Is it going to do this or that? And it's annoying.
It's the basics are pretty straightforward. Things that really like electrons are going to pull electron density away, like fluorine, chlorine, bromine, right? the halogens. They like the electron density more than carbon does, so they pull it towards themselves. It's hard when it's carbon-carbon, and like carbon's a weird carbon because it's like a carbonyl, or it's a this or it's a that. Then you have to know a lot more organic. Usually, like a methyl group is sort of pushing, right? If it's just a saturated carbon, it's like, yeah, you can have some electron density. I don't care about it. But.
And how does the electron density translate into the charge?
So a charge, a charge is just, you have one electron worth of electron density. That's a charge.
Oh, so it's not like a whole electron.
No.
It's like partial electron. Okay.
Mm-hmm. So you're just pulling some of the electron density away, not a lot.
You know that little like S symbol thing that's on there? That signifies partial. So when it's a partially negative, there's like a part like S with a negative.
It's a delta.
Yeah.
Partial.
So that just means partial. So whenever you see those symbols, it's just saying, oh, it's partially going to be like this. And typically there's an arrow pointing to a different direction, going from positive to negative.
So this, because the arrows always go the way the electrons flow, always. So when this carbon has a full net negative charge on it, it's a little less because of this delta plus. Just a little less. That helps stabilize it. So then, the opposite is true, right? We got an electron donating group. It's going to facilitate cationic. Here, I'll put the nice one up. Okay? Cationic. It helps stabilize the active site by pushing some electron density up to it. So it's a little less than a full plus charge. So you can try it. So I wonder if I can find this online somewhere, because chemists will make electron density maps. And so then you can see sort of like the electron density pulls a little bit away from the carbon. And then you can push a little electron density up towards the carbon that we're concerned about, okay? But this is why I used X, Y, and R. Tried to use 3 different variables for the side groups, because usually they're not the same. I'll give you an example where there's one monomer I know off the top of my head that can polymerize all 3 ways.
I have an example of the maps like right here. It's the one with the colors and everything.
Yeah. Yeah, I want to find it specifically for the, but
I don't know what it's called, like the actual name of the map.
Electron density maps usually. But, well, so if I have styrene, I can polymerize it anyway, because that ring is resonance stabilized, right? And we've probably never thought about it. Why do I always write this like that? Yeah, because these two are exactly the same. A double bond is shorter than a single bond, but in benzene, or the phenyl ring, attached to something, all the bonds are the same length. If you look at electron density map here, the electrons are they're equally shared among all 6 carbons. So if this is attached right here, this ring can take some extra electron density in and smear it out over 6 carbons. It can send some electron density the other way. And it polymerizes free radically, which is a little different. But, so the styrene is a weird one, because you can do it any which way. Okay. There ends our new content. So I was So close to finishing on Tuesday. So close. So, I can try and get the exam out tomorrow so that you have it over the weekend. And we can have it open. We can like have it Friday to Wednesday or something like that. Or I can open it on Wednesday and have it open next weekend. I see lots of nodding heads. But we have to continue with new material. We can't, it's like, I don't have the history of polymer science lecture to throw in so that we're not learning new material while we're waiting for the exam to open. We have to get done with kinetics before Thanksgiving. Thank you. I'm like, what is the words are escaping me. So it means that we'll have the next two exams very close together, but if you'd rather have it open not this weekend but the following weekend, do we want to vote, or is everybody sort of down with postpone? Is that what we want to do? Yeah.
I just have a question.
Mm-hmm.
Is the kinetics exam going to be over Thanksgiving, or is it going to be before?
I want it to be before, but it might, like maybe we'll have it end on Wednesday of Thanksgiving week or something. No, I don't want you doing an exam Thanksgiving weekend. So, okay, well, that gives me a little more time too. Okay, so the next thing we need to do is we need to do our last chain growth quiz. And I will point out, we did more quizzes and more homework in step growth because people need more practice in step growth in my experience teaching this class, where we're just doing quizzes in chain growth because that's really all you guys typically need. If you need anything else, just reach out. Go ahead.
So just to clarify, you said next Wednesday into the weekend, next weekend?
Yep, till Sunday. I like to have it open for 5 days over a weekend. So we'll do Wednesday to Sunday night. Okay, so let's okay, so I got a 2-page exam.
Are you passing them out?
No, because I was like, we don't need to run this through the printer, and because you're gonna have like 6 words on a piece of paper is what you're gonna end up submitting. And if anybody needs some paper, I got paper. Okay, so we got 3 or 4 of these. What type of polymerization is shown? Meaning, is it anionic, cationic, free radical, or coordination? And is it showing initiation, propagation, or termination? Or is there a branching reaction? Okay. So, this complicated one on the screen is it's complicated, but you're still gonna you just need 2 words to answer it.
Or 3.
Yeah. And I mean, you literally can write this anywhere and submit it. Scrap paper, it doesn't matter. Okay, so let's answer this one before we go through and we go to the next page. What type of polymerization is it? Free radical. That screen is not on, is it? Okay, it's free radical. What type? What step is it? It is termination. Anybody remember the big word that's hard to say? Disproportionation. Yeah. Perfect. Okay. Because see, it's grabbing this proton. I mean, this hydrogen atom. It's grabbing that hydrogen atom. You get two free radicals that collapse down. Okay. So we got 3 right here. Okay. Looks like probably half of you were ready to talk about it. So we'll just get started here. Okay, so what type of polymerization is the top one? Anionic. That is correct. What do you think the most common mistake is when I ask a question like this? They think it's cationic because of the counterion. Because the counterion's positive.
Okay, so if it's positive, it's anionic, and if it's negative, it's cationic.
Right. The counterion is always the opposite of the type of polymerization.
Oh.
Because the active site is what we're talking about.
That makes sense.
Yep. The active site. So then what step is this one? Propagation. Mm-hmm. What about the second? What the middle one? What type is that one? Cationic. That one's sort of easier because there's no counterion written down. Okay, what step is that one? Propagation. How do we know that those two are propagation?
Because they already have it when it's there, and at the end they still have the ion, the charge.
Yeah. So there's an active site on what was a monomer on the left-hand side, and there's an active site on the new monomer that just added, right? So the active site is on both sides of the reaction, so it's not termination, and we're not creating the first active site, or the active site on the first monomer. So it's got to be propagation. We're just adding a monomer and moving that active site to the end of the chain. Okay. So what about the third one? Cationic.
Initiation.
And it's initiation. Because we have A plus is the initiator, and we're getting that charge on the very first monomer. We're getting that carbocation on the first monomer. Okay. So the people usually do well on these. Step growth. Where is O? Everybody uses their phone. I have this silly little security key.
Oh wait, how? Do you just get to click a button instead of using your phone?
Yeah.
I'm sorry.
When your phone, I had my phone go dead, and one day, and I had to get in, and if for class, I couldn't buy it. It was anyway. That's when I switched to these. It's a little USB, and it's amazing because I've carried it in my pocket for 5 years, I think, and I just push the little button. And it's in with my keys. It's not,
Yeah.
And
It
it's like
doesn't even
80
work.
second
I
that
need a
day.
password.
Yeah.
It's like
And
flash.
it-
Yeah.
like,
I got a
it's
new
me.
phone and then like
Who else?
just could not
It's like, it's better than it used to be. Every single time they log on. It's not once a week, it's every single time.
Just do it for you once a week. Is that like what it is?
Oh.
Yeah, you know, there's just some time of doing.
It hasn't been the same.
I had dropped
But I mean, like,
had
it's
that
after you
phone
pass the
before,
1
so
week
I had
line,
dropped
that's
so
when
many times and finally just get
No, I got more than
okay, so let's go to module 5. So I'm viewing as a student. I'm in the step growth synthesis. Okay, in Moodle in the step growth synthesis. So, yeah, you guys don't need to watch these because you come to class. But the fill in the blank slides, these are all up. That's updated. These are just little videos from the web that are extra for polyester synthesis, and these are nicely done. So, so if you want, like the lecture videos are long, where these are nice and short and to the point, and you can pinpoint exactly what you want. And then here's polyamide.
Will synthesis of nylon 6,6 be on the, like, is that valid content for the test?
Oh yeah, but you wouldn't have to name it,
Oh,
right? You know,
because it's only the esters and amines.
right? But nylon 6,6 is an amide.
Yeah, yeah.
Mm-hmm. So then I've got all kinds of stuff for review because there's a lot of stuff for review because this is where students struggle, okay? So module 5, module 7, this is where people struggle. Module 7's next week, so we don't have to worry too much about that, okay? So let's look at this table, maybe. So here's polyester. Okay, we can have an AB type, and when that polymerizes, there's the polymer and there's the small molecule byproduct. We can do AABB, and we learn 2 reactions, the diol with a diacid or with a diacid chloride. You get the same polymer if the middle parts are the same. You have a different small molecule byproduct. So I set up this table to prove that there's not that many reactions that we have covered that I expect you to be able to complete for the exam. Okay? Is it looking manageable now that you see it? It's not so many. And they're very similar. Okay? If you look at the polyesters and you take away the alcohols and make an amine, all you have to do is take away the O from the ester and make it an NH to be in the amides, right? They're directly analogous. And then here are review questions. If you can do these, you are going to do well on the exam. Okay? And then if we go back,
And then I switched to Liberty Mutual and saved hundreds. I know, exactly.
it annoys me to no end that NC State has a contract with Google and then these ads.
Hello, everybody. I realized yesterday when we reviewed.
These are the 3 that are right here.
Where did you find the table again?
Right here. Module 6, the first thing under materials for reference and review. That's the table. And then this is polyester, which goes through the top 3 things on the table. And this is polyamide, which goes through the second 3 things on the second half of the table, the polyamides on the table. this is a flow chart that I tried to do out my thought process, and it's a boring flow chart. There's no colors or anything, but I think it's effective. So if I ask you what monomer or monomers was this polymer made from, and you have the structure of the polymer, first thing I'm going to do, is it an all-carbon backbone? No, probably step growth. Yes, probably chain growth. And then go from there. So, you can take a look at that one. This is a review video. The polymer, monomers, could it have been made, given a polymer, what monomers could it be made from? Oh, these are the PowerPoint slides. I thought I updated those. And there's the DocCam slides, that's the same as right here, the DocCam. So those are in two places. And then we had the step growth quiz. Oh, that's the weird problem set. You probably don't need to look at that one again. We only turned in problem 9, remember? I don't know why there's 2 videos. Okay, then there was the quiz. You can watch the solution to the quiz. Then there was the problem set. And because we were so far behind, we didn't go through the solutions, but you can watch the full video right here, okay? I can't because I'm set up as a student and I didn't turn in my homework. So, and then there's the last one, the last quiz, and you can watch the solutions. So you have all of the solutions, but start here, okay? The chain growth, we just finished the chain growth, module 6. This one, I know the slides have not been updated. So we've got the introductory, this is what we covered in lecture. These are the short videos that we watched, and then some additional ones. But we watched these in class. There's the little happy, sad face guy, right? With his little arms, okay? And then we have the 2 quizzes. I know I've been a little, quick and, on the chain growth, but you guys, students historically have always done really well on the chain growth, and I don't expect it to be any different for you guys, okay? Especially you that come to class. So it's a lot less material than was on the first exam. It's focused, it's just synthesis. And then I can't remember, I think I started getting the exam part going. All right, I'll get that updated. So there are the checklist for the 2. Okay, so I will do an exam template again, but it's not available yet. I was looking at it. I couldn't remember if I'd posted it or not. Go ahead.
Is there parts that we need to upload our work?
Yes. This exam will be in 2 parts, just A and B. A will be short answer, maybe type an answer, select a choice. So like the quiz today, it'll be 2 drop downs or 2 multiple choice. It was it was free radical anionic, like that. So so that'll all be in part A. You might have a short answer in part A. Part B will be questions that say, complete the reaction below. Don't forget any small molecule byproducts, if applicable. So there's the question. And then the other part of part B will be given the polymer below, what monomer or monomers could it have been made from?
Would that be something you would draw out?
Draw out and submit the picture. And that's why they're split. Well, and it gives you some extra time. So it's split so that you can, you can do them in either order. The pre-test, this is in Moodle instead of in Gradescope, but again, we'll be using Gradescope. So there's the pre-test is essentially what will be part B will be like. Okay. And look, there are the solutions. So I strongly encourage you to just try and do things before watching the solution videos. There's all kinds of research that shows this is a better way to learn. The act of struggling to figure out the answer helps you retain the information. So if you just look, like if you look at the table, that review table, and you're like, oh yeah, okay, now I can do it. That's less effective of not looking at anything, trying it, getting it wrong, and then figuring out how to do it right. Or getting it right and verifying that you got it right. The act of struggling through helps you retain information. So yeah.
You fire more connections and synapses and stuff when you do something wrong and learn from it than if you just do something right because you're not learning anything new.
But even if you do it right, if you're like sort of struggling, not sure, and then you verify that it's right, one important step is don't wait too long before you figure out if it's right or wrong, because that's how misinformation can get stuck in your head. And that's one of the reasons why we do the quiz and we go over it right away. Does that make sense? So, if you choose to do the pretest, which I encourage you to do that. Watch the videos pretty quickly thereafter, so you know if you did it right or wrong, and then correct what you did. So that act of correcting your mistake will help you retain it. The other thing that's research-based is if you can study for less time overall if you study a little every day.
I'd love to have time to do that.
It will save you time in the long run. So one of the things I will do is I have a video I recorded that talks about learning strategies that are all evidence-based and a reflection on exam 1. So you can, which you can turn in for extra credit if you want. So I'm gonna turn on some things that are under exam 1, and I'll send an email with that when it happens. So, and it's all sort of what I put in that opening document. How to succeed in T200. It's there as well. And the person who I took all this information from, she has a book, Sandra McGuire, and I've had the privilege of seeing her speak a couple of different times. She says that it's not very effective to talk about it before the first exam. Wait till after the first exam, and students will be more receptive. So I try and take her advice. Her results are amazing. She used to teach freshman chemistry, and the difference with the interventions and stuff was really impressive. So she talks about the study cycle and that kind of thing. So yes, she wrote that book. It is, and it's free through the library. Yep. So it's like something like Teach Yourself How to Learn, How to Ace Every Class, or something like that by Sandra McGuire. And the one for instructors is called Teach Students How to Learn, or something like that. But it'll be in module, it'll be under exam 1, the link to the book for the libraries and stuff. So, questions on exam 1, 2. Mm-hmm.
How can you tell, like I was doing some review earlier, how can you tell if a molecule is bifunctional? Like, will we have to be able to tell if it can polymerize that way? I mean, I think so, but I just can't remember how to tell.
So you need to be able to recognize a few functional groups. Well, recognize and know what they are. But you can recognize lots of functional groups, even if you don't know what their name is. So if a molecule has 2 functional groups, it's bifunctional, right? If it only has 1, it's monofunctional. So there was an example of this in problem 9 of that first weird problem set.
When it's monofunctional, that's when they have like the teddy bear, right? And they can only grab with one hand.
Right, exactly right.
Bifunctional, they're like, hello.
Yep.
Okay.
And, yep, so that's exactly right. And then the other, if you think about the squigs, the little yellow ones only had 1 sucker. They were monofunctional. 2 suckers, bifunctional, or difunctional, doesn't matter. Okay. So the ones we know, right? 2 alcohols, that's bifunctional, the diol. If I just have 1 alcohol, monofunctional. I can replace the alcohol with an NH2, it's an amine. I can have a diacid or a monofunctional acid. If it's not bifunctional, it can't polymerize. And the step growth monomers, you might not, you're like, oh, there's a double bond. How do I know that that's bifunctional? You gotta think of the little face, he was the sad face, right? Mm-hmm. And then when he's initiated, bifunctional. That's why I like that video so well. It really shows, they open up their 2 little arms. Now you can see they're bifunctional.
And like, aren't a lot of the initiators monofunctional?
Yes. I showed you an example of sodium metal that's bifunctional.
Oh.
But most are going to be monofunctional. So the chain is going to grow in one direction for the initiator. How do you know if it's trifunctional?
If they have a 3rd arm.
Yeah. What happens if you polymerize something that's trifunctional? A network. You make a network. So you can call it a cross-linked network, cross-linked, a network, a gel, there's lots of words, but it's not just a regular polymer if you're polymerizing something that's trifunctional.
Will we have to worry about tri-functional in the test?
Yes, you should be able to tell if something's mono, di, or tri.
The way that we do like the drawings with like the polyesters and the polyamines, we don't have to worry about doing those with tri-functional.
Good.
Good. Would that have like would it have like an arc? Would it have like the like bracket on the top or the bottom?
Yeah, we wouldn't get that far.
Oh, okay.
But yeah, it just grows in it goes in multiple directions. So you wouldn't really be. It's not something that you can easily just write down. It's more like it with you just do right. It's branches off of branches kind of deal. It's not.
So it wouldn't be one that we'd have to like draw out.
Yeah, you wouldn't have to like write it. Because what else? You have a question, somebody else probably does, and they're probably really happy that you're asking it. So.
Well, we need to identify the chain transfer.
The only chain transfer that I would ask you about would be for termination. So chain transfer is not going to be one of the options in the multiple choice question. But chain transfer that results in termination, yes. But
When will the pretest be open?
hopefully tomorrow. Oh, the pretest is open. The template should, I hope to get out tomorrow. But yeah, no, the pretest is already available to you guys.
Is that this right here?
Mm-hmm. Yes. Anybody have questions about the one homework we didn't go over in class?
The one that was in module 6.
5. Like with carbonate and urethane and.
Yeah. Could you like put it up so we can see if we or like are the answers on the Moodle?
Yeah, there's a video solution.
Oh, okay.
Yeah, for all the homeworks.
Yeah. Okay. Yeah. So that one, one of the reasons why I'm not concerned that we didn't go over it in class is I'm really, my objective with that homework was to show you, even though we just learned esters and amides in depth, and that's what I'm asking you to know for the exam, you can take that knowledge and a little bit of internet searching and you can figure out the reactions for any of the typical polymerizations. They're not so hard because if it polymerizes, it's a really well understood reaction and it doesn't have, it goes, right? Because for step growth, it's got to go way over 90%, 99% completion to get to high molecular weight, right? So. We good? Want to just end early? Any other questions? Everybody registered for next semester yet?
No.
Met with your advisors?
Yes.
Did you have a question? No.
Will we be able to ask extension like last time?
Yeah, you plan ahead. So, okay.